Okay, everybody, let's get started. Good morning. Thank you for coming to the workshop on Frontiers of Applied Statistics and Marketing. My name is Kinshuk Jerath. I'm a faculty member here at Columbia. And today I'm representing the American Statistical Association that's organizing this workshop, specifically the section on statistics and marketing. So let me talk to you a little bit for just 5 minutes about ASA, about the sponsors, about the plan for the day, and then I'll let the action start. So let me tell you a little bit about the ASA. So the section on statistics and marketing specifically. This is a special interest section under American Statistical Association. The aims of this section are to foster the development and application of innovative statistics methodologies for problems in marketing. And we'll see some of that today. And also to communicate that. And also encourage cooperation between academics and practitioners. So we do actually have several practitioners here today. Also the members and the executive committee comprises of academics and practitioners both. And even in the executive committee, you can see there's a very healthy mix of academics as well as people from the industry, and sometimes even the chair is sort of alternates and so on. So it's a great section to be part of if you're interested in this sort of thing. And I encourage you to take a look at that. I'll tell you a little bit about our activities. Our activities are mainly one of the main things is the section interest sessions at the joint statistical meetings, which is every summer. So this year it's in Baltimore. It's at the end of July and start of August for about 5 days. We have monthly online webinars on the applications of statistics to marketing questions. These are led by academics as well as industry people. We have an online discussion forum for, if you have a question, you can post that and others can respond to that. And we have occasional workshops like this one, and hopefully this one can become more regular. We also give a bunch of awards for doctoral research. So one is doctoral student awards for travel to the joint statistical meetings. So if you're interested, please apply. You can go to the website, which I'll share with you in a few minutes, and apply there. We also have doctoral dissertation research awards, which is something that we started this year. And so on that note, let me tell you who are the 2 winners for this year. The 2 winners are Dan McCarthy. He's from University of Pennsylvania, and his work is on customer-based corporate valuation. So how do you take CLV, customer lifetime value, and add it up across customers to get a valuation for the firm? The other one is Andrei Simonov, who's from University of Chicago and is actually going to be a faculty here at Columbia starting in July. And he's working on bias in news in the Russian context. So very interesting work. Actually, both of these speakers, both of these are going to give online webinars over in the summer. So if you're interested, please do look it up on the website or just email me if you want any details. And my email address is on the program, so it's easy to get. So please do visit us. I don't want to take a lot of time talking about this, but just wanted to sort of tell you a little bit about it. This is our website. Please visit us. Please become a member if you think this will be useful for you. Let me tell you a little bit about Data Science Institute, which is providing this room and this building and a lot of our resources and the coffee. So the mission, this is an institute at Columbia to promote data science. It has over 200 affiliated faculty from across different fields, so engineering, statistics, business, economics, journalism, medicine, astronomy, everything. So it's a very nice resource. They work closely with the industry. It has an active roster of events, about, I would say, 2 events a week almost, and very high quality ones. So please do take a look at DSI website as well. You'll find a lot of nice resources and events there. And also under the DSI is the Center for Financial and Business Analytics, which is also sort of a separate sponsor for this workshop. So they are actually the ones who are really providing the coffee. The DSI is providing the space. So the goal of this center is to, as the name tells you, develop analytical and computational tools to manage risk and support decisions using the great volume of data that we have. So if you go to the Data Science website, Data Science Institute website, you will also find easily a link for the center, so please do check it out. Okay, so let me come to the workshop. The workshop today is going to have two themes. One is causal inference, the other is text mining. So we'll start with the first one first. These are all our speakers. So we'll start off with Navdeep Sahni, who's from Stanford, and he's going to talk about designing and running online experiments. He'll be followed by Stefan. Now, if you look at these photos and you compare across them all, you can see that the one person who's not yet a professor is Stefan, but he's going to be very soon at Stanford GSB. So he doesn't have that formal professorial photo yet, but I think it's coming anytime now. Then we'll have Eva. So Stefan is going to talk about estimating heterogeneous treatment effects. Then we have Eva Ascarza, who's a faculty at Columbia in marketing. And she's going to talk about when you have any intervention, a company does an intervention, what is the impact of that on people who are related to you in terms of, let's say, phone calls or any other graph. Then we have the keynote speech by Professor Eric Bradlow, who is here from University of Pennsylvania. That is also on the theme of causal inference. We'll touch upon that. So then we'll break for lunch. And in the second half of the day, we'll have Olivier Toubia, who will give a tutorial on text mining. So Olivier is a professor at Columbia, followed by Oded Netzer, who is going to talk about how the text you write sort of gives out tells things about you in terms of how honest you might be in terms of when you apply for a loan, and how diagnostic is the words and the text that you use. And finally, at the end of the day, we'll have Professor Asim Ansari, who's also a faculty at Columbia, and he's going to talk about text mining applied to recommendations, personalized recommendations, and search. Okay, so that's the plan for the day. Promises to be a great day. I'm really looking forward to it. This is the program with the timelines and all. So copies of this are also available outside, so you could pick one up if you wanted, or you could just go to the website and see it. Logistics, just a minute about that. So everything, breakfast, they will have two breaks, one in the morning, one after in the afternoon. So these breaks and the lunch will be outside in the lobby. And please don't bring food and drinks into the auditorium. That's not allowed. All right, so and then at the end, we'll have a reception that's from 4:30 to 6:30. It's in a restaurant close by called Burnham and Schwartz. It's between 113 and 114th Streets on Broadway. Very easy to get to, just a 5-minute walk. And you could enter if you have pre-registered for that. Right, so that's it. Thanks for being here. Enjoy the day. And I'll give it over to Navdeep. Thank you.
Can you hear me? Is it? Yeah. Yeah. All right. Thanks, Kinshuk, for the introduction. It's a pleasure to be here and be discussing this topic, which I think is very important and coming up in marketing. It's already come up now. So experimentation is a very transparent and easy to understand tool when the experiment has already been done and the results have been presented to us. But there are a lot of, I think, little things that can improve the value of the experiment. And my objective today is to give a little bit of a high-level understanding of what those things might be, and also get into a few examples to make the understanding clear, because otherwise the discussion can be a little abstract. Okay, so that is the objective. So typical marketing problems are, here are a few examples. What is the marginal return of the dollar that I'm spending on advertising? How do I optimize my advertising campaign? Or who will respond to my advertising campaign? So all of these questions that I put up here have some sort of a causal relationship that goes into solving these problems, right? So these kinds of questions are very suitable for experimentation. Okay, but while these questions are very common, a lot of marketers, advertisers are asking these questions. Notice that nobody's asking the simpler version of the question, where nobody says, what was the marginal value of the ad that I showed yesterday? Okay, who responded to my campaign yesterday, right? So those are there's simpler versions of these questions that can be directly answered by experiments. These questions cannot be directly answered by experiments, okay? So related simple problems, what was the marginal return from the ad spend that I had yesterday, and these are the corresponding simpler versions of the question, okay? So an experiment is obviously done on something that we had in the past. It can directly tell me whether my last year's ROI was positive, what it was, if the experiment is done correctly, but it cannot directly be translated to the future, and that's where the challenge of experimentation comes, okay? So experiments can differentiate, an experiment can be different from the other one in terms of the extent to which it can answer the more relevant questions, okay? So that is basically a main point that I want to drive in, right? So a good experiment will be able to go much more further in answering the more relevant questions, and simpler questions can be important in certain settings, but not always relevant, okay? So here is an overview in that spirit for what I mean to talk about today. Okay, so first half or even more, I want to talk about designing online experiments and certain aspects of it that do not come up. So, for example, I was not able to read them up in a textbook. So, if we can spend more time there, I'll be fine with that. And you feel free to ask questions about that as well. Then I'll get into, so within the designing of experiments, the role of priors, the role of theory. I'll give a couple of examples to get those points through. Then certain issues like outcome variables to track what is the role of that, the unit of randomization, what's the role of that, power calculations, and then move to execution. Of course, it's very difficult to give prescriptions on tips on execution of experiments, but I'll try my best to give a few points that I've learned from my experience, and then certain things. Even though an A/B test can be very easy to analyze, after running the experiment, we always want more and more from it, and there are a few things to keep in mind when we analyze experimental data, and I'll discuss some issues there as well. Okay, so let's make it interactive. So if you have any questions, feel free to ask me. Okay, so let's start with some basic notation here. So we have a treatment. Treatment could be, in the marketing context, it could be an email promotion, it could be an advertisement. So the question is, what is the effect of my campaign or my advertising campaign? So the treatment effect, we define it as, okay, this is my relevant population. If I start this advertising campaign, the outcome variable for each one of you is going to change. I just want to know the average of that, and that is the treatment effect, okay? But we cannot change the whole, because we just have one world to live in. We can't experiment with the whole world, so we design experiments. We randomly pick a subsample of the population, and one subset gets a treatment, the other subset does not get the treatment. And if we do that, we get the average outcome for the treatment population, the average outcome for the control population. Okay, that is the first line there. Just adding and subtracting the second term, we can see that we can rewrite that expression as the treatment effect on the treated population plus the inherent difference between the populations. Okay? Now, if the randomization is able to balance the individuals across the treatment and control group, then the inherent differences are going to disappear. They're going to be 0. Okay, so then the only term left is this one. Okay? This is still not equal to the treatment effect. There are certain assumptions that go into this being equal to the treatment effect. One assumption is that the population that you're experimenting on is a relevant population. Okay, so if that's there, so that's obviously required. The other thing that's required is that the treatment has the effect sort of satisfies the sattva assumption. The assumption is that me treating an individual, the effect does not depend on who else is being treated in the population. Okay, if the effect of treatment on an individual depends on who else is being treated, then of course the effect is going to depend on the size, the proportion of the treatment group, and that can affect whether delta hat equals to delta or not. Okay, so these are a few assumptions that go in. Okay, so delta is the treatment effect that we want. Delta hat is what we can get from a randomized experiment. If randomization is done correctly, then inherent differences disappear. If the experiment is done on the right population, that's one thing needed. The other thing to keep in mind is that this assumption is what we are making while making causal inferences about the treatment effect. So there is recent work on how we can adjust statistical inference given violations in Sattva. So there is work by Susan Ethy, Dean Eccles, and Hiro Imbens who talk about this in at least a couple of papers. Okay, I'll recommend you take a look at that if you think that this assumption is going to be violated in the setting. Okay, so this is the basic setup. Now coming back to the earlier point, we run an experiment in a setting. We estimate the treatment effect with our method, and the treatment effect, of course, depends on the characteristics of the population. Okay, I'm denoting that by two vectors. One is x, which is observed to us. There's a lot which is not observed to us. Okay, and then the objective usually is, even if the experiment is being extended within the same company, we typically want to learn from an experiment and predict about treatment effects in the future. Okay, so x's and epsilons may change in the future. So the objective most often is to say something about some other x's, some other epsilons. Okay, so the state of the world is going to change, and a useful experiment is going to be able to tell me something about, okay, how does the treatment effect change when my situation changes? How is it going to be? Is it going to be stable in the future? Is it going to change in the future as well? Okay. If there was nothing unobserved and my current experiment spanned the full space of x's, then it's not a problem because I can just look at the relevant portion of my sample and extend the findings to the future, but unfortunately a lot is unobserved. So the typical approach we take is to design experiments that uncover a mechanism. Okay, so something that goes back to the theory, and the theory then guides us to extend the findings to the future, okay, or to any different setting. So a couple of takeaways from here. So one thing is that, of course, say I'm designing, I'm trying to learn about advertising campaigns. If I don't have this goal in my mind, I might end up running a campaign where it's a simple, so I collaborate with a company, we want to know the effect of advertising. I might just run an A/B test that'll give me the treatment effect, the ROI of a campaign that has been run, but I might be clueless as to where and how this will be extended to other settings. Okay, so while designing the experiment, we got to keep this in mind. Okay, the other thing is when we describe an experiment, it's good. See, when we write down an experimental paper, we should know that this is the goal in the end, because we're not just interested in what happened, we're interested in knowing what will happen. So relevant details about the experiment should be described in the papers. And I think this is where our experimental papers can improve. So having a theory, a model in mind can help us describe experiments and provide relevant details as well. So this is something that might get missed now and then. Okay, so these are high-level things that I wanted to talk about. So there is a related debate going on in economics as well. So Angus Deaton has a Journal of Economic Perspectives paper that talks about the fact that experiments are gold standards in describing what happened, but in order to extend and generalize to other settings, the gold standard may not exist, because obviously we need to make some assumptions in going from one experiment to the future. So something that I just wanted to mention, you can take a look at that if you're interested. And then Ludwig, Mullainathan et al., and they also are calling for mechanism-driven experiments. Their point is that if you already have a mechanism in mind, the design of the experiment can be such that the experiment can be cheaper and it can be run in a more convenient way. So the point is that the call for mechanism-driven experiments is more general in social sciences. In the field of marketing, I think we do, the field of marketing recognizes the value of mechanisms. It's ingrained in the field. We have a behavioral side of the field as well. So this is not in general a problem in marketing, but the design of experiments can be more aligned with theory. That's one direction we can get to. Okay. Now, all this is good. Okay, so I'm convinced that we need to do mechanism-driven experiments. We need to test theory, but yeah, we are talking about field experiments here. Okay, so the field is not my lab. I can't take a theory and go to a business and say, hey, I want to test this. If I do that more often, I just don't get much good responses. So we are constrained by what the businesses are interested in. Very often when the funding for the question is limited, we do rely on businesses to run experiments. So the mechanisms, the level at which we can usually test in the field gets constrained by what the business is interested in. Okay, so there is some sort of a balance that we need to strike. We want to learn something about theory, but we want to also learn about theory that is relevant to the population. It's not that theories are not all theories are relevant. That's not what I want to say. But businesses may not care about the depth that we care about in academia. Okay, so sometimes when we start projects, there may be too many theories, and there may not be much guidance as to what is more relevant for a setting and what is less relevant, and that can also be a deterrent here. The third thing is, if we are strictly testing theory, then not all constructs might be manipulatable in the field. So for example, customer expectations are much more harder to change in the field than in the lab. Okay, so there are a bunch of challenges to my previous point, which was calling for theory-driven and mechanism-driven experiments, especially if we want to take this to the field. Okay, so what I want to do next is I want to give an example from my own experience, because I can talk about that in more detail, of a setting in which we tried to balance these multiple things. We wanted to learn something more general, and we also wanted to be able to prescribe something by the end of the experiment so that the business is ready to collaborate with us. Okay? So this is in the context of a very recent paper on retargeting. So this is the paper jointly with Sridhar and Kirti. Sridhar is in Stanford and Kirti is in Santa Clara. The focus of this discussion is not too much on the findings of the paper, but the process of implementing the experiment, coming up with the problem area, coming up with a refined research question, the trade-offs in the design, the conditions that we came up with, and some subtle features of the experiment design that helped us run the experiment. Okay? So first of all, the big problem area that this company that we collaborated with was that, okay, we are spending millions and millions of dollars on retargeting. Is it worth it? Should I keep doing it, or should I stop? How can I optimize my retargeting spend? Okay, so that's the problem area that they have. Typically, in my experience, when I've talked to advertisers, they compare click-through rates from retargeting with click-through rates from display, and they say, hey, retargeting is very good because it's giving me so many clicks. But as you can imagine, the retargeted population is the population that visited the website very recently, and therefore it's a very, very super self-selected population. So we can't just compare click-through rates across campaigns. So there is an inherent problem here, and it seems to be very well suited for experimentation. Okay? So now, one thing we thought is, okay, one thing we can do with a very high-powered test is to run an A/B test, put a random set of people in the treatment group, show them retargeted ads, a random set in the control group, don't show them and compare and say, okay, what is the value of the campaign? Now, that would have been good, but it would have been slightly dissatisfactory because then extending it to other settings would have been difficult because, as I'm going to talk to you in a minute, retargeting is sort of a puzzle. At least I did not have a good model of why the effect might be happening going into the paper. Okay? So the goal is to learn something which can be generalized beyond the context, something more basic than just the effect of retargeting in one setting. Okay? So even that would have been good, but there's a lot of benefits to going one step ahead, I think. Okay? All right, so we began with this introspection. Okay, why do we think advertising works? The typical model we have about advertising is that it spreads awareness. Okay? It tells people about the existence of the product, or it reminds them of the existence of the product. There's a question, yes.
So can you define what you mean by retargeting?
Yeah.
You're showing the ad to a different population. Is that what you mean by retargeting?
Yeah.
What do you mean by work? Right? You use the word work. Right? What does that mean? Right? It must be a comparison of lift, right, compared to what happened in the past.
So the first question I understood, the second one I'll need some clarification. Okay, so retargeting is a format of advertising in which the advertiser shows ads to people who were on the website a minute ago and checking out the product. Okay, so I go to Zappos.com, I look at a pair of shoes, I decide not to buy it, I leave, and then I see the same pair of shoes following me over the internet on different websites. I go to Facebook, I see the same pair of shoes. I go to CNN, I see the same thing. So that's the format of advertising, and that's retargeting. Okay.
And what do you mean by work? And how do you
Work? Oh, okay. Does retargeting cause a change in consumer behavior that the business values? Okay.
He has to come back and buy something.
Yes, he has to come back and buy or has to achieve a goal that the advertiser has set for the campaign. Okay. Thanks for letting me clarify. All right, so the typical model of advertising that we go into is that, okay, it spreads awareness, it tells people about the product, or it reminds people of the product, okay? But retargeting in itself sort of stands at odds with this view because by definition, retargeting is targeting people who are aware of the product, they have seen the product, they decided not to buy it. And also retargeting happens immediately, at least platforms take pride in showing the ad to people within seconds of when they leave the website. Okay, so these kinds of things on the face stand at odds with the standard view of advertising that we take in general. Okay, so let me give you a concrete example. So this is from my own experience. Last year we were expecting to have a baby in October. So I was checking out rocking chairs on Babies R Us. Okay, so I left that website to see, okay, what might happen in the election. I went to this website and then I saw the same product that I had seen a minute ago, at least in 5 different ads on this page, okay? So all the products here are the ones that I had seen and decided not to buy. The top slot, the right slot, this one, all of them are covered by the same ad, not very different from each other, okay? So this is what I mean by it seems like it is not directly in line with the awareness spreading view because I just saw this a minute ago. It's not like it was months ago that I'd seen it. Yeah. Oh, yeah. Even though the advertiser intends to stop the campaign once a person buys, but there's a lot of noise in the marketplace. Tracking isn't perfect, so you might be subjected to a lot of advertising for products that you already bought. That makes you wonder. Okay, so that is sort of the motivation. That is the first step of introspection we had given this question. Okay, why would this thing even exist? It's not totally clear to me why this would work, especially if this is the strategy that the campaign is taking. Okay, so this is what we started with. It seems like retargeting stands at odds with the standard view. That helped us sort of refine the research question a little bit. Okay, so it tells us there's something interesting to be learned here. If retargeting ads work as intended, if they work immediately after people are leaving the advertiser's website, in that case, we might learn something about why advertising works in this setting. So there might be something to learn about the mechanism, and the advertiser will gain from quantifying the benefits of advertising. If this is the case, if it does not work as intended, in that case, the practice needs to be updated because right now a lot of advertising is happening at possibly suboptimal level if it does not work as intended. By intended, I mean showing ads, flooding people with ads immediately after they leave the website and showing the exact same thing that they had seen. Okay. There are a lot of details in the paper that I might not get into, but just to talk about the process of developing the question and coming up with the research design. Okay. All right, so if the ads work, what could be the effect? Okay, first is that, as I said earlier, maybe there's absolutely no causal effect in anything in consumer behavior. So in that case, it's totally possible. We've seen that in eBay experiments. Firms could be spending suboptimally. That was one possibility we were ready about. The other thing is, okay, if there are informative effects, by informative effects I mean if ads remind people of the existence of the product when they forget about it, or they tell them something new about it, ads might work only later, not immediately. In that case, we need some temporal variation in our experiment to test whether this is happening. Okay, effectiveness of ads might vanish with frequency. If it's an informative effect, in that case, I don't need to show the ad 100th time in the same week. I should stop after a few impressions. Okay, and then advertising now is going to act as a substitute for advertising tomorrow. So if it's just about reminder, if you remind me right now, the reminder for tomorrow has a lower value. So there's some sort of a substitution that comes inherently with this effect. And then it's also less likely to affect consumers that are more advanced in their purchase process. Okay, so this is the priors that we have given the mechanism direction that we are thinking. Then there are other possibilities as well. Okay, so we don't want to go into the experiment with this standard view only. We want to be open to other possibilities. One possibility is that by flooding consumers with their ads, the advertiser is blocking and blocking competitors and not letting competitors show their ads here. There are other possibilities like the mere exposure effect. It's possible that by showing the ad over and over again, there is perceptual fluency and consumers start to like the product more. That's a possibility. It doesn't. It's not the standard view that I went into the experiment with, but that's still a possibility to be open about. Okay. So our priors at this point were, hey, even it's possible that there is nothing, there's no change in consumer behavior, or there is some sort of an awareness effect happening. In that case, we have certain directions that the theory takes us in, and we can test whether that's actually happening in the data. Okay. So this is the motivation for our experiment. There are constraints about implementation. I can talk about that in a second. But the overall design was that advertiser can control frequency caps for campaigns like retargeting. So we randomly allocated people to different levels of frequency caps across the 4 weeks of the campaign. You either get a low, zero, low, or high level of frequency cap, and this is varied across the 4 weeks. So there are 81 conditions that a person can get allocated to. 0, high, low, 0, or any other combination of this. Okay? Now, the good thing about playing with frequency caps rather than trying to vary actual impressions is that in the end, when the experiment is done, the advertiser will have an immediate takeaway because one of the different 81 strategies is going to be the better one, and they'll know what benefit they get if they implement one of these 81 strategies. So the prescription side of this experiment design is much more appealing to the advertiser, okay, than an alternative I can talk about in a second. Okay, so each strategy that we are putting people into so each condition is a strategy that the advertiser can play. Okay, so this is slightly different from an alternative experimental design strategy you can take. So imagine a different design in which you collaborate with the platform, and then every time a person comes to the platform's website, you decide whether or not to show the ad. In that case, right now the experiment is generating variation over weeks, but you can imagine you can generate variation over hours or minutes or days as well. So our design is not doing that. It's just creating variation over weeks. It's not creating more granular variation here. That's the trade-off we are making. The benefit of the design that I just described to you is that by the end of the experiment, I don't need to estimate a model. I directly get to evaluate strategies from this space of 81 possibilities. If I took the alternative, I won't have enough observations for one specific strategy. I might have to aggregate. I might suffer with power issues, or I'll have to estimate a model to make prescriptions to the advertiser. So this is sort of a balance that we are making. In this case, because we were collaborating with DoubleClick doesn't even allow us to do this. So there are certain other constraints that pushed us towards a more prescription-oriented experiment. Okay. So another thing that happens because we are running this campaign in collaboration with a platform which is far away from us. Yes, question?
Real quick on the design piece. So doing the more complicated experimental design gives you a lot more information,
Yeah.
but practically that might be a little harder to do, implement, or to convince people that's necessary. So do you have any practical advice on should you do a simple RCT and then go into one more of these
Okay, so can I give you a definitive answer on that? I don't. See, in my experience, I've tried both. The complicated design requires a much more detailed collaboration with the platform. What I would say is that it's good to try that. I found it good to propose that. But you can get a sense very quickly whether or not that's going to happen. So I would just follow a fail-fast strategy, propose it, and if you think there are hesitations, then it's not going to happen, because it's going to take months of implementation for that kind of a design to go through. And you getting the granular data at that level, and the level of second and that kind of variation. So apart from that, another issue that comes up when in the field of advertising when we want to run experiments is that the campaigns, so platforms like DoubleClick or even Facebook or Google Display Network, they don't share with the advertiser outcomes data like page visits or purchases for individuals who did not see any ads from your campaign. Okay, so for example, if I implemented the design I talked to you about a minute earlier, I will not have outcomes data for control group. Okay, so I cannot estimate the mean outcome for the control group, and therefore I can't do a simple A/B comparison at all. Okay, so that's a problem. That's general in these kinds of platforms. Okay, so there is an alternative solution that has been suggested by Garrett Johnson, Randall Lewis, and people at Google, which ask the platforms to give this data to the advertiser, but it was not available. I don't think it's still available for the complicated design that we want to run. So in that case, we had to come up with a workaround. Okay? So our solution was that to every person in our experiment, we expose them to a dummy ad. Okay? Every person in the experiment gets to see just one impression of a PSA, a public service announcement that is sponsored by the advertiser. By giving an impression to this one exposure, we in the experiment are now going to see data for everybody. Okay? So we don't need to spend money on the control ads, showing ads to everybody. We just need to show one impression to every individual and tag the individual. Once the individual is tagged, we can see the outcomes data now in the DoubleClick logs, and therefore we can do our A/B comparison. Okay? So more details about this in the paper, but I just wanted to say here that even after all that introspection, coming up with the experiment design, there are more difficulties that can come up with, and these kinds of things can help you get over the implementation issues. Okay, so with this experiment, just real quickly, we were able to conclude that advertising is working at a high level at every point of time. So the optimal out of the 81 strategies was a high level of advertising in week 1, high level of advertising on week 2, 3, and 4 as well. So that was the best one, which is counter to the view that we went into. We also found that even within the first week, so the first week had the biggest effect compared to the second one, compared to the third and the fourth. And even within the first week, the highest effect in terms of getting people back to the advertiser's website was happening in the first few days. The first day in itself was responsible for a third of the effect of the first week. So a lot of the effect is happening on the first day. Week 1 and week 2 are complementary to each other. So if I don't advertise to a person in week 1, the value of advertising in week 2 is low. So keeping on advertising in week 1 creates value in advertising in week 2 as well. And as you can see, this is counter to the standard awareness mechanism that we went into the paper with. So we were able to learn something about the mechanism here. The data are more consistent with a competitive blocking kind of a mechanism rather than an awareness mechanism. And in the end of the experiment, the advertiser was, they didn't have to get involved in all the nuanced discussions. They just had to know the means for these different strategies and a qualitative prescription about why they might be happening, and they were happy and they moved on. Okay, so we didn't have to estimate a model to make a quick prescription to them. Of course, extending to other settings and generalizing does usually require making assumptions and estimating a model. Yes?
So were these all people that had been to the website?
Yeah. Yeah, so this is a field experiment in the sense that this is a live campaign. So this was done in collaboration with BuildDirect.com, which is a seller of home improvement products. So the experiment was run on people who come to the website and leave, they enroll into the campaign, they get allocated to one of the different conditions for the DoubleClick campaign that the company was running at that time. DoubleClick is a company that conducts retargeted advertising.
But there's no point in concentrating that to someone because you should be showing it to someone else instead, so it takes into account in your calculations.
Oh yeah. Because so a person in our control group could have been seeing anybody's ad, so we are not blocking or doing anything with that. So our control group, for example, is simulating a world in which this company does not advertise on DoubleClick. Yes?
So I understand how it's counter to the informative view. Do you track things relating to the other advertising to support the idea that it's actually displacing other?
Yeah, so no, we don't have data on ad impressions people are getting from the competitors, concluding definitively that this is displacing other competitors, and also those displaced ads had an effect for the competitor. That requires a very different design. Okay, so I don't want to get into the details of how we can conclude this mechanism here. I want to still tell you that the priors did play a role in design of this experiment. Okay, so there was clear priors if you read the literature in the industry as well about how retargeting might be happening. Awareness and reminder is the mechanism that people have in mind. So that is the prior we went into with. Even in our academic research, that is the main model. Retargeting seems to stand at odds with it, and the data shows that it does actually work the way it's being done. It doesn't work after waiting for a little while, like what you would expect. Yes? In this case, all we had to do is, because we observed data for each one of the 81 conditions, all we had to do was calculate the mean outcome that they care about. So in this case, whether or not a person comes back to BuildDirect.com, how much they engage with BuildDirect.com, and so forth. And we can just take the means for each of the conditions and compare them. Yes. Given the design, we didn't have to do anything in the end. All the work went into before the experiment was done. Okay? And then another decision we had to take while designing this is that if we were doing a simple A/B test to compare the effect of retargeting with no retargeting, we would have had much more power because we would have had 100 times more observations per cell. But as I talked about earlier, that would have told us a little bit less than what we can say now. But we would have seen much more outcome measures and more power to detect effects in more downstream measures as well. So that's a conscious decision we took initially while designing the experiment. Yes?
From the company's point of view, isn't there a last step that they want to do the sort of cost effectiveness trade-off?
Yeah.
Assuming there's a price for more advertising?
Yeah. So all that is doable with the data that we have, because you actually observe the impressions that were given, you know the cost of the impressions that were given, you have the outcomes data, you have the value of the outcome in this case, what is the value of getting one person back to the website who would have never come back. So all these kinds of metrics they had. And the only thing missing going in was the effect, and they could just plug in from this experiment, that missing. What do you mean by did not correct for differences?
No, I mean that the guys who replied, let's say, policy or treatment group versus non-treatment group, they might have very different.
No, so this is a randomized experiment. So this is people who get allocated to one of these conditions are randomly chosen. So the prior characteristics, and we verify that in the data, they are similar for all these people. So it's a randomized experiment. So people who get into the control group versus full high-level advertising, they are same in terms of their characteristics and their preferences and everything. That is what the randomization bought us in this context. Yeah.
So maybe the question is, if I'm going to spend $1,000, I could spend on retargeting or I could spend on other types of campaigns. So would you be able with this experiment to help the firm decide whether they should spend on retargeting or some other type of, and maybe, so maybe.
It's similar, because actually the whole point samples more comparable because you don't know how similar they are?
I think these are two different questions. So that thing is taken care of by randomization, because if I'm randomly picking a population, putting some of them in the treatment, some of them in the control, in that case, they're going to be comparable. Right? So we can talk more if there's something else. To your point, where should I allocate my money now? All this is going to tell you is the returns you get from this campaign. Okay? If you have done similar studies with other campaigns, you can compare the returns and decide where you are getting the most benefit. Okay, so the objective here was to illustrate that a few steps that we took in introspecting before designing the experiment, and that influenced the conditions which we actually implemented, and told us something about why retargeting might be working and when it might be working. Okay. All right, so let me, how are we doing on time? All right, 20 minutes, okay. So let me touch upon a few other issues about experiment design and give you some short examples there, and then a few points about analysis that we can keep in mind. Okay, so one thing is that when we push to test theory in the field, it's important to keep in mind that the stimulus that we make, the actual manipulation that we make, is within the realm of what consumers are expecting. So showing something very, very odd to people who are not expecting that can lead to very unusual outcomes in the field, and we need to avoid the Hawthorne effect. So something to keep in mind: the experimental manipulation should not be very, should not act weird in the field. That's something just to keep in mind here. Then it's very useful if we can get multiple outcomes from the field experiment, not just revealed data, but also if we have matched survey data in addition to the revealed data, that can go a long way in providing evidence for the mechanism. So this is a paper by JP, Shuming, and others, where they ran a field experiment in collaboration with a company. They got the outcome measure. So in this case, the finding was that in settings where the purchase is associated with a charitable donation, in that case, the demand curve is not monotonic. We see that very high discounts do not really work. And that is anomalous to the usual demand theory. In addition to observing purchases, they also observed self-reported survey data for the population, and they were able to conclude, they were able to show convincing evidence that people are not buying in very high discount conditions because they don't get utility when the actual charity is being given by the company and not themselves. So this pro-social behavior evidence was shown in this case, and I think the matched survey data also played a role in showing evidence for this. Okay, so this is not always possible, but whenever possible, I think it can be useful. Okay. So so that was stated data. There are other settings that give you much more granular data. For example, if you're studying email advertising, email platforms give you much more data than just whether it was shown to people or not. It tells you whether people actually opened the email, so whether they actually saw the advertising message, whether people unsubscribed from the email, which is sort of a negative reaction that you don't get to see in display advertising, for example, and then whether people reopened the email in the future, whether people responded positively, whether people clicked to get more information. All these measures, this hierarchy of effects, and also some negative reactions of people in revealed manner can be given by these kinds of contexts. And in this one paper, we were able to use this to show some evidence for a detailed mechanism that we wouldn't have been able to show if we did not have all these measures, I think. Yeah.
Any advice here on once you do that, you're the issue of intention to treat versus those who were treated, and as you go down the hierarchy, randomization is not obvious. Any advice there?
So I think the point here is that if I'm looking at, say, clicks, If I condition on people opening the email and look at clicks, there's a selection problem because people who open the email are not the randomized people that are intended to show the ad to. So one thing we can do is not look at conditional means, but unconditional means. Okay? So just look at average clicks in different conditions instead of looking at average clicks among people who opened the email, and that can help. Now, of course, there are power issues that come up there because if you condition on opening, then you're much more closer to the actual mechanism that might be happening. There's more power there, but I think there's a trade-off, right? So I think unconditional means go much more further in terms of being clean and causal. The conditional ones are closer to the mechanism, but there may be biases there. All right, so having a hierarchy of effects can help, but of course, this thing is something we got to keep in mind. We got to look at unconditional means for randomization properties to be preserved. Okay, so then another decision that we might have a choice on is the unit of randomization. So should I randomize different markets or different consumers? If I'm randomizing more disaggregate unit, then I might have more power because I might have more observations that are randomized into different situations. There are certain contexts like, does my promotion work or not? If it's a store promotion that you might not have any choice, you might have to randomize stores. In that case, your observations are limited by design. The advantage of going with a more aggregated unit is that the sattva assumption may be weaker there than an individual level randomization. And even while analysis, if I have time, I can touch upon that. While analysis, especially while estimating your standard errors, you got to keep in mind at what level the randomization was done. Okay. And then, a simpler point, but we got to do this, is power calculation before we get into experiments. So I work in the area of advertising, and low power is an issue we face all the time. If you're doing pricing experiments, you might not suffer with low power, but still doing power calculations before getting into the experiments can be very useful. So one thing that we got to do before we do power calculations is to have an idea of what the effect size is going to be. A lot of the times, the businesses are helpful in deciding what that effect size can be. So for example, the collaborating company might say that, I want to run an experiment which is large enough to detect a 5% change. In that case, they are giving me ideas as to what the sample size of my experiment needs to be. Okay, so this is standard, you can find in any textbook on experimentation. Given an estimate of the effect size, given the power that you want, the type 1 and the type 2 error, you can back out what the sample size per condition is supposed to be. Yeah.
So you in an experiment,
yeah.
the sattva assumption would be violated, for example, other people who open the email send me an email telling me to open the particular email that you made out.
Yep.
Right? So that could happen, right? So how do you protect against that?
So sattva assumption can be violated in marketing settings, especially if the target population is so spread out that it's all over the world and you draw 500,000 observations from the whole world, then you may argue it's not that strong, especially if you know the way it's distributed. But in general, you might think that everybody is connected through a network, and in that case, you got to keep that in mind. I might not have time right now to get into the details of how you can correct for it, but I can refer to a couple of papers that talk about that. A very recent paper in JASA by Susan Athey and colleagues is something that I would refer you to for a discussion on this. Especially if you're running experiments on Facebook among people who are linked to each other, that's an assumption to think about. Okay, so given all this, who would be a good collaborator? A company that can implement a powerful experiment with the design that can help you learn something more. Okay, so now that's easily deducible. So one thing that, one little practical thing that I've learned right now is that if I go to a company and I start telling them things, they might understand something else from what I intend to convey. So it's good to ask questions and then link to what you are thinking rather than telling them your theories and effects. So that helps me a lot, asking questions and keeping to myself all the detailed theories that I'm thinking about. Another thing that helps is, starting a conversation and failing fast, so getting an idea of whether something's going to happen or not, rather than lingering along with the relationship and going 1 year into the experiment and then not getting anything out of it. That has happened to me in the past. We did a collaboration, we designed experiments, went all the way, experiment was done, and then they said, hey, we can't share these results for publication. So that's, it's good to write an agreement in advance, I think. Okay, and then while the implementation is going on, I found it very useful to be involved in each and every step of implementation, not relying on, so when a person tells me that I randomized, I often ask them exactly how they randomized, whether they used a random number generator or not. And sometimes what happens is when they say randomized, they're just they're putting people in a list, say alphabetically, and then the first half they give one treatment, the other half they give the other treatment. They may have used this sort of a strategy in some other past campaign as well, and that can affect your inherent differences disappearing assumption. Okay, so something to keep in mind. Okay, so this part of the discussion I wanted to spend more time on. The analysis part, I'll touch upon a few things to keep in mind. As we analyze data from experiments, I'll give you some pointers as to some places you can look at for more detailed discussions. The exploring heterogeneity part, I think Stefan is going to touch upon that in a lot of detail, so I might not have to cover that here. Okay. All right. So experiment is done. I got the data. The first thing to do is to check whether the inherent differences are actually disappearing in the data. Of course, I can't test that assumption directly, but I can check for other observables in the past and make sure that the treatment group and the control group are balanced. Okay, so this is related to a question that came up earlier. So if after doing the retargeting experiment, we looked at the past visits that people had made, past purchases people had made, all past impressions people had, and made sure that all of these characteristics were balanced across the experimental conditions. Okay, lag-dependent variables are a very good predictor of future dependent variables, and therefore being balanced on the lag-dependent variables is a good sign for the experiment. Okay. Now, estimating the treatment effect, the randomization lends us to a simple mean comparison, but oftentimes we want to say something more with the experiments. So our experiments are costly. We spend a year implementing it, so we want to learn more and more from it. So we are pushed towards estimating a model, which is obviously useful in extending the findings to other situations, to other subsamples. Okay, but running a linear regression on running OLS on experimental data is not, there are certain things to keep in mind. If after doing the simple treatment control experiment, I run this regression, regress Y on the treatment, the beta coefficient I get from this regression is an unbiased estimate of the treatment effect, but OLS makes some assumptions in calculating standard errors. So for example, the homoscedasticity assumption is something that would not have been made if I was comparing the means. So there's something to do there, just estimate heteroscedasticity robust standard errors, and that can take care of it. But this is something to keep in mind as we go forward with the experimental data. So David Friedman has a couple of papers that talks about caveats and estimating even simple models from experimental data, like logit regression or OLS. Some things to keep in mind. Okay. So my recommendation is that going ahead after running the experiment is usually a good idea. It's good to show the mean comparisons first and then estimate the models and touch upon these different issues that can clean up the analysis. Yeah.
Can you explain why the regression is?
Because the error term has a specific form at the extreme. So if you, so Friedman's argument is that heterogeneity may be correlated with the error. He gives specific examples as to where logit regressions can be messed up. There are other reasons where the outcome measure is so rare that you are in the extreme. In that case, the extreme value assumption can be a problem. In practice, these things go away when you have a very large sample, but still, my point here is to be aware of these assumptions so that, when we claim a gold standard in an experiment, it's good to keep in mind that there are certain caveats that we can check upon. Okay, so then, given that I have like 5-7 minutes, I'll quickly talk about this. There may be situations in which we have multiple experiments. We just don't have one. We have the opportunity to learn from a lot of experiments. The natural instinct that I can talk about myself, I had, and other people I've seen have had, is to pool all the experiments, run a fixed effect regression, so put in a fixed effect for every experiment and one treatment coefficient across experiments. If I run this kind of a regression, it's usually okay. But in certain situations, the experiment design is endogenous. So for example, a company doesn't run all experiments with the same design. The more expensive experiments, they keep a bigger treatment group. In cheaper experiments, they keep a smaller treatment group, and that variation is correlated with the heterogeneity of the target population, and that can bias the estimates significantly. In this paper, we realized that the bias was significant. There was a 30% or 40% change in the point estimate if we run this fixed effect regression versus the other method, which is go experiment by experiment and get a different estimate for everyone, and then aggregate and estimate the standard errors. Okay? So this problem is more general. There's a more recent working paper in BER that talks about the pitfalls of running a fixed effect regression when the actual randomization is chosen at different levels. The proportion of the treatment group is chosen at different levels in different submarkets of the analysis. Okay, so then, as I said, in contexts like advertising, power is a big constraint. So what we can do is we can reduce the noise in our Y variable by putting in controls. Okay. By randomization, if I add controls to my regression there, assuming I do have robust standard errors, my treatment dummy is not going to be correlated with X's. So if I put in X's, that should not bias my beta, but still there is a bias for small sample, and that again has to do with the heterogeneity of the actual treatment effect. And another issue with this is that a reader of the experiment may critique the experiment, saying that, how do I know that you didn't try so many different covariates and you got significant results in one and you're showing me that one? So again, multiple hypothesis testing becomes an issue here, and Angus Deaton talks about that in his critique. Okay, so again, to get over this, it's good to do a simple mean comparison first and then get to a regression with controls. Then if randomization is at an aggregate level and the analysis is done at the individual level, in that case, this is the kind of regression that you might be running. Treatment is varying at the aggregate level, but the outcome that you observe and the actual mechanism that you have in mind is at the individual level. In that case, the IID assumption across observations becomes a little strong, and the standard errors can get messed up. You might be overstating the precision of the treatment effect that you have. So a typical solution is to cluster the standard errors and allow for observations to be correlated within market. So that's something that I think is routine and should be done. The problem is that when you're running store-level experiments, you may have very few stores in your treatment and control group. In that case, standard packages can make errors and they don't give you accurate standard errors. There are some small sample corrections that you might have to do, and this is a reference that you can look at for small sample bootstraps. Okay. The basic thing is that observations within a market can be correlated, and the shocks then eventually don't vary independently by treatment because your treatment is at the market level. Okay. Then coming to the last point of my discussion, once the experiment is run, you have baseline characteristics for individuals. it's useful to look at where the effects are higher and where the effects are lower. Okay, so what you can do that is, if you have X's for individuals, you can interact the treatment dummy with the X's and be able to say, when the effects are large and when the effects are low. For marketing, that's because targeting is usually at the back of minds for all the marketers. So this is a useful exercise to do. But the concern that comes up here is that if you put in 100 interactions, 5 of them are going to turn up to be significant just by chance, and therefore there are certain things we need to keep in mind. And I think that's a good segue to Stefan's talk, and he's going to talk a lot about heterogeneous treatment effects. So I'll leave that to him. Yes, question. So heterogeneity is in the treatment effect. So even if I randomize people into 2 different groups, within the treatment group, there are people of different types. And these different types of people may respond to my marketing stimulus in a different way. Okay? So, and that heterogeneity, those differences in effectiveness are obviously useful for the marketer and for the business to evaluate their future strategies. And that's what I mean by heterogeneity in effects. If you have a lot of baseline characteristics, you can uncover some of that systematic heterogeneity that varies with observable characteristics.
So, for example, in your first experiment, people were in different stages of doing this funnel. For example, when you are shown these retargeting ads.
Yeah.
So that is a form of heterogeneity.
That is a form of heterogeneity.
So in that case, how do you treat that form of heterogeneity? How did you deal with that?
So in that specific example, we treated them as very different experiments. We said, okay, people who exit the website after viewing the product, they are a different subsample. People who exit the website after creating a cart, they are a different subsample. I'm going to do a different analysis for this one and a different analysis with that one. That was our prior. Even within these samples, we explored more heterogeneity, but that was not related to the stage people are in. Okay, so it depends on what X's are available to you and how they relate to the priors that you have going into the experiment. Okay, so quickly to summarize, the main point I wanted to make here is about the designing of experiments. So there is no clear prescription that I can leave you with except for the examples and certain tips within these examples. It's good to have, in the end, after the experiment is done, we want to be able to say something about the future, about some other settings. So therefore, it's good if we can say something about an underlying mechanism or an underlying theory, okay? For obvious reasons. Now, if I go too much deep into the theory may have very precise predictions that I might not be able to test in the field. So in the field of marketing, because we are doing experiments in collaboration with businesses, we got to strike a balance there in the prescription and the learning goal that we have in our experiments. And in the retargeting area, I talked about the steps that we took in my experience, the overall problem area, refining to the question after thinking through what the possible mechanisms would be and what might be useful for the business and for us in academia, and different conditions had different implications directly, and therefore the collaborating advertiser got satisfied immediately after the experiment was run, so it was quick for them. Okay. Now then, other aspects of design, the outcome measure. It's very good to have multiple outcome measures. If it's possible to match a survey with revealed outcome measures, that's good, because then that can help me learn much more deep about theories. Unit of randomization plays a big role in how you estimate standard errors later on. It's better if you can do randomization at the individual level. Power calculations, I didn't spend a lot of time on that, but you gotta do it. Otherwise, it can be a very risky thing. Okay, and then once the analysis comes in, mean comparison is the main way to report results. That's what the experimental data lends us to. Start with randomization checks. Regression is good, but again, be careful how to estimate the standard errors. You got to correct for heteroscedasticity and also cluster at the level of randomization. And then exploring heterogeneity can be very useful, as Stefan will talk about in a minute. Thank you. Yeah, I can send them over. Yeah. I think all this is recorded.
Sorry?
All this is recorded anyway, so you'll have access to it.
I see. So you've read it.
Yeah.
It looks like a couple of hours.
Otherwise, feel free to email me. I'll be happy to send you.
So just click it's more convenient too. Right. This guy should also be pretty self-explanatory. All right. That's a laser. Cool.
Shall I just start? All right. Thanks a lot. Thanks a lot, Kinshuk, for the introduction, and Navdeep for that very nice first talk. I'm happy to be here. Before I get started, I just wanted to apologize. Right after I finish my talk, I'm going to have to run out the door. I have a plane to catch. I would much rather be listening to Evas and Eric's talk than being sitting on a plane. But that's how it went, so I just wanted to apologize preemptively. Anyways, so this is about estimating heterogeneous treatment effects, and okay, why should we care about treatment effect heterogeneity? I think, say, if you ran a randomized trial, you kind of always have in the back of your mind that some people react to it differently than others. So here's one example. If you want to say flesh it out, kind of imagine what it could be like. Let's say you're T-Mobile and you have this new product you're excited to offer. You pay $1 a month, you can tweet as much as you want for free. I don't know, something like that. And to get people motivated, you're offering 3 months for free if you sign up for this new product now, and you run a randomized trial to see if this coupon is helping people. And I think it's entirely plausible in that kind of experiment that you'd have some people who just don't tweet. So they're just not going to buy your product. Whatever you do, there's some people who tweet all the time, and they calculated themselves that it's worth it for them, and they were going to buy it anyways. And in between, there are some people who maybe weren't going to buy the product, but now that you gave them the offer, they always wanted to start tweeting, and who knows, and maybe this is the opportunity to get started. And anyways, if you have this kind of setting, it's kind of obvious that having a table of this form is super useful. Because here, okay, the numbers, the treatment effect here is probably too big here, but still, having this table is much more useful than if you just had the average number of people who subscribe to your product without the coupon versus with the coupon. If you just looked at it marginally, that's like the sums across the rows, it maybe looks like the coupon helped maybe increase the number of people who bought the thing by 10%, something like that. Which is already a big number. But if you look at this table, you see it's really having a humongous effect in this bargain hunter group and no effect otherwise. So conceptually, if you could have this, of course, you'd want it. And what's the difficulty? It's that here we had these column headings that correspond to things that we don't know what these categories are. We may have some theoretical inkling of what types of categories there should be. We probably have much less idea of which specific customer falls into any different one of these categories. So what should we do? And okay, if we don't know these categories, we kind of have to fall back on what we do know. And again, thanks, Navdeep, for setting this up so nicely. We did not coordinate. The one thing you could do, and people often do, and is sometimes a reasonable first thing to do, is a logistic regression. So let's say what we really would have wanted is these different types of customers and see how the treatment affected them differently. Okay, we don't have that. What we do have is for every customer, we measure their age, we measure their income, and we might want to say, like, did age or income have an effect on who responded to the treatment or not. And why would you want to say that? Well, maybe you think people who fall into like the bargain hunters are in some quadrant of the age-income distribution, something like that. I mean, this is kind of a, if you run an R, if you run a logistic regression, this is what the output would look like. You have a treatment, you care about age and income, you put in treatment and age interactions, you get some coefficients for them, and then you claim that these coefficients kind of tell you something interesting. So here it looks like age does not have a star, so maybe age doesn't affect the treatment effect, and income does have 2 stars. It's like good income. I mean, the question is, does this mean, can we conclude that age is not associated with the treatment effect and income is associated with the treatment effect? This is with 10,000 samples, by the way, so not too small a sample size. And I guess the answer is, if you specify the correct model and everything is wonderful, then yes. Here, of course, this is not true. The treatment effect depends purely on age. So only treatment and age do have an interaction in the population. Income is independent from treatment conditional on age. So here's the shape of the true treatment effect function as a function of age. Of course, what caused the problem? Well, age and income were correlated. The model was misspecified. They interacted in a way that made logistic regression tell you something different. So this is not to say that this kind of interactive model could never work. It's just that it's, can we get something that's maybe more flexible, more transparent? Let's just see heterogeneous. Like what we want to see is, in the Oracle example, we divided people into 3 different types of people, and then we looked at the treatment effect in each group, and it was completely transparent. And then we went from that to this kind of table where we have a bunch of numbers, and it's much less clear, if you allow for the models would be misspecified, what these numbers mean. So can we go to a feasible kind of heterogeneity model that can give us insights? So that's the main objective of this talk. I'm going to talk about random forests in particular. Okay, but we're going to get there at some point. So now just to be formal about what we're talking about, so I'm doing everything in the potential outcomes framework, which is exactly the same thing Navdeep was doing earlier. So for every single person, when they come in, you have a feature vector x. That's who you are. So this could be your age or your income. Your response y, did you buy the product or not? And then the treatment assignment, that was assigned. And kind of the standard mental exercise, mental gymnastics thing you need to do in the potential outcome framework is that you only had one response y, but we're going to pretend that there are 2 responses y. There's one universe where you got treated. Something happens to you there. There's another fate where you didn't get treated. These 2 fates sort of coexist. And then when the experimenter flips the coin and sends you, then the experimenter sends you into one of those 2 fates, and that's the one we observe. But both of these somehow exist in the background. This may be a heavy assumption conceptually. The advantage is that mathematically, it gives you a definition of the treatment effect that's completely model-free. So now the treatment effect at x, so for people with x equals little x, the average treatment effect of those people is just the expectation of their counterfactual treated outcome minus their counterfactual untreated outcome. So our goal will be to estimate this quantity across x. And of course, here the difficulty is that the treatment effect is determined in terms of difference of 2 quantities, and we only ever observe one of them. And just this kind of thing in general is identified given data if conditional on x, the treatment assignment is as good as random. So if you have a randomized trial, then just this thing, the potential outcomes are independent of the treatment assignment because the treatment assignment was completely random. It's actually enough just to condition on x. You can still get identification, but we don't need to worry about that. And OK, given this kind of boilerplate, these assumptions we're willing to make, and let's say continuity assumptions, what's maybe the simplest way of thinking about treatment effects? And remember, before we had these oracle buckets, people who didn't care about your product, people who were going to buy it anyways, people who were kind of in between, and we wanted to estimate treatment effects in these oracle buckets separately. Here we don't know what the relevant types of people are, but it was willing to assume that we have these covariates x, and people who are close to each other in x space are pretty similar, then it's natural just to say, let's draw a bunch of little circles in x space, and inside of every one of these little circles, let's estimate the treatment effect separately. So here, if person little x is a new customer, we want to estimate what would be the treatment effect for them. Just draw a circle around them, a Euclidean ball in x space, take the k closest people who got treated, take their average, the k closest people who didn't get treated, take their average, and that's a treatment effect estimate. And the advantage of this, it's super transparent, it's kind of clear what its intellectual, conceptual justification is. The downside is it doesn't work. The problem is, imagine you have 20 x's, so this kind of not even high-dimensional data, just medium-dimensional data. If you try to draw a Euclidean ball around someone in 20 dimensions, you're going to have to make it really big until there's anyone inside of there. So this kind of thing, if you have a gazillion observations, it might work, but in finite samples, it's not so good. So I guess one solution to this is if we had this idea that we had this analysis with oracle buckets. We have 3 buckets. That's great. K-nearest neighbors analysis, it's feasible. It doesn't require knowing a priori what the buckets are, but the problem is if we're in 20 dimensions, we need to draw too many balls and estimate treatment effects in each of them, so that's not practical either. So what's something we can try to do in between? And essentially, we can try to do something that's like K-nearest neighbor estimation, except we replace the Euclidean ball with a kind of smart bucket of people who are like you that we learn adaptively from looking at the data, and then we compare you to those people. And the hope is that this kind of comparison group we get for you is somehow, these are the people who behave like you, estimate a treatment effect for these people, and you'll also get a good treatment effect for you. So now, in principle, there would be many ways of getting this kind of adaptive nearest neighbor method. In this talk, I'm going to focus on trees in particular, just because it's one methodology that you can use for this. And in trees, the way we produce these neighborhoods comparison groups for you is we start with X space, we cut it in half, or we cut it along some axis, and then we throw away this stuff, then we only look at this stuff, and then we cut it in half again, or in some fraction. And we keep doing so until we have a rectangle around the point, and that's your comparison group. That's a set of people like you for who we're going to estimate a treatment effect and assign it to you. Okay. And the way we're going to do this in practice is one approach to doing this is just greedily try to build groups that capture as much heterogeneity as possible. So if we step back, maybe this slide is most helpful. If we step back, remember we kind of had this idea in the back of our minds that we wanted to estimate treatment effects. We have a bunch of different people, and we wanted to find subgroups that capture people in this subgroup they respond to the treatment in one way, people in this subgroup respond to another way. And we want to discover these groups on the fly. And the algorithm we're using here is kind of a very optimistic, greedy version of this thought. We're going to start by first dividing all our people into 2 along some axis-aligned split. And how do we pick the split? We'll just pick the split in a way that the estimated treatment effect is as different as possible on this side versus that side, in a way that's weighted by the number of people here and there. And the idea is then, if you found a split where on one side of this, you divide your data in 2, and on one side of the split, the treatment effects are different from the other side, you kind of discovered some heterogeneity. And then you did this once, that's a good start, and then after we did this once, we're left with this data, and then we're going to do it again. We're going to split maybe here, and the next time we're going to split here. So from an optimization perspective, we're not trying to do anything too smart. Maybe the surprising thing is that this kind of greedy, if you want to find subgroups, just start by dividing your data in 2 and recurse, is actually not so bad. And then, so that's one thing you could do. And then finally, to get something that actually works in practice, there was you can do this many times. This is a general principle about if you want to run statistical procedures with any kind of instability. If there was any randomness in your algorithm, just run your algorithm many times, average the predictions made by the different runs of your algorithm, and they're going to be better than any of the runs alone. And so then this is the kind of thing that actually works in practice. We had these kinds of little trees where you always get a comparison group, a set of people like you. We estimate treatment effects in there, and then our final treatment effect estimate is just the average of the predictions made by all of these trees. And the way you actually build these different trees is by adding noise to the sampling. So anyways, okay, kind of back to our original goal, right? Our original goal was to understand treatment effect heterogeneity. Maybe you feel like this is all very complicated. There were a lot of bells and whistles. Why would you want to go to all this trouble? The idea is maybe even though this algorithm seems more complicated, the analysis in the end kind of avoids these tables of numbers you get out of logistic regression, and you can just kind of see the treatment effect in a fairly transparent way without having to assume parametric forms or anything like that. So here's a simple simulation example. The kind of thing you might encounter in practice is that, let's say here I assumed a 6-dimensional problem with 20,000 observations. So it's a pretty straightforward problem, but with a nonlinear true treatment effect. So you have a positive effect if you're in this corner, but all in this area, you don't have a treatment effect. So the first two features matter. Features 3 through 6 are garbage. So because the treatment effect is nonlinear, logistic regression could get you in trouble here unless you're very careful. But what about? Well, again, you could do k-nearest neighbors here. And it turns out 6 dimensions with 20,000 observations, that's so much data that even k-nearest neighbors works. So here, if you take every little point, you draw a little ball around them, estimate treatment effects in that ball. That also lets you estimate treatment heterogeneity quite well. Or you could use the forest, like I told you, that adaptively tries to find the shape of this area where you have a positive treatment effect, and it also works, yeah?
So this is like getting you like a piecewise constant approximation to your treatment effect, something like that?
It's a great question. So remember, the thing we're actually doing is we're going to average. So each tree finds these rectangles, and over the rectangle is going to just compute the treatment effect, and everyone in this region is going to have the same treatment effect estimates. So these are going to be piecewise constant. But then we're going to run this algorithm many times, adding some noise to kind of get rid of instabilities from where you chose to split exactly. And the end result is when you average many different piecewise constant functions, then it doesn't act like a piecewise constant function anymore.
So how do you, at the end, interpret the, maybe you're getting there.
That's also a great question. I'm going to show some visualizations. So how about we save this to the end? I'll have some plots. If you don't like the plots, then we can talk about it more. I should get to the plots soon. So anyways, the point was in 6 dimensions, kind of k-nearest neighbors does this kind of non-parametric thing well. What if you go up to 20 dimensions? Now k-nearest neighbors breaks down as promised because drawing Euclidean balls in 20 dimensions doesn't work. But the forest-based thing still kind of gets the right answer. So the claim is if you have these, if you want to flexibly estimate heterogeneous treatment effects in a way that doesn't rely too much on functional forms, you can, forest kind of can be used for that. And here in terms of mean squared error for the estimated treatment effect, you do a lot better too. So I don't have time to go in details at all about how we run these kinds of things. There's one thing I wanted to stress though, that's kind of, you might worry about when we're looking for heterogeneity. There's always a big concern about how do we control for overfitting? How do we make sure that we don't look for a group because in that group it looks like we have a huge treatment effect and then we're too optimistic. And it turns out that forest-based methods have a great kind of fix to that problem that you can hide into the algorithm at very little cost. And the point is, usually when we build forests, the way we're going to build a lot of trees, and we're actually going to build the trees on subsamples of the data. So if you have 10,000 observations, first draw 4,000 observations, build a tree on those 4,000 observations, and then draw different 4,000 observations each time. And this is already something that's advocated in practice as a way to stabilize the algorithm. And it turns out if you're already subsampling, instead of drawing one subsample, draw 2 subsamples. Draw 4,000 observations, pick your tree structure using them, pick the rectangles, pick the sets of people like you using the first 4,000, and then take another set of 4,000 observations and estimate, and use those to actually estimate treatment effects in the leaves. So you use different data to pick your comparison group and to estimate treatment effects, so you avoid the overfitting problem. And the nice thing that didn't really cost you anything, because you were subsampling anyways. And so then next time, maybe if this time these 4,000 were used for growing the tree and these 4,000 for estimating treatment effects, next time they swap roles, everyone gets to participate in learning the structure of the forest. Everyone gets to participating in estimating treatment effects. And it kind of solves the overfitting problem, at least point-wise, in a nice way. So since I don't have very much time, I wanted to finish with an example that maybe gives some opportunity to talk about how you could interpret estimates coming out of these kinds of things. So this is, as someone who grew up in Europe, you come to the US, you realize people have very strong feelings about the word welfare. Someone had the great idea of running a randomized experiment where they asked people, are we spending too much money on welfare, or are we spending too much money on assistance to the poor? And I'm sure I'll surprise no one by saying that people answer these two questions completely differently. People are way more likely to say we spend too much money on welfare than on assistance to the poor. So it's a randomized trial. You can get an average treatment effect, and that's already nice. But I guess if we want to go further, talk about treatment heterogeneity, are there some people who answer these questions more similarly, some people who answer them more differently? That could be interesting. And here, you might really say question B is the control. This is like, are we spending too much money on assistance to the poor? That's the baseline, how you feel about the issue. The treatment is asking, are we spending too much on welfare versus assistance to the poor? The treatment effect is the difference in your answer to these two questions. And so you can run a forest on this, and I guess the first thing you see is you can kind of visualize the results. So here I ran an analysis with 12 covariates. You'll have to excuse me, I ran this a while ago. I don't remember what some of the others were. But here you have a plot where we see as a function of income and as a function of political views, liberal versus conservative, how you answer the questions. All the other covariates, I think, let's say, age or something like that, and here are set to their median values. So this shows a slice of the predictions where everything else is set to median, and we vary income and political views. And you kind of see what you might have expected is that if you're less wealthy and more left-wing, then people often, there's a smaller difference in how people answer questions about assistance to the poor versus welfare versus wealthy conservatives. There's an actual humongous difference in how much you answer these points. You see here there's a 0.4. So that's like 40% more people say we spend too much money on welfare versus assistance to the poor in this quadrant. And so maybe the nice thing about the kind of analysis we had here is that we end with a picture that kind of shows what the shape of the treatment effect is instead of just like numbers that may be misleading. Another way to look at this is, of course, you may want notion of statistical significance. So then here I'm plotting, so before I plotted a slice where you vary both income and political views and set everything else to their median. So here I'm plotting one-dimensional slices. So here we vary political views and set everything else, including income, to the median value. And there you see how the treatment effect varies. You see, okay, apparently how much is to the left or the right doesn't matter that much. The jump is more in the middle, at least if you believe in the shape of the curve. And I haven't discussed it here, but it's possible to get confidence intervals for these kinds of curves too. These are pointwise confidence intervals. Kind of give you an idea of how much uncertainty there is in the problem. And here you have a similar plot for income. So again, now to come back to your question, how do you interpret these things? I guess a blessing and a curse of these kinds of non-parametric methods is that there are no parameters. So you can't talk about, it's hard to put a number on a parameter saying like, what is the coefficient of political views? I don't know. Like this doesn't reduce to a number. But on the other hand, what would you want the coefficient of political view to be anyways? If we say that if we actually believed that the effective political views on how you answer this question is this kind of sigmoidy thing, then that's just the shape of the thing. You might want to talk about the slope of the best line, but I guess that's something that's up for discussion. So you may say random force one to, instead of just having this ready-made numbers that kind of tell you how to report heterogeneity, they kind of encourage you to plot predictions for different subgroups, set some things to the median, set some things high, see how the treatment effects vary when you vary other things. You could plot curves through your data, things like this. And then they let you kind of look at how the treatment effect estimates change when you do that. So anyways, that's what I had for you today. Thanks a lot. And here's also software if you want to run this.
Okay, we have a 15-minute break now. After that, we'll come back for more topics.
Thanks. Enjoy your
How
talk.
did you,
Thanks a lot.
how do
You need to run.
standardize?
Yeah.
Hey, if you want to run, I can follow up later.
Very quickly, a different question than what parameter would you estimate is, can you answer the question, is the relationship between, is the heterogeneity additive in income and political views or not? And based on even the picture, the two-dimensional, the color-shaded picture, one couldn't tell. I mean, it looked like it was going this way, correct?
Yeah. That's a great question. I guess you could, so you have these confidence intervals. So I guess there are many ways you could try to answer this. You could have these confidence intervals that kind of fit the best additive surface and see does it poke out of the confidence intervals. What someone else has suggested is you could fit different forests that only on one feature or only on the other feature and see does the forest that gets used both of them improve on the fit substantially? If the x's were independent, you could go through something like that. I think it's something you should be able to do, but I don't have the methodology to do it right now.
Thank you.
Thanks.
I have a question.
Then I'll talk to you later.
Hey, sorry, you.
I was just wondering which reference would you give to estimate standard errors on these things?
So in the software package, we have standard errors. Both of these, so these two papers are the ones that.
These two papers talk about how the software works, because I want to know the nitty-gritties behind it as well.
So the motivation behind the standard errors is in the first paper.
Okay.
The second paper, I guess if you want to heterogeneous.
Start with there and then I'll figure out. Okay.
Exactly.
Sounds good.
And I have an earlier paper with Brad Efron and Trevor Hasty that kind of heuristically justifies the standard errors, but doesn't have theory.
Yeah,
so.
theory is fine. Okay.
No, so the first one is the, yeah. Okay.
It's more about what I would like to see when I look into this presentation. Like you started from example when we run some kind of regression and abruptly get a significant coefficient. So do you have any Monte Carlo simulations results to show us that, for example, if you are using the old fashioned regression with covariates, you will have in 5% chance that you will get abruptly significant coefficient. But for your results, if you're doing such kind of mixing, you will have more robust, less such kind of wrong conclusions.
That's a great question. So here the standard errors I was showing you,
Okay.
they're valid at a point. So they have the same property as the standard errors you get out of linear regression, is that for every number you give a standard error, and it's valid for that number marginally, not jointly. Building joint confidence intervals with forest would be cool. We don't have it yet.
Oh,
Yeah.
oh you mean that this shape, kind of sigmoid shape, you can still...
So this error bar,
Oh,
it's
yeah.
for this point.
I see.
It's not, these error bars aren't for the whole curve.
Oh, I see. So kind of with some probability could be straight line or constant
Yeah.
with
So I think a better way
very
to.
time.
So maybe if you want to test for heterogeneity, you could compare this point to this point, or something like that.
Oh, yeah.
And here it looks like the error bars don't overlap. So
Now, do you have any kind of packages already you can use it? Oh, okay.
yes, this one.
Sorry.
It's still under development. If you find any bugs in it, please let us know.
Okay.
Yeah, actively working on it.
Okay.
Yeah, I have a really quick question. So I have more computer science training than statistics training, and for me it would be natural to do like you make the best prediction model for y1, then you have the best prediction model for y0, right, as a function of x, and then you just subtract them. Why did you decide to focus? Like, what I really don't like in your approach compared to my approach is that you have to have this artificial criteria, like maximizing variance or minimizing variance. Like, you see this? It's like.
So this paper, we try to dig a lot deeper into that question.
But look,
if you
intuitive answer, like.
Okay,
what is the
so
key difference?
just an intuitive answer. Here's what I'm worried about. If you're here, and I have the tree that does treatment effects that compares you to these people, and I have the tree that for the control condition that compares you to these people. Like, it's possible you're being compared to completely different people. And in a regime where you have big main effects but very small treatment effects. Yeah, so okay, maybe this is the kind of thing. Let's say the shape of the curve for people who get treated is like this, and for people who get controlled is like this. The point is that these two lines are very similar. The difference between them is maybe something like this.
Small.
Yeah. So then if you fit both of them separately, like you might pick your regularization in a way that makes sense when you're trying to fit the whole thing, but the effect of the regularization may be more than you bargained for.
But what about your approach? Is it the same?
So this approach you have is.
It's like you say that in my approach, because of regularization, I can just get rid of the effect, and your approach sort of sustains the effect and it's low, but it demonstrates at least some is better.
Inside a rectangle, you still randomize trial inside that rectangle.
Yeah. But the same is true, right? I mean, so for my approach, you can use the same random forest and it be the same.
If you actually ask me what I want to do, which is not quite clear. Here's what I actually suggest. First in forest of y on x, without looking at the treatment. Okay, so plain version first. Then in a forest, treatment assignment on x, without looking at it. So now take residuals. You have y minus w hat, y minus y hat.
Yeah, you say partial knowledge. Yeah, I know. Yeah, okay.
And so then we have these two things. And then you can run essentially another tree forest that uses these residuals. And so then the idea is this kind of provides the first bit of
Just want to check with you if people pay, can we get
We can email them a receipt.
Oh, I see.
Yeah, you can just let them email them a receipt.
Thank you.
But this will give you like an average.
Okay, and so where do you want me to drag it to?
Inside this.
so we're going to use this
So now next is Eva, then I'll take a minute to introduce you, and then
Okay. All right, so there it is. Yep, you're all good. So we can remove that. We're all set.
you want me to do it the right way?
Nah, I don't care.
Yeah, I see that. Yeah. So then you can track what's normalized to MSTV.
All right.
Thank you.
So if you,
Okay. And what is Victor?
I've run into it many times. Do you work with that?
Well, no, but I mean, I'm at MIT and they're both Russian, so we talk a lot. He's doing very similar stuff what you just described.
The big work is very So this specific orthogonalization was kind of motivated by the fixed perspective.
All right, thank you.
So I'm curious if this method is overkill for which I'm interested in estimating the heterogeneity for it, but I don't want to assume functional form necessarily of the heterogeneity. Like, is this a tool for that? I mean, are you aware of other macro you come with a micro you how you going to get because big care on long-term equilibrium analysis, right? It's not optimal solution, this type of things. This temporal substitution effect, right? Locating kind of nice the heat map goes to change over time. I was doing some kind of like a dynamic programming. I'm not sure what else is so it's like a backward induction. What they get is optimization, not just heterogeneity effects, static, they do dynamic, so they have treated the same person one time, two times, maybe micro randomization, right? And then you optimize depends on the heterogeneity, the feature variable. Yeah, so I have some examples applications targeting, retargeting, etc. Because the idea is I have been learning customers, like the customer go through like two stages, series of window shopper line, and then the second stage retarget this line with over time. So I know the heterogeneity, and then I tailor my second treatment because the first time we brought it into the purchase, right, I don't bother you too much. And then I optimize based on your prior history, the feature variables, and the response in the first stage of my treatment. So it's all dependent on my previous responses. And then I optimize, personalize each DO2 features. And then that the key learning or the computer science languages that we call key learning, right? So this is of this analysis cover I think the clinical trial because precision medicine. Yeah. So those are the stuff I think probably there's some really exciting stuff. That's directly marketing more kind of like relevancy. So maybe later I can send you the stuff and maybe work with the Python and the society. I'd be very good. Now I know what it looks like. You need one. So I need to. So if you.
No, that one. No, I just want to name it.
Hello. Great.
So right after you're done, I'll just take a minute to introduce.
Yes, that's very good.
That's fine. We don't. I mean.
Eisenhower.
I don't want to. It's on, so I don't want to put it yet.
You just start. No, that's a projector, right? So this.
Oh, okay, that's it, project.
Yeah.
I saw this. Yeah, exactly.
I think it's on, right? Because the screen. Can everybody hear me? You guys would say yes? All right, so hello everybody. I want to have a very quick thanks to Kinshuk for putting this day together, and to Stefan, who's led, and Navdeep as well for great tutorials so far. So I am Ascarza. I am a faculty here at Columbia, and the purpose of this 30 minutes is to show you an application. More like they have been talking about field experiments, I have been talking about heterogeneity. I'm going to tell you about a paper that a colleague of me that was here a minute ago, Oded Netzer, Peter Eves, also there, he's hiding in the corner. So Peter is a collaborator and friend from us in HEC Paris, and Matt Danielson, who's a person who's working for the company who actually ran the experiment for us and give the data and all that. So this is a project. I'm going to start with the idea of what we wanted to do with the project, the research challenges that we faced and how we solved them, and I will jump to the results to keep it on the application way. So here's the original idea of this. We have been working on what generally is called CRM marketing, which is customer relationship management. The whole idea of this is one of the main ideas of CRM is that we need, as a marketers, we need to recognize that different customers are different. And if I'm going to just, for example, run a marketing campaign, or I'm going to do something to a customer, I should recognize that I should expect different value, different money back from each customer. So the whole idea of CRM is like, look, the better you identify this heterogeneity, the more you will know that you should, for example, I'm going to target, say, a campaign, and this is going to be the return per customer. Well, I should go to this guy for sure, right? Because this is the person I'm going to make the best. So this is the whole idea, one of the main ideas of CRM. And we have done a lot of work on that, and we have learned a lot in marketing. But also we recognize that in many, many settings, and actually in an increasing number of businesses nowadays, what happens is that these customers are actually connected to each other. And I not necessarily mean Facebook connected. It could be connected in many other ways. It could be that in your service, you use Dropbox. You are connected to the people that you share files with. You use gaming, for example, you are connected to the people you play against in many, many other contexts. Or you could actually think about going to the gym. Just the fact that I go to the gym to the same class that Ryan does, there's a connection there that might affect our demand, right? So what we wanted to see was whether these targeted campaigns, or CRM campaigns that are targeted to this person, might actually have an effect on the people connected to that, which is kind of great, because at the end of the day, if I'm just spending money of sending something to a customer, if that effect is positive to the people around Navdeep, for example, this is great news, because actually I'm getting more for my money. If the effect is negative, then I have to really think again whether I want to target Navdeep or not. Right? So we're thinking that was exactly the question we were trying to answer. So just to formalize it, the real research question was, does the effect of targeted CRM campaigns to a particular individual have an effect on the people connected to them, or have a spillover of those effects? We wanted to think about, OK, which behaviors, depending on the context, obviously, will be affected. What could be the mechanism that goes behind it? Why is that if this effect is there, why is that we are finding that? back to Navdeep's point this morning, that will help us go into other contexts, go into other campaigns, right? Of course, also the company and us, in a way, we wanted to know how much money actually we're leaving on the table if something. And the whole idea that I wanted to start the talk with was like, OK, how can we actually measure such an effect, right? So let me start with the first research challenge that we faced, or that I guess almost anybody trying to answer this question would face. Trying to find contagion behavior in your networks is tough. And here I put a few references of actual papers that I really like, that I think they make the point, and they might be mainly general the talk and the topic. So there are mainly 3 reasons why identifying actual contagion is tough. One is that when people are connected to each other, it might be because we like similar things. So Ryan and I, you know, we both are connected maybe because we have common interests. For example, nerdiness in marketing, right? So if you have I don't know, any action about that is good for nerds in marketing, we might both do something about it, adopt that book, buy a book, but it's just because we both were going to like it anyhow. It's not that I affected Ryan in any way. The other one is, it depends how you, the paper you read could be called correlated unobservables, confounding effects. The whole idea that if I'm connected to Ryan, and now happens that we both live in the same neighborhood, it could also happen that marketing actions from other companies or any other shocks in the environment affect us equally. So just from observing our behavior, you're going to be able to pin down the actual causal effect. And also the other one that is called simultaneity or reflection, the whole idea that, OK, wait a second, you see us doing something. Is it that Eva affected Ryan or the way around? So to overcome these issues about identifying contagion effects, the first thing we thought was, we're going to run an experiment, right? Because we can actually manipulate the demand of one of us and see what happens to the demand to the connected people. And this is what we did. We were in contact with this company. We're the 4th after works. And what this company does is they actually manage so many marketing campaigns to telco companies. So the focal company that we're going to use the data in this study is a telecommunications company from Australia. And they have plenty of customers, about 4 million. This is the second largest telecommunication operator in that market. And then we run into issues of field experiment with a collaborating company. Well, they have to agree on doing the things we want them to do. So they were willing to play around with certain types of customers. So they selected customers who were enrolled in a particular cell phone plan. This is a prepaid plan. This is not that common here in the US, but the whole idea is that I put money on the cell phone, I put credit that lasts for a month, pretty much, and I can use that credit to call, to text, etc. In this particular plan, the consumption within the network was for free. So if I call Navdeep, and Navdeep is in my network, it's free. If somebody, for example, Ryan is on my network, and I call Ryan, I pay, he doesn't. So in this market, people pay for making calls, not to receive calls. Just a little bit of the context. Now, the whole idea was that they wanted to incentivize some people to stay in the network and to use more the network. And what we wanted to know is, OK, now what happens to the people connected to them, right? So that's why instead of only focusing on the people who actually are going to be, well, let me tell you briefly how the experimentation worked. It was very, very simple. The company just said, look, we're going to run a marketing campaign. There's going to be a control group and a treatment group, A/B testing type of thing. And the people who are going to be treated, how they are treated, you're going to get a text saying, hey, Navdeep, if you just reply to this email, we're going to give you some free credit, like that. It's really giving away money. I mean, you give minutes. That is definitely cheaper than giving money for the company. And then you have to respond within a week, and then you can use that free money only for a week, right? It's not forever. And what we do is we collected data on the 4 weeks before the experiment was run, and then 12 weeks after, because we wanted to check like short-term effects, long-term effects, et cetera. Now it comes with actually the question was about their friends. So how do we define the network we're going to be looking at? Well, so among the people who were treated or not treated, so these treatment control people, well, let's call them egos. So what we looked at is with the data from the 4 weeks before the experiment, we looked at all the connections that these people had. What is a connection for us in this case? We defined connection as anybody who has contacted you or the way around at least twice. The idea was to avoid a call to the Uber driver, which is just, but this is also a measure that the company is using right now. The 2+ connections, text, call, I don't care how is the method of communication, I know you communicated with them. The types were undirected, we just didn't care who calls what. We called you connection if any conversation or text happened. And then just for the names of that, the people who were part of the study were the egos, which is the center of this ego network, full of alters, which is the connections to them. So the egos got a treatment or not. The alters didn't get anything. This is the whole thing. Now, if we run the experiment here, and we try to understand what happened, what is the treatment effect, now, the second research challenge we face is what Navdeep already discussed earlier today, is the Toubia assumption. What, in this case, so this is, by the way, Toubia, it's something that we assume to actually, when we make inferences, and we claim that this is the treatment effect, we're making that assumption. Now, the question is how valid is this assumption. In this case, it's very easily violated if there is some interference in the network. What do I mean by that? So, for example, let's say this is the person I was going to target in the beginning. This is the ego network. This person is not in this ego network. This is all these guys. So for me, this is the ego. These are the alters. Now, what if just by chance one of the alters was part of the experiment? Then that person might have been treated, and then I cannot actually compare these guys. I'm going to assign this guy as a person connected to this guy, but then it might get some of the effect from other guys, right? It could be at that level. It could also be at this level. Maybe my alters were not touched by this experiment, but a person connected to them was. And then again, this is just one way of violating the assumption. What I put here for those interested, so there is a very nice chapter about network experiments by Sinan et al. In this handbook, and it's really talking about what happens in networks, which is very focused on that topic. This is, I think, one of the papers. I don't know if it's the one that you're referring to. So Susan Athey and Imens recently wrote a very nice chapter about field experiments, and it's about the econometrics of it, which touches on many of the points that I've already discussed, and they talk about the Toubia violations. And then, if you cannot control for this, there is many ways to actually fix it afterwards, which he mentioned as well. How did we do that? In our case, it was a simpler way to do that because the experiment was not very large. Let me explain what we did. So this is the two main reasons why we should be worried. What we did was we actually looked at the connections. We actually looked at the ego networks that were part of our experiment. Now, we are not going to allow this pattern to happen. We can do that. We are not going to allow alters to be treated or to be controlled. We also know the friends of the alters. So we are not allowed the friends of the alters to be part of the experiment. Now, why we were able to do that, and now here's the truth, is like this experiment was involving 1,000 egos. And the net was about 4 million customers, right? So this fix was OK for us because the experiment was a small size. If you want to run a large experiment, say in Facebook, this is not going to bite. You will have to find different ways to do it. This is just to put the whole caveats of what we did and why we did it. So what we do in the data, we ensure that none of the alters receive the treatment or control, and none of the alters actually have it. So what I have now is that we are more comfortable making the Toubia assumption because at least we know that there's not going to be contamination from 2 degrees, right? So this is what we ran it, what we looked at. Now, pretty much what is kind of this is what it's also called peer encouragement design in the literature. There's many papers about that. The whole idea is just visualizing a little bit. In the usual A/B testing, randomized trial, what you will have is a bunch of people who are treated, a bunch of people who are controlled. Then you want to estimate, for example, what is the impact of your treatment. Then you compare the behavior of these guys with the behavior of these guys. Our focus is not going to be that. Our focus is going to be, look, these people have connections. And we have made sure that there is no overlap in any of these ego networks, right? So now what we actually are focusing on and what we're going to use to answer our research question is we're going to compare the behavior of these people with the behavior of these people. This is just visually to see what we're going to do. So this is what I'm going to do in a couple of plots. I'm not going to go deep into analysis. I'm going to show you the results with more or less with visualizing what happened, actually just actual behavior. What data we're going to use to show you that? So we look at the ego activity. There's two types of activity for these people. Because these people are prepaid customers, they don't actually kind of churn in the sense that they call the service and they disconnect the cell phone. What they do is just let the money go and therefore get suspended. So we're going to call it suspension behavior. This is what the company does. And also we're going to look at how much consumption, how much minutes you call, how much texts you send, how much data you use, etc. Well, actually, I'm not going to show you data, but we had it. Now, altered activity, same thing. I'm going to look at the consumption. I'm going to look at suspension because there will be people prepaid. But also, there are people here who are in contracts, like most people in the US. So for these people, we're going to look at actual churn. Do you call the company and cancel your contract? Also, we have some, we're going to have some information about the degree of the people in the network, which is pretty much how many connections you have. Now, first of all, the randomization check. As Navdeep clearly told everybody we should check first. So what did we do here? This is when I'm using this logo here, or logo image, I mean the ego, right? So what we looked at is like, okay, on the ego, let me look at all the behavior, consumption, like how many calls you made, how many calls you received, text, etc., before the experiment, and let me make sure that treatment in red and control in blue are exactly balanced. And that was fine. Of course, it should happen also that your alters are equivalent, because if these people were picked at random, their friends should be balanced, but it's good to check. This is what we check exactly on the right here. Also, the number of calls made and received, and for the alters was also balanced between alters of control and alters of treatment. And also, we look at the suspension among alters. Yes, question? A structure like clustering or other metrics? Or? We did not, so we did on the how many number of alters in treatment control, yes, so the size of the ego network. And we had a few other metrics, I'm looking at it. So the metrics, we had measurement about the egos or the ego network. We matched them on and that's fine. They were fine in the sense they were balanced. We did not compute the ego network of each alter and then run those metrics. We didn't have those data. But the ones of the ego network, yes. But we had limited information on that. Yeah. So this is the randomization check, we checked. Now, let's look at behavior. So I'm going to first show you the behavior of the egos. These people that we actually gave free money, right? So first of all, let's see what happens to them. And then red is going to be treatment all the time, like control. So actually, if you think about suspension, yes, fewer people got suspended when they received free money. Makes sense. Now, what happens with their consumption? What I'm going to put here from now on is all the time outbound consumption, meaning I make the decision to call Navdeep. Why? Because this is the behavior A, I decide, and B, I pay for if he's out of network. So in the sense of out on minutes, this is the summary across all the treated egos, yet they consume more than the control. Which is interesting here is that I gave you free money, but the money only lasted for a couple of weeks. So this difference post 2 weeks, they're actually good for the company because they are not free money anymore, right? So this is about the egos, but the interesting goes for the alters. So what happens to the alters? And now red means that you are an alter of an ego that was treated or the way around. Indeed, the alters of treated customers consumed more minutes than the alters of control customers. This pattern consistent for text and for number of calls as well, all the behavior we had. Yes, Ryan?
Is it conditional on them not having left the program?
No, so the things we had to have these two together, because so one way would be, I'm going to condition on you not having suspended, for example. But then I will run into selection issues because more people in one condition, the people in the treatment condition is more likely to suspend. So here I cannot fully separate the behavior, which is suspension or churn, or what is consumption. It's a bundle.
So it's like, because those zeros are averaged in.
Totally. So this is coming from both behaviors. Yep. So the one other thing that we checked with that we could, without getting to any selection issues, was we thought, well, could it be that I got free money, I just start calling Navdeep more often, and then he has a missed call from me, so he has to call me back, pretty much. So this is just reciprocity, or I text you, you text me back, right, or not. So what we did was, let me make sure that this is coming from behavior that the alter does to other people. So the consumption, the data, the DB of interest now is going to be outbound minutes, but minutes that do not go back to the ego, just to make sure that there's no reciprocity in it. And indeed, we find that is the case. So this is for minutes. Now, what happened to suspension and churn? Now we want to, if this is good indeed for the alters, we want to find the red below. So slightly fewer alters suspended under this condition, and fewer alters churn when their friends were treated. Now, when we run the tests, which I'm not going to run into that, so all these differences here that I showed earlier were significant, depending on the test we run, or for the test we run econometrically. Here, looking at churn, we're looking at the proportion of alters that early on we didn't find that effect, but later on this one is significant at the alter level, at the ego level. So now, what else we did? Well, for now we showed two things. One is like, if I treat the egos, so first of all, there is an increase in consumption of the ego. I give them free money, and not now, but later. But also, if I treat the egos, what happens is that the alters now speak more, or increase usage, and decrease churn. But I'm not doing anything to the alters. I'm not giving you any free money. So the thing is actually, let's test the obvious, which is this change in behavior of the alters has to come from something different the ego did. So what we do here is like, if you want in a kind of more in the stats language, here we were estimating the intent to treat. If you think treatment as getting the increased consumption or getting the free money, here what we're going to test now is more the local treatment effect, which what we're going to look at is ego behavior right after treated or not actually affecting alter behavior. And to do that, what we did is, this is the post-treatment weeks. We split that on short-term and long-term weeks. And what we did is, well, I want to see whether when the ego talked more to the alter early on, this is actually when I observe stronger effects on the alter. So Navdeep was treated. He has multiple friends. And I want to see if actually the effect is stronger when he talks more to a particular friend. So this is, you are the alter that I'm looking at. If he talked more to you in the early weeks, I want to see whether actually that means that you were affected greater. So what is there is this linearity on the quantity of usage. The way we do that, we cannot just run OLS or Probit and sum like this behavior on this behavior, because we know that we're going to run into very endogenous regressors here, because this actually might be, they both may be actually correlated. But we did in this case, and that's why this really relates to the local treatment effects literature, is that if we use the treatment as an instrument, actually I can actually clean that possible endogeneity, and then I can give you a causal. So this is exactly what we did, both for, I'm going to run fast now, both from in terms of, do the alters speak more? Yes, they do, having instrumented this. Do the alters churn less? Yes, they do, when the ego talk more to them versus less, right? So this is more kind of them trying to identify the effect. They're trying to measure it. Now, but why this may be the case? Why are you really telling me that when Oded calls me more, then I'm going to call more my mom? So what could be driving that effect? And we could not test so many mechanisms because we're limited to how much we did. But there's one thing that we always went with our hypothesis early on was one of the things that might be driving that is actually the value that as an alter, the value that I get from the network is higher when there's more activity in it by my friends, right? So for example, think about Candy Crush. You're playing Candy Crush, and many of your friends play Candy Crush. You might derive more value from the network just because there's more activity among your friends. In our case, telco, what are you talking about? Well, here is one of the explanations that we think is more plausible here, and what we want to test now is like, the more you call me, the more I can keep calling. So for example, I'm going to start using WhatsApp because everybody in Spain does. Now, the more Oded texts me, I might text somebody else just that. Just this different, for example, in this case is, how's it? Substitution of methods of communication. In this case, for example, consumers are going to find more value of using that method of communication, either friends use more. So this is what we wanted to test by looking at heterogeneity in treatment effect. If indeed people who have stronger relationships exhibit a stronger effect, it's going to come partly from the network externality idea that I'm telling you, like, if my network is more active, then I might derive more value from it. So how do we look at that? Well, we were looking at, is there any observable that I can use to explain some heterogeneity in the treatment effect that is related to network value? We find two. What we looked at was, if I look at the strength of a type, so if Navdeep, I can look at how often he was talking to each of the alters before the experiment. All I want to use as a heterogeneity has to be before experiment, right? So if I look at Navdeep's different strength of different people, and I find that those alters that had a stronger relation with him are those who exhibit a stronger treatment effect, this might be in line with the account that we are trying to put forward. The other one we looked at is the alters' numbers of connection. If you have many, many, many friends, how much Navdeep start calling you is going to be less relevant because you talk to more people. This is kind of the two kind of semi-hypotheses we did. So the way we did it was a linear model on treatment, the x and the x times t. You have seen this equation earlier today. And just running quickly, the actual effect we find was like, yeah, tire strength positively moderates that effect. Number of connections negatively moderates that effect. That was just to add to the thing. Now, back to the manager, we also wanted to see how managerially relevant this is. And very quickly, what we did was, look, in this case, I'm going to give you average treatment effect in the groups. The egos, given what we give them, they increase consumption on average 35%, which translated to the alters increasing consumption by 10%, which is actually very, very large. Now, if the company now knows that if I'm going to target you, I know that with the same treatment in a similar population, I know that this is the effect I should expect from the egos. This is the effect I should expect from the alters. How different this is when you go to alters with weak relationships versus alters with strong relationships. Of course, you're going to get a higher spillover effect when you go after alters with strong relationships. In terms of dollars, what we looked at, I'm going to just be quickly with that. We computed, this is the ego we targeted, right? Now let's ignore the behavior from this person, and let's look at how much money the company made from those in the ego network. I can look at the behavior before and after and compute those differences. So combining, making some other assumptions in the very, very small footnote, and looking at their behavior, we quantified that for this firm, each of the alters ended up giving 0.85 extra dollars of revenue to the company in the 12 weeks after the experiment, which is actually very, very sizable. So just to conclude, we did find that, yes, indeed, the CRM campaigns propagate to the network. We find in this case, in this context, the increased usage, decreased churn. And the spillover we find is more or less 1, 2, 3. Like if you increase 25, like 25 the egos, 10 the alters. What I want you to give away, it's like many of you are not in marketing and many of you don't care about marketing problems. This is definitely not a marketing problem only. First of all, it's not about a context of telecommunications. There are so many cases in which what you do to a unit or a customer affects the other. And this is just some examples. We thought that companies that could be interested. For the marketing point of view, we think that in cases where you have network externalities, the return on investment in campaigns should be adapted in a way that you actually account for all the impact of that campaign. And something that we definitely are pursuing further now with all the same co-authors is like, okay, this raises a very interesting question of who are the customers that should be targeted. Because if I target Navdeep, I know I was targeting Navdeep based on what I expected him to do, but not necessarily what the people connected to him would do. And how companies should adapt those targeting rules, then it's still like to be answered, but this is kind of the first step towards that. With all that, I want to really thank you. And then you can. Okay. I don't know how I'm doing in time. Fine, right? Yeah.
We have a minute.
Yeah, we have a minute for a question.
In your estimations of those changes, you didn't know that particular eagle told the particular
Yeah.
Topics they called up experiment.
Totally. I do not, so I know how much you call to each alter. That I know.
But you didn't know the point of topic.
Excuse me?
The topic.
The topic, no, I don't know what they talked about.
It means if, let's say, at that time, Trump said some scandalous things and increased the things, it didn't count for it.
So,
dynamic of other things was not encountered, correct?
Yeah, so the thing is, if the fact that I called you...
Because actually something increased.
Yeah,
nobody else can hear it anyway.
I know, I
Right
put
now.
it on. Ah, that's good.
Okay, so first of all, thank you very much to Navdeep and Stefan and Eva for the wonderful tutorials and talks. So there's question being asked by a few of you. The slides for these talks will be put up on the website after this, and we're also videotaping the talks, so we'll put up the videos as well, so you can go back to these. So now let me get to the highlight of the day and welcome our keynote speaker, Professor Eric Bradlow. So Eric is a phenomenal individual to the extent that it's actually difficult to introduce him because you don't know where to start, and then you don't know, once you start, you don't know when to stop. So you can see his amazing list of achievements. Right now he's at the Wharton School at University of Pennsylvania. He's the KP Chow professor there in the marketing department. He directs the Wharton Customer Analytics Initiative. He's chairperson of the department, and he's also a professor of economics, education, and of statistics. His interests are very wide, but mainly focused on Bayesian modeling and statistical computing applied to a range of problems and data sets, et cetera, in marketing. The two things I've highlighted here is that since this is an ASA event, he is a fellow of the American Statistical Association. There are a lot of, one thing we did want to highlight when we were planning this with the ASA committee was to highlight the fact that there are lots of people who are very accomplished in marketing who are also fellows of the ASA, and Eric is indeed one of them. And he has also been a past chair of the section, the section on statistics in marketing that is organizing this event. He's also been a past editor-in-chief of Marketing Science, and on top of all of that, he's a great mentor. He has mentored over 50 PhD students, and he has won scores of teaching awards. So with that, let me welcome Eric, and the title of his talk is From Correlation to Causation, the Statistician's 20-Year Journey.
Well, thanks, Kinshuk. I have to admit, when you're first contacted about giving a keynote speech, the first thing you think to yourself is, damn, I'm old. That's the first thing you think to yourself. Then the second thing you think to yourself is, wonder what the topic of the conference is, do I have anything to say about it? Fortunately, this is a topic I've actually spent a fair amount thinking about over 20 years of my career. And also when you get to my age and you've written, I guess, a number of papers, you say, well, what do you know about it? I'm not going to come up here and just talk about general stuff because I just don't do that. So I do what I always do. I went to my resume, my CV, and I said, what papers have I actually written that I could actually talk about? And that's actually what I'm going to talk to you about today. I'm going to really talk to you about, it's hard for me to believe, I've been now at Wharton for 21 years. I was a research statistician for 2 years before that at the Educational Testing Service in Princeton. So if you've taken an online test in the TOEFL or the GRE or the SAT, that was my first job, was designing adaptive algorithms. As a matter of fact, I see Olivier Toubia here. When I first came to the field of marketing, I didn't think, by the way, I always joke, I'm the chair of the marketing department, that's true. I was the editor-in-chief of Marketing Science, that's true, but I've never actually taken any marketing courses. And so when Olivier started doing his work on adaptive conjoint, this seemed like old times for me, because when I first went to ETS, they said, all right, so when someone gets a test item right, you got to give them a harder test item, because you got to zero in on their ability quicker. When someone gets a test item wrong, you have your posterior belief about their ability is lower, you got to give them an easier test item. And then, of course, I never thought about applying it to conjoint or anything else. And then, of course, a brilliant person like Olivier came up with this idea and all these methods for doing it, and it made me feel like old times. So what I'm really going to talk to you about today is really a 20-year journey through my career. So probably in the first 15 or minutes or so, I'm going to relive old memories of papers that I've written over the last 20 years. Each of them having something to do with basically either correlation, what I call self-selection problems, and then eventually I'll move into kind of causal inference. The other thing I have to admit that came to my mind is, so my doctoral advisor, his name's been mentioned many times on many of the slides, was Don Rubin, and so I think he would be proud. Well, he's alive, so I can tell him. It's not like he's gone anywhere. But I think he would be quite proud that I was here talking in a conference on causal inference and machine learning as well. So let me get to the first paper. Actually, the first paper I ever wrote was with someone who was visiting Harvard Stat at the time. His name's Kjell Doxum, very, very famous mathematical statistician. And he actually was very interested in the problem of what he called local treatment effects, or what we call here now local treatment effects. And the idea is very simple. Imagine you have, let's see if this works, oh good. Imagine you have a bivariate scatter of x and y, and imagine the shape of the pattern looks something like, we called this the pear shape. I remember I actually liked the fruit pears, so it was a very nice thing to talk about pears all the time. But imagine the relationship between y and x isn't linear, and not only is it not linear, but you can see that the variation, if you like, the conditional variance as x is increasing also seems to be increasing. And we called this the correlation curve. And so the first paper I ever wrote tried to understand, if you like, first of all, dy dx is not going to be constant, but also the variance of y given x is not going to be constant. And so what do you do in situations like that? Can you come up with, if you like, as mentioned in both Stefan's, Navdeep's, and Ava's talk, treatment effects aren't always constant. Depending on where you are on the curve, if you'd like, dy dx is going to be very different, and we came up with methods to do that. So that was the first paper I ever wrote, was in JASA back in 1994. This was as a PhD student. So this kind of brought back some old memories. Then I started moving, by the way, you're going to notice as I'm going down, and there's no order in this except time. You start at the top of your oldest paper, and then you kind of move forward. And so the next paper I wrote was actually a vendetta. So I submitted a paper to Psychometrica. I'm a statistician, but I also consider myself a mathematical psychologist. I submitted a paper to Psychometrica in 1995. 21 months later, I get back like a 2-line review. Your paper is rejected. And I'm like, well, okay, you can reject my paper. Could you at least do it quickly? So I decided what I was going to do was I was actually going to collect data on submission times and times to publication in a bunch of different journals. And by the way, let me just be clear. I was an assistant professor at this time, but I was literally going to publish. I wonder how quick JASA is in publishing stuff. I wonder how quick, and as far as I knew, this would be the last paper I ever published. And so we collected a bunch of data between, in this case, you can see Psychometrica between 1988 and 1997. And you see this pattern here, and these are the years, and these are just box and leaf plots of the time to publication, and you can see the median time. And a normal thing would say, so Navdeep, if you read this, you can see the medians are going down over time. A natural thing would say, well, I guess Bradlow has no claim. Psychometrica, maybe it's long, but they seem to be getting better from literally, by the way, 5 years in time to publication. This is not rescaled to protect the innocent. This is the actual number of months, down to something like 15 months. But this is where you have to be careful, because then you say to yourself, well, you stupid idiot. I'm sitting here in 1997. The maximum of this distribution is 3 years. This is your classic self-selection problem. This censored data. They can't have if I'm standing here in 1997, of course, anything published then, it can't be more than 3 years. So actually, Psychometrica, if you actually do the correct analysis, Psychometrica actually got no better. They got better from this period. But in this period, actually, this is just what would happen if there was censored data. In some sense, you can't publish a paper. You can't look at a published paper time before it actually gets published. And so that was kind of an interesting paper. This is a paper we wrote in one of my favorite journals, Chance. These aren't necessarily, if you'd like, the most rigorous academic paper, but you can actually see the title of this paper. It's called A Selection of Selection Anomalies. And actually, just as a story, Howard Weiner was my first boss at ETS, And this was his 14-year-old son at the time who knew a lot of mathematics, and so we kind of wrote the paper together. So that was kind of fun. Now, of course, what's scary about it is you can do the math. That's like 20 years ago. He's like, 35 now. He's like a real person. So that was kind of scary for me to think about. Now going forward in time, the next one was a paper I wrote while at ETS in the Journal of Educational and Behavioral Statistics. You can see the reference here with a former colleague of mine, Neil Thomas. And this is actually one of my favorite papers because the finding is so startling you won't believe it, but I promise you it's true. So let's imagine you're at ETS. Let's imagine you're taking a standardized test, and we all know there's the multiple choice part of the test. They give you a bunch of questions, and then they say, Ryan, pick one out of these three that you'd like to answer. Okay, so this is the classic. You get to select. You get to pick which one that you do. Okay, so we were very interested in the following. I wonder if which item you select is actually informative about your ability. Forget your actual score that you get on that item. Just did you pick number 1, did you pick number 2, or did you pick number 3? Now, it turns out it's very informative. Why? Well, there's two arguments you could make. One is smarter people are better at picking items that they can actually answer. That's number one. And two, smarter people can actually pick easier items. It actually turns out when you run this is a Bayesian IRT model, when you actually run the model, there's more information in the item you selected than the score you got on that item. So in other words, I could just go to Ryan, which of the 3 items do you want? Ryan picks them like your test is over. You don't even have to do the actual item itself. Because just by knowing which one you picked, if you'd like, in the technical term, lowered the posterior variance more than actually the score you got on that item itself. So that was a really interesting problem to me about selection effects, and that in some sense, I'll get to this a little bit later, in the Don Rubin language, we've heard some of the Don Rubin language, Sutva is Don's stable unit treatment effects and stuff. One of the other things he talks about is non-ignorability. This is a non-ignorable selection mechanism, which means the likelihood of which item you select is correlated with the parameter you're trying to estimate, in this case, ability. So in other words, the fact that you picked an item is actually informative, and you need to build that into your likelihood function. So that was kind of a fun project to work on. And thinking back in time, Neil's a close friend. The next one, actually, Ava talked about encouragement designs, actually, in her talk. And by the way, she could not have known, because I didn't, as a matter of fact, I loaded this slide deck on 5 minutes before to Kinshuk, so there's no way she could have known that I was also going to talk about encouragement designs. But actually, it was the first paper I actually ever wrote in marketing, was about the use of encouragement design. So let's imagine someone gets coupons or doesn't get a coupon, and someone's encouraged to use the coupon versus not. Now you might say, why would you encourage people? And here's just a very simple additive linear model and the proportion of people, if you'd like, in each group. What you can show in an encouragement design is that well, first of all, even if coupons and non-coupons aren't randomized, which, by the way, they may not be by the firm, if you randomize who gets encouraged or not, in some sense, and Navdeep talked about this a little bit, you can actually borrow this randomization if you're willing to make an assumption about the lack of interaction between this randomization and the delivery of the coupons or not. And typically, this is randomized, so it's reasonable to assume an additive model and not a linear, and not an interaction term between the two of these. So this got me into the idea, and I love the way Navdeep said it during his talk. Yes, I would love to actually be able to run an experiment that randomizes this thing, but I can't, because the firm is going to choose that to maximize profits. But I can randomize this other thing, which will help me identify the effect of coupons or not, if I'm willing to make an assumption. And actually, this is kind of one of the things I've always loved in the field of statistics. You can either have good data or assumptions, and sometimes you have both, and sometimes you have to replace the data you really want with assumptions you kind of sometimes have to make. And this paper kind of taught me a lot about that. But again, that was nice to go back and relive that one. This is actually a paper I wrote with a former colleague of mine, Elaine Zanuto. Elaine now actually works for a big marketing research firm and actually heads their analytics division. And the idea is very simple. You can see the title of the paper, The Perils of Data Pruning in Consumer Choice Models. And here's what we mean by that. So how many of you have ever worked with scanner data? Probably a lot of you, doctoral students, a lot of people have worked with scanner data. And imagine you have 15 brands in the data set, let's say orange juice, brands of orange juice. And Ava says to herself, well, I'm just going to look at the 4 biggest brands. We do this all the time in marketing. Now, why would we do that? Well, 15 brands is a lot of parameters. You know, maybe there's sparse data for some of them. And then the justification Ava gives is, well, I got the big brands, so I'm good. Well, you're not good. And that's what we're saying. This is the perils of data pruning. And this is where you pruned the data. I don't mean missing data. I mean you had the actual full data set, but you chose to only look at a subset of it. Now, what would be a story of where you're not good? Well, someone give me a reason why a brand could actually have low market share. What could be a reason? Maybe marketing's not effective. Maybe the distribution. But I don't really get to manipulate distribution, so that's not it's a good one, but it's not one I'm interested in here. But it could be that their marketing's not effective, their prices are too high, maybe they've targeted the wrong people. But last time I checked, that's what I'm trying to measure. So by pruning the data set, I've actually taken the variation. Number one, I've limited variation. Yeah, Joe, 1 second. 1 second is I limited variation. And number two, back to that other idea, I've created a non-ignorable missing data mechanism. In other words, now, by the way, I should say, and Navdeep talked about this a little bit in his talk, but not as much as I'll say it in the following sense. You're fine as long as your inferential goal is to say, here's the price elasticity of demand, or here's the effect of marketing amongst large brands. But the minute you want to make an inference for a more general population, then you have a problem because you don't know anything. As a matter of fact, the fact that they're small brands means they maybe have high price elasticities, and you're pruning them away, and you're going to say, hey, brands in soda have low price elasticity. Well, what does that mean you do? You raise prices. Well, it's okay to raise prices maybe if you're a big brand and you're not competing with small brands, but if you are, it may not be the right thing to do. Yeah, please, Joe. Yep.
Small, but it's a strong brand, but there's nothing weak about it. It's a small, niche brand.
Well, so what you're also bringing up, which is a great point, is that brands, there's lots of things about a brand that you may be interested in measuring. For example, you're saying maybe the intercept, if you'd like, is small, which means that it has low share, but it could very well be effective towards a target market. It could be effective in their pricing or advertising. There could be lots of reasons. And by the way, in the technical language of statistics, you have your observed data after pruning. You have your parameters of interest, theta. But that's not actually the likelihood. The likelihood that you have is you have your observed data, and then you have your selection mechanism. And in the Don Rubin sense, there's this second piece of the likelihood is what's the probability that these are the ones that, if you'd like, made it into your final data set, given not only your observed data, but the missing data, this is the data that you pruned, and some other set of parameters. And for those of you that, based from your basic statistics class, so when does this likelihood equal this likelihood? Well, there's two times. Number one is if this actually doesn't depend on Y miss, and you can just factor it out of the likelihood, that's a good start. But that's not the most important one. The most important one is that phi and theta are what Rubin calls independent of each other. In other words, if the parameters of this model don't influence the parameters or don't have any intersection with the parameters of this model, then the selection mechanism is what's called ignorable. In other words, if I'm interested in measuring theta and the selection mechanism doesn't involve theta, then who cares what it is? It could be anything you want, and there's no problem. This is why, by the way, it's a good thing to talk about in a conference on causal inference, because a lot of times you'll have endogeneity, but it won't be endogeneity towards the problem you're interested in solving. You could have self-selection, but not self-selection that actually influences the problem you're trying to address. So when anybody can say you've got an endogeneity problem, a self-selection problem, but the question is, if I'm interested in price elasticity and I don't believe this selection mechanism has anything to do with prices, then it's an ignorable selection mechanism. And sure, you're right, this does not equal this, but for inference about theta, it does not matter. So this was another project we worked on, published in QME in 2006. I'm pretty sure it was one of the first papers ever published in QME. I don't know when you guys might know when QME was started, but this has got to be pretty early. The next one actually shows you what happens when very smart behavioral people partner up with stat-type people. This is a project with my colleague Jonah Berger. We were interested in, actually I thought it was a very interesting question, which is, if I hear the name Navdeep And for example, let's imagine I was having a child. I'm well beyond that. I got 3, but I'm not having another one. But let's imagine I was, and I know I'm just at a conference with Navdeep. I wonder if I'm thinking, let's imagine I'm considering 2 names, Gavin and Navin. Well, Navin kind of shares something with Navdeep, right? Like that first NAV part. So we were interested in is when certain names get popular, do names with overlapping what are called phonemes, sounds, also get popular? Not unrelated to what Ava was talking about in some sense in social effects. Now, I don't necessarily mean in a causal sense. I just mean if names with similar sounds get popular, do other names that are, and this also relates to Stefan's talk, if I create a little ball, if you'd like, around certain names in a distance space, do ones that are closer in, are they correlated processes? And that's where we're interested in this paper. And as you can see here, on the x-axis here is the number of sounds that are shared, and you can see here this is the correlation between their time series. It turns out they're very correlated. Now, what does this have to do with selection? Well, what we also did was we wanted to test this in some sense where there wasn't endogeneity. So this plot here on the right looks at what happens to a name when we think this is an exogenous event, when a hurricane hits. So let's imagine a hurricane hits and now it's all over the news. So everybody hears about Hurricane Sandy. Now, I don't think they're naming it Sandy because they think Sandy is going to be a popular name. In fact, there's an alphabetical list order. It happens to be after maybe Hurricane Robert or whatever the R1 happens to be. So there's no endogenous selection of Sandy based on the popularity of names. But it actually turns out when hurricanes hit, and this on the x-axis here is the strength of the hurricane, and the diffusion of similar sounding names, when stronger hurricanes hit with certain names, those names become more or less popular. But there's diminishing marginal returns because, I hate to put it this way, people didn't like the name Sandy or Katrina that much once those hurricanes hit. So popularity is good, but actually only up until a certain point. And the reason this is related is because this was a source of, we were trying to say, could we get to a more causal story? Because maybe I choose the name Navin because lots of other people, the homophily, the simultaneity, all the things that Ava talked about, but hurricanes are an exogenous shock, and we actually see that pattern. So that was kind of interesting. Yeah, Kinshuk?
How do hurricanes get named? Do they get named based on popular existing names?
No, that's my whole point. They don't. So I don't know how they chose Sandy versus Sabrina versus Samantha, but actually, let me just say, by the way, they're also published years in advance. And so, of course, Mr. Miami here knows a lot about hurricanes and how they're named. But I do know you can look up into, let's say the year 2020. Right now, you can go see the list of hurricanes starting with A, B, C, D for 2020. So, it would be, again, could somebody want to make an argument that a hurricane's not an exogenous? Yeah, I guess someone could make it. I think the data refutes that. So that's how they're named. So this was kind of an interesting paper. And again, the part I thought that was interesting is this part I think is interesting. We were very interested in this part, in some sense, to bring us closer from a correlated story to a causal story, hence my title, From Correlation to Causation. The next one is actually a paper with one of my former doctoral students, Blake McShane, who's now at Kellogg, also at Jonah Berger. This paper appeared in JMR. You may have wondered, when is Eric going to get to a paper that was actually published in marketing, which is his home field. So this is, although I had one in, again, marketing letters and QME, which is kind of a blend. What we actually were interested here is, if you see other people driving a new car, does it make you more likely to drive a new car? Now, you might think to yourself, well, you might leave here saying, well, I heard Stefan and Navdeep. I'm just going to randomize and, well, if you're wealthy enough to, if your school and your research budget is wealthy enough to randomize an experiment to assign people to drive new cars, please come and see me, because I'd like to come to your university. But I can't actually randomize people to drive new cars or not. So it's going to be very hard to tell a causal story here. But you'd like to do something that's at least as close to causal as you can get. So let me show you the pictures I have here. This is actually, we actually know, we had a data set where we know were men buying the cars or women buying the cars. And so what this represents, let me just show you. This is how many people bought new cars in your neighborhood, like your zip code. And then this was like 1 to 3 miles away, 3 to 5 miles away, 5 to 10 miles away, 10 to 20 miles away. So while it's not a causal story, And we had fixed effects for different areas so that we're taking out any unobservables that we didn't have. So, I mean, you're right, it's not a randomized experiment. But someone come to me with a plausible alternative story, whereas the distance from where I live and work, we checked where you live versus where you work, as the distance goes up, the effect of other people goes down. Now, I can't prove that's causal. You just come up with a plausible alternative explanation, and I'm happy to listen to that alternative explanation. So sometimes, while you can't run experiments and prove something causally, once you put in fixed effects and you start looking at specific patterns, like with distance, you start to say to yourself, I don't know if it's causal, but I don't have a better story, and so viewing people makes me want to buy a new car. That's what we found here. So this was interesting again, and actually it's a different talk I tend to give in these keynotes. It actually turns out, it's another thing I realized when you look over your Vita after 20 years, I love problems that involve distance. I don't know why, but I just love the problems like if Navdeep and I are close to each other, we have more of an effect on each other, and if we're far away from each other, we have less an effect, and think of distance being broadly defined in all kinds of different distances, and this is another one of those problems. Okay. So the last 35 minutes or so, I actually want to talk about a specific paper, probably the most recent paper that I have, and one that's actually an experiment. This is work with Daniel Zantadeshi, who is a postdoc in our Center on Analytics. He's now a professor at Ohio State. My colleague Ellie Feit, who was the managing director of WCAI, who's now a professor at Drexel, and me. It's a paper that just appeared in Management Science. And this is probably one of my favorite all-time papers that I've written, because it's addressing a problem that I think everybody, as I go around and talk to companies in my role with WCAI, it's a problem, as far as I know, that every company wants to know the answer to, which is, I got $1 million to spend on advertising. How much should I spend on Facebook? How much should I spend on Google? How much should I spend on email advertising? How much should I spend on search engine optimization? Everybody wants to know the answer to this problem. And let me say the good news. The good news is, it's actually a trivial problem to solve. Very simple. A lot of people have this, last click attribution's bad and all this other stuff. It's actually very simple. All you've got to do is take all of your marketing channels and run a massive multi-channel field experiment. Well, that's how simple it is to do. But let me tell you the practicality of it. I run Wharton's Center on Analytics, and we have 100 partner companies. None of them, zero, run those types of experiments. Zero. So when someone says to me, Professor Bradlow, help us with the attribution problem, I'm like, I can tell you exactly how to solve that problem. Run a multi-channel advertising experiment, know who's getting, at the individual level, because I'm a Bayesian guy, so I'm about heterogeneous treatment effects, measure who's getting those treatments. So you're now thinking to yourself, well, how am I going to measure who gets TV, for example, or billboards? That's why you got a problem. But conceptually, it's a simple problem. Just measure treatment effects measure exposure at the individual level, have it tied to your CRM system, track it over a period of time, and you're done. It's what I call fool's gold. It's easy for me to say it, but it's data you can kind of never have. Well, sort of. So I'm going to talk to you about a project today where it is the data we have. This is actually, we found one company, one of our corporate partners, who had actually run a multi-channel experiment where literally there's no possibility there was other forms of advertising they got, because they only do 2 forms of advertising. There was randomized holdouts, which is absolutely the crucial part of it, and I'll show you how you can take away any possibility of endogeneity biases. So I always describe this talk as, well, it's only recent, actually it's the first time I've given this talk, but it's the data you wish you had, but most of the time you can never have. And the reason I also call this slide a slap down from the editor, I'm not going to call him out in a positive sense. So we sent the paper into Management Science in 2015 to begin with. The editor is a close friend of mine, Pradeep Chintagunta. He writes us back in the review letter. We look at the Associated report. Associated's like, this is fantastic. The reviewer's like, this is fantastic. Then we scan up to the editor. We're like, well, this is an accept or a conditional accept, reject. But then of course you wonder, why is the paper rejected despite everybody loves it? And I want to give Pradeep a lot of credit for this in a positive sense. What he said was, and it's something that will probably stick with me for the rest of my career, he said to me, Eric, we could publish this paper pretty much as is with no modification whatsoever. But let me tell you why I'm going to reject this paper. It turns out it's not the paper I'm showing you. I'll tell you why in a second. The data we originally used in our paper was not an experiment. It was observational data. We're using instrumental variables. We're using all kinds of what I'll call fancy econometrics to fix the problem of the fact that we actually didn't have experimental data. And Pradeep basically just said, look, I'm drawing the line in the sand. I'm not going to publish one more paper on advertising effectiveness without experimental data. So the minute you go out and get some experimental data, you don't have to change the model. All you have to do is change these 3 tables and I'll publish that paper. But this paper, I am not publishing. So that's why I refer to a slap down from the editor. So he slapped us down. And so that's when I said we had to start thinking, well, how are we going to get multi-channel randomized experimental data? And that's the story I'm going to tell you about for the last half hour. But it's a good story. In other words, he wasn't saying there's anything wrong with our paper. As a matter of fact, it was, and this is good news for not good news, it's good advice for the doctoral students. It was entirely, the first version we submitted was entirely consistent with tons of other papers that had been submitted on advertising effectiveness without randomization. Lots and lots of papers. And then, of course, in some sense, the gentleman sitting here to my left actually hurt me in some sense because he obviously, since Pradeep knows Navdeep quite well, said, you know there are people running randomized experimental data sets in marketing right now. And I said, damn Navdeep, I'm going to get him back someday. But either way, let me tell you about the story here. Now, as I mentioned, if you go to most people, everybody gets ROI. It's, you know, what's my incremental sales minus my cost divided by my cost? And you say, well, that should be pretty simple to compute. That's not a problem. Well, this is the hard part. I mean, cost of marketing, firms know what they spend. That's not the hard part. The hard part is what is the incremental sales due to the amount of money you're spending. That's the big challenge here. That's the big challenge. And so why is it hard to figure it out? Remember what I just said. First of all, you need to know exposure data. Who got exposed to which forms of advertising? Now, of course, in digital advertising, that's a lot easier to do than in other forms of advertising. And if I had 3 hours to talk, what I would talk about in my second 2 hours of here is all the papers I've written on what I'll call Bayesian estimation with aggregate data, where you don't actually know who watched the television, you don't know who got this ad, but you know in margin how many people got it. So I've done a lot of work, but this is a different issue, which is, number one, you don't have the data. So you don't have the data typically on advertising exposure at the individual level. Or at best, you have a hybrid, which is some forms of advertising you have at the individual level and some forms you have at the aggregate level. As a matter of fact, it's another paper I'm very proud of. Ellie Feit and I wrote a paper in Marketing Science in 2013, and this is what everybody calls this the data fusion problem. What do you do when you have individual level data for some forms of advertising and aggregate data for other forms of advertising? That was a paper on, for those soccer fans out there, this was the data from ESPN on the ESPN World Cup. We knew which ads people got through ESPN.com. We knew which emails people got. We knew how much in total in television people watched. Therefore, we knew the total number of ads delivered, but we didn't know who got which ad. Okay? So number one is data. Second is multiple channels. Actually, it turns out about half of our corporate partners do run experiments. They just don't run multi-channel experiments. And so they'll run a TV experiment, they'll run a Facebook experiment, but they won't run a factorial experiment. And so again, this is a paper on multi-channel advertising. And so I need randomization across those channels. I can't just have a bunch of one-channel A/B tests. That's not going to work. So actually that's the big challenge here. A lot of companies run single-channel experiments, but multi-channel experiments not as much. The third one is time. And so one of the big questions, Navdeep talked about this a little bit, is when you run an experiment, like how long do you wait? Like how long do you wait until to see the effects of this? And it's a big issue. People have studied this in marketing for a long time. Let's imagine, this isn't us, but let's imagine your experiment is about banner ads. Well, if you actually look at the price of banner ads, like back in the late 90s, they was really high, partly because there weren't a lot of other ways to spend money on advertising. And then they dropped because people knew that the short run effects, banner ads don't actually make you click that much. But then people started to find that banner ads build the brand equity. And so there's actually a longer term effect. But again, most people run short term experiments. And so how long do you wait to actually find, Ava, obviously, Oded, lots of people in this room have done work, Kinshuk on Michael, on customer lifetime value. Well, how long do I have to wait to see these effects? That's a big challenge in advertising effectiveness. And the last one is the one that I'm going to spend the most time on, talking about correlation versus causality. Most firms, you actually want to say, because I spent an extra dollar here, here's the ROI I got of that expenditure. I actually want to know the causal story. Okay, so let me tell you about the data set, and you can tell by my title I'm very happy about this data set. This is the holy grail of advertising attribution data. This is data from a multi-channel retailer. Let me tell you about the data set. These are 300 customers from the retailer's CRM system. Emails were sent to each customer, and catalogs were sent to each customer. We have the daily purchase amount, both direct, meaning online, and in-store for each of these customers. And just to let you know, is there some leakage? A little bit. But actually, this is a conservative number. 98% of this store's transactions can actually be tied back to the individual customer. They know exactly who made these transactions. So there's no leakage on the Y space, if you'd like. These are observations over about a 2 to 3 year period, and this is the key part that I'm going to talk about, is the part that there was randomized holdouts, meaning they actually ran in this case, 2-channel experiment with emails and catalogs where they actually randomized for every campaign. They said some of the people are going to randomize, 10% aren't going to get an email on this campaign, 10% aren't going to get a catalog for this campaign, and they did this over a 2-year period. And the good news is, I'll talk about this in a second, these are the only 2 forms of advertising that this firm does. They do not do other forms of advertising. So maybe I've bait and switched you a little bit. You were going to say, boy, I wonder how Eric's going to say the ROI of Facebook advertising, or I'm not going to say anything about that. But I am going to say that I know how to, if you just took this exemplar and just approached it in multiple channels, but in this case, the reason I say the holy grail is we know that all of this was randomized. So I'll talk about that in a second. Just to give you an idea, one question you might ask yourself is, why not just run like an aggregate? And actually, this is actually an interesting issue. Why not just run an aggregate marketing mix model? So, for example, here's sales over time, and here's let's say the fraction or the aggregate amount of marketing expenditure over time. Why not just run an aggregate model of aggregate sales on aggregate advertising expenditure? It actually, does anybody know, why wouldn't that work too well? If you have aggregate sales against aggregate advertising expenditure, why might that not work too well? Any thoughts? Say again? Well, part of it, but although an individual level model might still have the same problem, if you think about it, if you heavily do advertising all the time, there's no variation. There's no variation in the aggregate amount of advertising. Very, very little variation. They always send people emails. They always send people catalogs. So in aggregate, there's very little variation. However, let's take an example of an individual customer. For an individual customer, as I just told you, they do randomized holdouts. So I'm actually going to exploit the fact that at the individual level, there's actually variation at the individual level. And that, in aggregate, they tend to do the same total amount of advertising in any period, but not at the individual level. At the individual level, there's variation in the amount, because we're controlling that variation, the amount of email or catalogs. So this is actually one of those times where there's, this is not it's sort of like an aggregation bias issue. There's more variation at the individual level than there is at the aggregate level. And so you want to exploit that variation at the individual level. Yes, please. Great. It's a good question. Just to repeat the question, how did you get the company to do this, or were they already planning on doing this? It actually turns out, if you looked at the data of this data, 2012 to 2014, remember I told you we submitted the paper in 2014 and then got slapped down in early 2015. they had already done this. So literally, I mean, this is, I don't want to say an advantage of running a center on analytics. I literally called every single one of our corporate partners and said, forget the data you've shared with us at WCAI. Have any of you run a multi-channel experiment? And this one company got back to us, said, actually we did. We ran a 2-year multi-channel experiment to understand the effectiveness of email and catalog campaigns. So no, it's a much bigger pay grade than mine to try to go to a company of this size and try to get them to run a multi-channel advertising experiment. But I will say, many people in our field have been successful in doing that. I'm not one of them. Yeah, I'm not one of them. They had the data already. They just hadn't sent it to us. And then they did, so that was good. So this is just to give you an idea of the variation at the individual customer level. And so again, this is my point, using customer level data allows us to exploit that variation. And by the way, let me just say, by the way, this is not, if you go back to John Little's original work on advertising in the late 1970s, John Little back in the 70s has already espoused or touted the value of what's called single source data, meaning tying together marketing expenditure with sales at the level of the individual customer. And again, in our data set, this is the key. Variation is not enough. If you've heard Stefan, Navdeep, or Ava's talk this morning, I mean, you can get variation, but if it's endogenous variation, that's not the good variation. You want exogenous variation. And remember, just to remind you, the only reason every one of these people, and I'll talk about this in a second, are in the targeted population for emails or catalogs. Therefore, had it not been for the randomized holdout, they all would have gotten it. So you can't, that can't be a reason. There's no other reason except for the randomization that these people did not get emails and catalogs. And that's exactly the variation that we're going to exploit. Okay? And so for each campaign, the company designates a list of targeted customers from their CRM database. Then the company randomly selects a fraction of targeted customers to be held out. Now, for those that are, maybe Navdeep is sitting there saying, I wonder if they target, the fraction that they target to hold out varies depending on periods of peak demand versus low demand. Fortunately, no. Because that would be, see, there's an example where you would have randomized holdouts, but the fraction or who they or in some sense the amount of randomized holdout could be endogenous. And I'm going to show you some data in a second to say that's not possible in this case, because essentially, they essentially said 10% every period, each and every period. We don't care if it's Christmas, we don't care if it's Thanksgiving, we don't care if it's the big peak seasons of the year, we're keeping the fraction of randomized holdouts constant. Yeah, Michael? Yeah, good question. The reason it might matter is if something we're going to talk about in a second is actually relates to both Stefan's talk and a little Navdeep. If you were trying to estimate heterogeneous treatment effects, you might not have, and this is something we're going to talk about, you might have lower power in certain parts of the distribution. You would not get bias. You would not get bias in the estimate of the treatment effect, but if let's say you only had 1% randomized holdout, you're going to have extremely low statistical power potentially to estimate certain treatment effects. And that's, I'll talk about that in a second. Yeah, please, Ryan.
I'm curious about the actual effects that you're kind of trying to, maybe you're getting there. So in a setting like this, you would have all of these permutations of ordering some possible effects through time, right? Like
We're going to get there. We're going to get there. So, right, Ryan wants to know, for example, let's imagine my pattern is catalog, 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 no catalog, no catalog, catalog, whatever. How do we deal with that path and ordering? And that's what I'm going to get to. Yeah, that's the math part. That's the fun math part that's coming up. Okay? And then again, this induces exogenous variation in advertising exposure. And again, it could be, therefore, we can make a causal statement about the attribution to advertising. Okay? And again, this is back to my comment. They're always targeted. So everybody here, and by the way, when I say targeted, it's essentially, since 98% of the people they can track back, and these were people that they had their email address for, essentially that was how the targeted list came up. These were all people for whom they had their email contact. And what they would say is, if they're not in their email list, they don't even care about those people anyway. And so again, this is the sample. Okay? Just to give you some, if you'd like, just to give you a little bit of reduced form evidence of effects here. Here was an example of the July 12th catalog campaign. These were people that were treated that got the catalog. These were people that did not get the catalog. You can see the average 30-day sales between the purchase. You can see the purchase incidence. You can see that, as mentioned many times here, you might as well check the randomization, like were the people that got the treatment and not, were they different before the treatment period? You can see they were. And you can see here a very large effect of the treatment, but the bane of individualized experiments and isolated campaigns, Navdeep pointed out in his work as well, this is a pretty damn wide confidence interval. And so this is a big challenge if you're going to run a campaign, is that the confidence interval might be, there's no bias, it's just an extremely wide interval. So now I'm going to start to get to Ryan's question. So for example, if you look at the data from all of our experiments, again, starting in April 2012 to April 2014. This is for catalogs. These are 95% confidence intervals for the effect of the treatment. Again, remember, every single one of these is a randomized holdout. Okay? So now you can see here, I mean, it doesn't take a genius to figure out there probably is a treatment effect. I mean, just look at all of these intervals sitting above 0. Most of them are entirely above 0, although there's some fairly wide ones. The real question is, how are we going to combine, or if you like in the statistics language, how are we going to do a meta-analysis of all of these different individualized campaigns and aggregate the information from all of them? And just to show you a similar picture, it's hard to see in light blue here, but you can, I don't know how well you can see, but these are the effects of the email campaigns. By the way, a lot of these are centered very closely to 0 and also have extremely wide confidence intervals. So again, that's where the math and the modeling is going to come in, is the combination of campaigns. How are we going to come out with an overall effect of the treatment, noting that we may have done, in this case, this is weekly data, so we may have done 104 different email campaigns, and catalog is monthly, 24 catalog campaigns. How do we combine the information from all of these, if you'd like, isolated experiments? Okay, and this is the idea. We're going to actually use a mathematical model to pool this information. Yes, please.
But was it about the same product everywhere, both for emails and one particular brand?
Great question. So, well, let me answer that one. I guess I'm senile, and then I'll answer that one, and then I'll answer your other question. I didn't mean to cut you off. The answer is, this is something I have on slide 35, where I talk about future research. A great question, not one we addressed, was what do we know about the contents of the advertising versus what category they bought in? We don't study at all the quality of the advertising or anything like that, just the presence or not of email or catalog and people's purchasing behavior. We don't actually have what was in their market basket, or we don't have, the firm would have it, that would be a separate analysis about what was in the email, were they promoting a certain brand or a certain, was it a price discount? We don't have any of that.
So they bought different products.
They could absolutely be right. It's a good point. So in some sense, now let's talk theoretically. What are we actually measuring the average effect of? We're measuring the average effect of, I guess, I don't even want to call it generic, but an unspecified might be a better word, an unspecified campaign. It wouldn't tell the firm how to create it. It wouldn't tell the firm this type of campaign might be more effective than another type. It would allow me to compare emails and catalogs, but not types of emails, types of catalogs, types of inserts, or other stuff that you might want to manipulate. We didn't have that data. But by the way, it would be trivial, I'll show you where, be trivial to build into our mathematical model if we had, let's call them covariates of the different campaigns. We don't. We literally just treat them as email versus catalog. Of course, we know their date, but that's all. We don't know anything else about them. It's a good question. Okay, so let me also just quickly talk about this work in the realm of advertising. I think the reason why this paper has gotten as much popularity, it's gotten a bunch of sites already, is that we claim, but Navdeep will possibly correct me after the talk, but maybe as far as we know, it's the only paper, at least as of 2016, or 15 when we wrote it, that was published that's actually a multi-channel field experiment. There may be other papers that have appeared since. I don't know of them, but I'd be interested. Again, it's really hard to get that kind of data. So, let me tell you about the model, and Ryan, this is going to answer your question. So the model we build is our old friend, the ad stock model. So what do I mean by an ad stock model? Well, this is called lots of things. It's sometimes called a Koik model. It's sometimes called a leaky bucket model. Advertising happens, it has a contemporaneous effect, and it has a lagged effect over time. It's also, I see Xu Ming here, it's also a version of an autoregressive model with a very specific form. And so that's the basic idea. We're going to apply a Koik model at the individual customer level, because remember, we know who got the advertising, email or catalog, at a specific point in time. We know purchasing at a specific point in time. So advertising through exogenous variation comes in. Let's call that water goes into the bucket. Time passes, water leaks out of the bucket at a given individual rate. And there actually, in this case, since there's email and catalog, there's going to be 3 buckets. Let's call it email stock, catalog stock, and interaction stock. And again, because of the exogenous variation, we can attribute the variation in stock to the randomized holdouts. That's the basic idea. So basically, Ryan, you may not be satisfied with the answer, but the way we aggregate through time is by assuming a parametric form that allows us to say things happen at an exponential decay rate. Classic Koik model. Water goes in, lags go out. Every individual has a different decay rate for each channel, and so we're relying a lot on the data, but we're using a parametric form to look at all possible paths and to use that to estimate the actual effect of the advertising. Okay? So, just to remind everybody or introduce you if you've never seen a Koik-like model before, I should also say, so let's imagine, I'm not going to skip it, I'll skip Y star for just a second. Y star is, if you'd like, your latent purchase amount for person I at time t. Now, why do I say it's latent? Well, we're actually going to fit a Tobit structure on the model. It turns out the reason we need a Tobit structure, this is a form of what's called a spike at zero model, is that much of the data set is zeros. You just don't buy in a lot of different periods. And so I need a way to model all of those zeros. And so we're using what's called a Tobit 1 structure here, but here's the magic, here's the Koik structure. So again, we're using a Tobit 1 selection process. So if this Y star, which is latent, is greater than 0, then that's the Y you see. If it's less than 0, then it's 0. These are the channel-specific shocks. So K indexes channel. Notice the amount of stock or water in the bucket at time t is there's an effect of X at the amount that you put in, and it decays at a rate rho. So rho is the stock variable. And then there are interactions. So how much did you put in K and how much did you put in K prime? So think of this as how much did I invest in catalog at time t and how much did I invest in email at time t? And there's a potential interaction between the two. And then, of course, since I'm Bayesian, everything's going to be heterogeneous. Everybody has an individual intercept, so some people just buy more than others. These are the stock variables. Everyone has a different stock variable. Everyone has a different decay rate. And this is going to be the Bayesian machinery we're going to add. But again, let me just remind everybody just quickly, this was no change. This was our original model in the first paper we submitted, except the X's had all kinds of endogeneity and other problems that we tried to fix through math as opposed to actually getting randomized holdout and variation. Okay? And just to give you some model-free evidence of interaction, there were 263 customers that in a given month, in this case this is the July campaign, that got catalog and email. These were catalog only, these were email only, and these were neither. By the way, the fact that neither has this shows you why you kind of need to pool across campaigns. You can see extremely wide intervals for any given campaign. Okay? And so how do we do the estimation? I'm not going to spend too much time on it. There's really actually no methodological contribution here. It's a standard Bayesian dynamic linear model that uses the standard common filtering forward backward algorithm to actually do the computation. So actually there's no contribution there, but it actually turns out to be there's lots of methodological challenges, but nothing new. Okay? So again, how do we deal with the endogeneity problem? Like, for example, maybe there's targeted advertising. Well, again, as I mentioned, well, first of all, there's a recent paper by Liu, Otter, and Allenby that says that won't be a problem. And secondly, just to remind everyone, we know that's not possible. Even if this paper had never been written, in our case, all of the presence or absence of advertising, again, is due to randomization. You might wonder, what Ava described, Navdeep described it as well, simultaneity. Maybe they heavy up advertising to certain types in certain time periods, like they observe a demand shock that we don't. Well, actually, this is the pattern of total number of the fraction of customers that were mailed campaigns. It was actually fairly constant. Actually, the blue up here is emails, which you can see is almost entirely constant. And if you just correlate this with sales or any observable, there's no correlation whatsoever. So it's not like they're heavying up or lowing down in periods of heavy or low demand. Okay, just to let you know, we fit our model, the big model. We also fit the model without interaction stocks. Like I wonder if we don't allow for email and catalog to interact with each other. You can see that model fits worse. We also fit a model that says there's a leaky bucket model, but maybe email and catalog all have the same rate. Maybe they don't decay at different rates. So we fit a lot of nested versions of our model because we want to argue that you need all of this heterogeneous parameters, different leakage rates by channels, and all of that. Okay. This is one of my favorite pictures here. So this actually shows the response curve. So if you like, in the spirit for those people that like vector autoregressive models, this is in the spirit of an impulse response function. Suppose you pulse somebody by one email. How much effect is that going to have over time? Not surprisingly, it decays at a quite-like exponential rate. You can see here catalog. Notice, by the way, that, this one is email and this one's catalog. Not surprisingly, email has a higher contemporaneous effect, but catalog catches up very quickly. And actually, what's also neat about this plot, the reason I love it, and this is, by the way, what we show on the bottom, this is the cumulative impulse response. Catalog passes email at about 7 days. Now, what's interesting about this is this was something I was hugging my co-authors literally when this plot came out, and let me say why. How often does this firm send out emails? Once every week. Take a look at how quickly essentially the decay is basically down to 0 every week. How about a catalog? Wonder how long that, 30 days. How often do they send out? Every month. So this is interesting. It actually shows that this firm knows something. Like they're not sending out too many catalogs or too many emails. By the way, there's nothing in our model that would have suggested that 30-day or 7-day. It just happened that that's what the empirics suggested. So this firm seems to be doing something right in their cadence of emails and catalogs. Let me just show you also, you can do one second, Ryan, you can do a decomposition effect. You can see the effect of catalog over time, email over time, and this thin white piece here is like the interaction stock over time. Yeah, please.
Is it necessary that they be monotonically decreasing? So for instance, if I receive a catalog, maybe I spend a few days to look it over and then several days later buy something.
Yeah, so if one wanted to be more general, in the Koik-like structure, first of all, one could allow for a delay effect. So maybe, by the way, that it takes a while for it to kick in. Another possibility is the Koik-like structure forces a downward monotonic pattern. So as I said, you give some, you get some. We assumed a parametric structure that forces a decay pattern. Could one try potentially to do something more non-parametric or more flexible form that might allow for decays, it to go up at some point and down? Possibly. Possibly. Actually, to be honest with you, we use the Koik structure because it's so prevalent in the advertising effectiveness literature that we didn't want reviewers to criticize us, like, why did you pick that functional form? By the way, a nice paper to add might be, I wonder what the pattern of advertising effectiveness is over time in an experimental setting. And one could do something, certainly some of the work you're doing in non-parametrics or semi-parametrics. One could absolutely, we'd be thrilled. I mean, obviously, anybody can have this data. I can share this data with anybody that wants it. Okay? Yeah, please. Oded?
Eliminate one, right? I mean, that's why I guess why you call it holdout as opposed to treatment and control.
Right.
Because in your particular case, it's really holding out. But to some extent, that may explain a little bit of the. You said there is nothing in the data to suggest 7 and 30. I agree, but there is also. I assume, for example, given the randomization you had, you don't observe or very rarely observe a person with a month without email. Meaning 4 times in a row, you'll be below.
Well, we could all compute the probability of that, right?
Yeah. So to that extent, I mean, there is something in the data that I think you probably can say more around these, for email, for example, 2 weeks, about of memory, because at some point, I mean, you're really getting every week, apart from here and there, you're missing a week.
Well, let me. I agree with you. No, I agree with you. Let me reframe your question in a different way, your comment in a different way, which I agree with, by the way. Let me reframe it in a different way. If I had my way, I would randomize patterns, not randomize it each week. Because what I would like to see, this gets to Ryan's other point, what happens if there's 4 misses in a row? Well, I don't have that. Now, I can run that counterfactual, even though I don't observe it, if I make an assumption of, as Ava said in her talk, if you want to call it lack of interference, I can look at if there's lack of interference of missing that email, and I assume that there's a common Koich structure. But if you asked me, what would I love to do? I'd love to have they're going to do an 8-week thing. They're going to randomize the 2 to the 8th possible patterns, and that's what I've got. And then I could look at all kinds of, I wonder what happens if it's 2 in a row, 3 in a row, 4 in a row. I could do that counterfactual, but I actually have almost no variation in the data around that, and I would love to. Yeah.
More for the discussion on experiment, meaning the randomization helps with getting a very clean effect. I think what we are still limited with the variation the experiment generated in the data with the statement you can make.
And absolutely, and by the way, it's a great point to make because that's what you get. In other words, we can't create exogenous variation or patterns of exogenous variation that don't exist in the way. So actually, maybe I'm happy I put Holy Grail in quotes because it's probably, for anybody that's working in this area, it's better data than you have. It's maybe not the best data you could have. It's a nice way to frame it. Let me just wrap up in the next minute or so. Just to let you know, to show you what these plots are, we were just interested in, I wonder if people that are sensitive to getting emails are also sensitive to getting catalogs. And so these are plots of posterior means of, you can see here, beta for email, beta for catalog. It actually turns out it's true. We're also interested in, I wonder if people whose decay effects for email and decay effects for catalog are related to each other. It turns out they're not. We were also interested in, I wonder if people that are sensitive to emails are also have a higher decay for emails, and that's true. So you can see the 2 by 2 of the different effects. We were just interested in that as well. Let me wrap up with this. And Ava said something, and she said it very carefully, and I'm glad she said it the way she did, because I would have stood up in my seat in the back there and said, no. But actually what she said was correct. Remember the slide that Ava showed you with the different dollar amounts on the different people in the network? As long as those dollar amounts are ROI, then I'm fine with it. But if you say, I'm going to target people with high CLV, my hand goes down. And by the way, most firms do that. They say, we're going to target people for advertising that have high CLV. Turns out that's wrong. And this is what we did here. So actually, it turns out under this model, you can actually compute, beautiful, you can actually compute an analytic form for the cumulative impulse response. You don't actually need to do posterior simulation. You can actually compute the posterior distribution of this quantity directly, which we did. And here's what we did. This is what happens if you have no targeting. What happens if you randomly target 10% of the people, so you don't use any of the information, the data? What happens if you target people on recency, frequency, or monetary value? What happens if you target people on some kind of RFM or CLV type heuristic? And what if you target people based on the predicted cumulative impulse response? Matter of fact, we're pretty sure we're the first people in the literature to run this experiment. We actually targeted people not based on how much they bought in the past or how much their predicted CLV is, but how much DCLV, de-advertising, is. And that's a big difference. And what we show here, again, is that the effects are much, much larger. That you should not target people based on CLV. You should target people based on the derivative of CLV with respect to X. And we believe we're the first people in the literature to actually prove that point empirically. Okay? So what have we done? We've developed a Koich-like ad stock model that allows us to exploit exogenous variation over time. We've discussed potential sources of endogeneity, which again do not hold in our case, but they could hold in other cases. And again, we think we're able, in our limited case, again, we wish we had 10 different channels. We don't. So I say we're lucky in the sense that this firm only, by the way, this is another reason why all of you that are interested in estimating marketing effects should cozy up to the direct mail world. You know, we've kind of moved beyond them in some sense. But understand, as Shuming I see shaking his head, yes, these people knew this in the 70s. I remember as a kid, my mother would get, you know, essentially some months she'd get catalogs, some not. Some would have the red cover, some. The direct mail people had figured this stuff out 40 years ago, that you do randomized experiments. And fortunately, in this firm's case, again, it's the only form of advertising they do, email and catalog. So that made a big difference in our case. And again, the model can be applied in many cases. Just quickly, we assume linear effects of advertising. We know that's false. It's okay. We could build that in. We don't have competition in here. Last time I checked, competition affects sales. We don't have competition. Again, we don't, related to Igor's question, we don't deal at all with advertising copy or what could possibly be in it. We just say, did you get a campaign or not? We don't actually look. Michael's written some very nice papers on different aspects of campaigns and stuff like that. We didn't bring that in at all. So let me wrap up with just some final thoughts. I want to thank Kinshuk for inviting me here. I've taken pride in my entire career. Matter of fact, I kind of make it a must. Every time I publish a paper in marketing, I say to myself, my next paper has to be in statistics, because I try to blend the two. It doesn't always work that way, but at least I try to make that happen. I joke with people, I'm a fellow in psychology, education, and statistics. Not yet in my home field of marketing, so I'm still waiting. I also joke with people, I've won the best paper award in 6 different fields. I'm a 9-time runner-up in marketing, so I've never yet won the best paper award in marketing. So that's why I'm still publishing. I'm just going to keep publishing. One of these days, I'm going to win the best paper award and it's because Oded has cleaned up almost all of them. And Olivier, we got 2 people in this room that have cleaned up almost every award over the last 10 years. But I'm going to just keep publishing, keep working. The reason I wanted to provide you both an overview and a specific research project is, doesn't matter how old you get, how many papers you published, it's always about the next paper. I'm always looking for great ideas. I'm still as active and feel as great as I have been. I'm going to go back to my office later today and do some coding in R and Python and stuff, because that's what I love doing. So, Kinshuk, thank you for inviting me, and thank you very much.
So thank you very much, Eric, for that wonderful talk, for walking us through your 20-year journey, which has brought you to the point of causality, and we could have you here today. So thanks again. So now we'll break for lunch. Lunch is right outside, and we'll be back here at 1:30 for the second half of the day, which is on text mining. So we'll have a tutorial by Olivier Toubia, and then 2 talks, both application talks, one by Oded Netzer and one by Asim Ansari. So we'll see you soon. Thank you. Yeah, one request. Please don't bring any food into this room. Thank you.
mathematically true. It's the math. Just go to the math. There's no theorem. I mean, it's no theory. This is true. I don't know that paper. When you now nothing wrong with that experiment. But now I'm trying to weight them across experiments and not that problem. Like, no. I had never thought about it that way. You said during your talk, and then I was thinking about it. My class, basically the same question. But that makes sense. Thanks for asking the question. Some ideas. Yeah. Right.
Yes, really enjoyed it.
20 years allowed me to go back through my vita, which, you typically do that at tenure time and at full professor time. And now keynote time. I've been a full professor for 15 years, so I mean, it's just, you don't go through your vita that much. But go back, and there's actually a lot of fond memories of writing those papers.
You try your best, still this is done, still running off, but you're still working in order to come fast. It's kind of motivating, right?
No. That's not what motivates me. I'm just someone intrinsically interested in problems. It would be nice to win the best paper award in marketing, given, I'm a professor of marketing. But no, that's not it. Somebody else, I was joking. I should have made that clear. I was joking when I said that. Those types of extrinsic motivators, if that's the reason, those are the type of people that really concerned. What happens when those extrinsic motivators, when you get tenure, full professor, what happens when those things are gone? Those are the people I want. It's the intrinsic motivation. I do it because I don't want people to walk around. Also, why do you do it? Write papers, find stuff, learn stuff. Yeah, but we brought in, it was the control variables we brought in. We brought in all kinds of macroeconomic, locally economic variables. Those are the effects after controlling and putting in fixed effects for observables at the level of the zip code. I mean, the zip code controls, macroeconomic controls, there's some consensus data and the standard stuff that you get for zip code low. We did all of that stuff in there. And the part of it was interesting. Farther away from blue car
But one of the comments from Olivier was saying that because I did it in SEM models, algorithms models, and they advised me to do try to expand design. And I tried to I mean, like, you don't see those. The main feature is personalization in my work, in my contact, is when you set something online, when it's just laptop and open, and there you open your portal, you see that. So that's what we do, but in operations data, I mean, using the SES function. And I thought very, very good. And I contacted with a project which I easily do. And you're talking about that, but I'd like to show you something that I saw. Wow, this is a very interesting topic, and I think something that this guy shares something in common. Okay, nice to meet you. Good to talk to you. Have a nice day. Thank you. I don't know. I have to run the train. Daddy. Do you mean kind of a traditional store? Dissertation work is only in fact it's an augmented difference in difference method that is assessing Warby Parker's impact of launching a business of actually brick and mortar stores. It's the first paper that I've seen that kind of looks at online versus online and what the effect
the founder of the Google Marketing. Okay, that's me. Awesome. That's me. It's funny, I've been trying to get into that program for like a year now. Send me an email and I'll send a note to somebody. Yes, that's me also. That's me also.
So like the basic idea is, you know, like, you know, if you think about brand, like Google's big brand searches is like representative of awareness for a particular brand. What happens as like all these folks are losing their stores, basically, what happens when they close stores?
That's a great problem. That's a great problem. The impact on even Google branded searches on a physical store. I've never seen an analysis like that. I don't know anybody that has it. You guys have that data. I don't know anybody that's done that.
Marketing structure, like I don't know, like mail ads, right? Like Hurricane mail ads, they stop sending mail.
Well, again, it depends on how you want to treat the physical store, right? If it's purely just this is a debate we have, is it just purely a form of what's called awareness building, which I don't believe it is. But it's also, you know, service happens there, all kinds of demonstrations happen there, and so, but technically, the removal of a store can just be treated as a holdout where, you know, all of a sudden you drop out some channel, and now all of a sudden you want to see the impact of it. You have a data set on that.
So I know that like got around there are companies that have historical subscriptions.
Right.
I know that we have some like data sets for all these stores. So when you're fill out stores that are opening and closing, look at the rents,
Well, this way, you have my card. I can throw this out.
Okay, all right, right. Thank you so much.
Are you under the Chelsea office?
Chelsea, yeah.
Okay. Oh, thank you. 20 years of my life. Actually coming out of direct marketing. And so I think it's a great form of data you can flow. What agency? Small. Okay. Nielsen is basically $1 billion single source. No. I was in Minnesota. No. I was just going to go to the train station. I have to pick a 2 o'clock train and I can grab something. I'm good. Thank you for the offer. Okay, but yours is digital advertising? Yeah. But that's the effect size of your time. Right, no, the treatment is to not send.
request for you. Like, would you guys mind putting some text references? Not just papers, but a textbook kind of thing, because some of us would like to learn about.
Yeah, so in my slide, I have a lot of, complete references. Like
okay, you have some books that we can refer to.
They mostly, there's some survey review papers, but they're mostly papers.
I don't want to disturb you now, but I was just going to suggest that for Kinshuk, in case you guys have certain things that may be worthwhile looking at.
I mean, and that's why I put it in my slides. They happen to be more papers than textbooks.
Okay, sounds good.
So Olivier, I guess we've switched to this mic. Does this one work?
Is there a break after that? Or go straight?
There is a break at some point. Is there not? Let me check. So we, that's an old bottle, but that looks like a new bottle. I don't know whose bottle this is. I have it here, but what happened? We used to have mic number 1, now it's mic number 2.
Is it working?
It's working. Hello? Okay, it's working. So you can either hold it like they were doing, or just flip it to yourself, works fine too. Yeah, I don't think it has to be super like close to your mouth.
Yeah, but with the sweater.
Yeah, it's probably fine like that.
I can hear you on the...
And I will have time for 10 minutes, 5 minutes, 1 minute.
Start at 1:30.
Should we start? Yeah, of course. Hi everyone, I think we're going to start. How are you doing? Hi. After Kinshuk introduced the highlight of the day, which was Eric Bradlow, I guess I'm going to introduce myself now. Okay, you can see the... Okay, that's the post-lunch mode. Okay, so hi, I'm Olivier Toubia. I'm one of Kinshuk's colleagues in the marketing group here at the business school. So first of all, I'd like to thank Kinshuk for putting together this wonderful conference today. It was his idea, and it's such a tour de force. So thank you, Kinshuk, and congratulations. Okay, so thank you, Jeff, also. So it's such a good idea to do this, and I hope that this can continue this way. Maybe I put some effort in the slides, and I can recycle them another time, maybe. But anyway, so just to get a sense of the audience, so how many of you are PhD students? Wow. Outside of marketing, PhD students not in marketing. So which fields are you in? IT, IS, okay. Operations. So we have also some faculty. Yeah, any non-marketing faculty? Which field?
Cardiovascular behavioral medicine.
Okay, you're in the right place. And then we have some real people, I think some, we have some practitioners also. Yes. From which companies? You want to tell your companies? Or anyone else? Okay, startup, okay, cool. All right, so, so I will, so Kinshuk asked me to do a tutorial on text mining, and so I tried to put these slides together, thinking of this as a resource that will be put on the website for people who want to do research using some of these techniques. So I put some references in the slides, some details, formulas, kind of just to get you started if you want to do more. This could be a starting point, and then there will be the references to the actual papers that you can learn more from. I actually myself started learning some of these techniques only a
few years ago. And actually, I learned a lot of them from my PhD students, who learned them from some of our wonderful colleagues in the university. So we have Jalu here, who's just graduated 2 weeks ago from our PhD program, who's going to join Microsoft Research for 1 year as a postdoc and then HKUST as a professor. So she taught me a lot of what I'm going to talk about today. We have Ryan also. I will keep calling on him, just like Eric did earlier. Who's also a wonderful PhD student here, who's on the market this year, and who also is doing some great research. So we have a few other PhD students here, some colleagues. So try to convey some of the things that I've learned from them over the last few years. And so I think really the title I put in quotation mark because, I mean, it's a good title, but it's not exactly maybe the best way to describe what I'm going to talk about today. So text mining is almost an older term, I would say. So it suggests that you're mining, so like data mining, you don't know what you're looking for, you just try to look for stuff in data, which is not exactly what we talk about today. We talk also about theory-driven models and not just mining. And also it's text, and we'll talk about some models that can be applied to non-textual data. So it's not just text, and it's not just mining, but that's one descriptor. This will also have been natural language processing, which describes maybe more the trying to make meaning get meaning out of language as opposed to just mining for specific terms. Topic modeling is also a type of model trying to extract topics from text, which we'll discuss today. Unstructured data is kind of what we look at, although what does it mean to be unstructured? So it's basically things that don't come to you as zeros and ones right away. We'll talk about what could be described as mixed membership models or graphical models, which again are pretty loose terms. So this could be other titles of the tutorial today. So, but what I'll try to do is I'll try to, the outline is not easy to see here. Yeah, this is the outline. No, that's not. So this is the outline. So I will get to the models and the inference. So some more technical stuff. But I think given that most people here are in marketing, or at least interested in marketing, this would be meaningless if we didn't put this in the framework of research in marketing. So we'll spend some time first talking about what type of data we're talking about here, and then also try to think about what type of research questions we could address with this data. So I'll tell you about some of the things people have been doing. I will be biased towards my own research, but I hope to kind of maybe stimulate some of you to think about what type of research questions could we address with this data. So that's maybe the hardest part of a research project, is finding an interesting research question to study. And then we look at some models that can be used to study this data. I will go over the more basic models that talk about LDA and Poisson factorization, which has kind of some building blocks of a lot of these models. And I will show you how these models work, how you can estimate the models, and then I'll also show you how you can tweak them and extend them, and kind of some interesting ways in which you can push these models. But I will focus more on covering the basics. And also, I'd like at some point also to give you some practical tips on things like how do you report the results, some practical aspects, which are things that you just have to do it one way. And so this is just one suggestion for getting the research done. So hopefully with this, this could be again a starting point if you're interested in doing some research along these lines. This will give you the references, some high-level ideas, and then you can learn and develop some of these yourself also after that. And please feel free also to email us or ask us questions. Email me. I won't volunteer anyone else's time, but email if you have questions or if you want to follow up on today. And also ask questions if you want during the tutorial. That's completely fine. So let's start with the type of data that we're looking at. So again, we're not only looking at text data here, but the usually the type of data that we're going to deal with here. One of the main components of this is going to be basically a matrix, in which you have the rows will be documents and the columns will be words. So that would be kind of in the text analysis situation. We have a bunch of documents, and then each document has a bunch of words in the document. So that's kind of the basic structure. It's usually a count of how many times each word appears in each document. So that's kind of the basic form of data. Now, documents and words don't have to be actual text documents and actual words, right? So if you think of the documents, so in a few years ago when people started using some of these methods, the first place to go to was online reviews. It's marketing. Let's do something with online reviews, UGC. So a few papers have looked at reviews being documents. Other UGC, also other user-generated content could be used as documents. So Jai and I have spent the last few years looking at search queries. If you think about the volume of text that is being generated online every day, a big chunk of these are search queries that people type on Google or Bing or other search engines. So how do we understand the search queries? How do we learn from people's search queries about their preferences and so on and so forth? So this is a journey on which we embarked a few years ago, and I'll show you some of the things we've done along these lines. Oded and I also started a few years ago working with ideas as the document. So it's a text that describes someone's idea. And so how do we mine this? How do we understand the ideation process? How do we help people come up with better ideas? I also have some projects in which we look at entertainment products, like a movie script or a book as a document. And so maybe we can try to understand people's preferences for different types of products. Other creative products, like academic papers. There's been a few papers studying the text and the content of academic papers. I will show you also one current project on which I'm working that tries to understand these type of documents. So Ryan, and with Asim, Ansari, and myself, we have, so mostly Ryan in his dissertation is working with the brand logos and brand descriptions. So we're already moving away from text. Logos are pictures, but basically a picture is like a document as well. It's just the columns are not going to be words. There would be features of the picture, like the color, saturation, font, the shapes. So the columns don't have to be words, but this could be another application of the type of models. There's people at Columbia also, not in marketing, in computer science, who work with videos. So you have a YouTube video, for example, or a movie trailer. That could also be a type of document. There's an interesting paper also that was published last year in Marketing Science, in which they applied some of the models we talk about today to shopping baskets. So one row of observation is a shopping basket that the customer purchased. So you see we're very far away from online reviews. In that case, the column were the product that people purchased. So again, you can think of this framework of we have rows and columns, but you can put different things in the rows and different things in the columns. So I would like to invite you to think maybe there's other types of documents that we could study that we haven't studied yet, or that we could study better, and that could be opportunities for future research instead of just going with the obvious ones. In terms of the words or maybe the features, so in many of these, the columns are usually the actual words. So how many times does this word appear in these of these documents? But no, if you're studying pictures or videos, and you can extract features from that, and that becomes the columns of your metrics. In the case of shopping baskets, you have SKUs, what products the person actually purchased, and how many times did this person purchase this product in this shopping basket. So again, think about other types of features that you can extract that could expand the boundaries of what we study with these models. All right, so that's the data that we're dealing with. So just kind of to set the stage. So the basic building block is usually these observations with the different features. But oftentimes in marketing, we're looking at dependent variables. So maybe we want to know the rating that someone gave to a movie, or how many times someone downloaded a paper, or how many times did someone click on the result of a search engine. So often we have dependent variables that we'd like to capture. And so what I've seen quite a bit in the past few years is people first applying, let's say, LDA, which is one of the basic models we'll talk about today, to the text, extract some topics, some higher dimensional descriptions, and then use that as covariates in a model that will predict these dependent variables. So like a two-stage approach in which you first extract some higher level features of the documents, and then you regress things like purchase on these features. I would invite you to try to build models that actually do all of this in one step. According to the likelihood principle, all the relevant information should be in the likelihood function. So try to think of models that actually are going to jointly capture and model the actual content and the dependent variables and the behavior. And so the basic LDA model does not really allow you to do this very easily, although there's some extensions that do that. But Poisson factorization, which is the other model that we'll touch on today, is really well suited for this because of the structure of the model. It's very easy to capture dependent variables that are count variables. So we talked earlier about distance. I think Eric talked about the distance between, I don't remember exactly what. So with the Poisson framework, you can say, okay, here's a user that has some preferences. Here's a document that has some characteristics. And we're going to describe both of them in the same space of features. And then based on the distance between them, we're going to predict how many times this user is going to download this document or what ratings they're going to give to this document. So you can basically model some dependent variables based on the distance between consumers and documents or different types of units in this latent space. So that's a very useful framework, which I think might explain why, in the recent years, the machine learning community seems to have moved a little bit away from LDA and more towards Poisson factorization. It's kind of easier to expand and to capture some of these other types of variables. In marketing, we're still seeing mostly LDA, but we are starting to see a few papers that are now moving also to Poisson factorization. Oded?
Your thoughts on, I think there is a difference between machine learning and marketing or fields like marketing, where if the goal is truly just to predict the dependent variable, I can see why one would want to do it what you call a one-stage approach. I think the reason to do a two-stage approach is not just lack of sophistication of getting to the two-stage. Kind of like if you make the analogy to the earlier life of LBA marketing, maybe, which is vector analysis. There is a reason why you don't put yet the dependent variable in which brand we are talking about, and I'm just trying to understand characteristics of people because they exist outside of the world of brand, and then I want to know which one truly talks about the brand. Arguably, you could think the same thing about a document. A document has topics. The topics are independent of whether people like or don't like this movie. That's a whole different question. First, I just want to understand what exists in this movie or in this review about movie, and what your thought about the prediction of the dependent variable and the reason we do the LDA just for that, or I'm trying first to describe, and then I'm looking for the best predictive model.
Yeah, so LDA is basically like doing factor analysis. I told you about these metrics of latent Dirichlet allocation. Latent Dirichlet allocation. So it will become clear. As I'm sure many of you. How many people here have heard of LDA before? All right, so most people have heard about it, but it will become clear in the slides. So I think there's nothing wrong with just doing LD on the documents just to get a sense of the topics that are there. But if you do this in a way that's going to incorporate the dependent variable, this is going to kind of allow you to discover topics that are relevant also to the dependent variable. So it's going to guide already kind of a little bit the discovery that the topics are going to be informed also by the dependent variable. And maybe you don't want that. In that case, you can just do it on the actual documents. For me also, a little bit like Eric Bradlow before, I'm a little bit of a nerd or a geek, and so it's kind of nice also to work on models that are a little bit different, and so that's more of a personal taste. I think it's more elegant. But if the goal is really only to learn the content of a corpus of text, then irrespective of other types of behavior, then sure, you can just apply something like LDA. So that's fine also. I think oftentimes you see research where the goal is really prediction that use a two-stage approach, and there's nothing wrong with this, but I think it's more elegant if you can try to combine all of this in the same framework. And again, as we'll see, this is really highly feasible with something like Poisson factorization. It's kind of also fun to work with these models, but it's a matter of taste, maybe. Yeah. Yes, Jeff? Yes.
It's bug of work, which means it's completely excluded all meaning, all relationship between words. It's just frequency against document.
Yes. So the basic LDA is exactly that, but we'll see today how you can add some supervision to the learning, and how you can actually incorporate some other types of data within this. So the basic LDA is completely, it's just like factor analysis. You can try to find groups of words that tend to appear together, but completely, irrespective of any other behavior. But today there's many other tools that extend or that kind of a little bit different from that allow you to do what Jeb mentioned earlier: supervised learning, trying to link this to downstream behavior, trying to fuse different types of data. So hopefully I'll have a chance to show you some of this, or at least it will be on the slides. You can look it up after the talk. Yes, Navdeep? Oh,
yeah, I just wanted to make a quick comment on the previous one. Another advantage of combining the two stages would be that the uncertainty in the first stage is taken care of in the same estimation. Otherwise, there is sampling varies in the first stage and it gets mixed out in the standard errors that you might get.
I mean, again, the reason why the question is more, it's almost a philosophical one or behavioral one, in the sense that now we are biasing our exploration towards the dependent variable, which may or may not be what we want to do. So in that case, it's not just that obviously, if I can do things in one stage, I wouldn't want to bring the issue of always one stage is better than two stages, but what it leads to is biasing our exploration towards the dependent variable, which may or may not be the thing we want to do. Even if eventually I want to predict, I may want in the first stage to truly see what is it that this is saying.
Yeah, even maybe you can do this before, just exploratory analysis, and then maybe go to something different. All right, so so what type of research questions can we address? We just heard from Igor, this is just bag of words, it's just, descriptive. So in that case, it's pretty limited what you could do with these models. I mean, how much can we squeeze out of these models if they're just, like factor analysis type of models? So let's try to see what type of research questions people have studied. And again, I will talk about some of the things that I've been working on. It's my own bias, but I really want to maybe get you to think about other questions that you might want to try to study in your own research. So when these methods were first brought into marketing, the first instinct was to go to online user-generated content, like online reviews, and then try to understand from using some of these techniques, understand the sentiment of these reviews, understand the market structure, what is the, how close is Toyota from Honda, and this type of things. And so actually Oded had one of the breakthrough papers in this, and then Eric Bradlow left, so I won't even mention that he has a with Lee, and then also Jerry Tellis with Tirunai also. So some very nice, groundbreaking work trying to see how we can, use some of these methods to understand sentiment, market structure from user-generated content. So this was great. I mean, I would say today maybe it will be a little bit harder to publish a paper that tries to do this because it has been done already by a few people, and so there's a new type of insights or new types of methods. It might be a little bit limited. So unlike the speakers from this morning, I'm not really going to talk about advertising. I know that was a theme a little bit in the talks before lunch. So my own research, I'm interested in kind of two big areas. One of them is measuring preferences and motivations, and then the other one is ideation and creativity. So some of my research using these methods have been in these two areas. So measuring consumer preferences and motivations. So first of all, the paper that I mentioned earlier tries to model why people buy certain products by looking at the baskets that they buy. And so trying to use an LDA style approach to understand motivations underlying the shopping behavior. Is Alain here? Alain Lemaire is another of our PhD student. We have a paper with one of our colleagues in IOR, where we try to understand and model people's preferences for entertainment products. And so using some supervised version of topic modeling. And then Jay and I have some papers in which we try to understand consumers' preferences based on their search queries. So how can I learn something about what you're really looking for based on the search queries that you type, based on the result that are linked to this, and then also based on some downstream behavior, like maybe the click-through rate, the search volume, and so on and so forth. So there's examples of research questions that here are in that case about measuring preferences and motivations. And then also, as I said, I'm kind of interested in ideation and creativity. And so I thought a few years ago, we have all this data. Why only use the data to sell people stuff and advertise? Why don't we use the data to actually maybe help people come up with better ideas, be more creative, solve problems more efficiently? So Oded and I had a paper that was published last year in which we tried to mine the text of ideas to understand some properties of creative ideas and try to help people come up with better ideas. I have now a project that I'm working on in which I try to see now when you summarize the idea. So let's say you have a paper, you write the abstract. How can we understand the process by which you summarize the paper to an abstract, and how can we help you maybe write better abstracts? So something like you have a movie script and you're trying to write a synopsis, understand the process of summarization, and helping people come up with better summaries. And then Ryan, in his dissertation, is looking at logos, which is another type of creative product. And so how do logos convey the personality of the brand? And how do we understand this? How do we understand how these higher level traits of the brand are going to drive the features of the logo, of the brand description, people's perceptions of the brand? So these are another type of research question. So these are just a few examples, but really, please come up with more ideas. So that's kind of one of the fun parts of doing research is to try to think of these research questions that could be studied with this data. And so really, I encourage you to try to go beyond online user-generated content and sentiment analysis, try to see what type of interesting things we could study that were not maybe easy to study before, like new phenomena or new data on older phenomena that we could study using these models and using this type of data. So this is kind of just to set the stage that it's just not text mining. We're going to look at models that allow us to answer some of these research questions. All right, so some considerations when you come up with research questions. So back to Igor's point earlier, supervised versus unsupervised. So unsupervised learning is when you get a bunch of data and you're going to try to let the data speak for themselves without any theory, without any kind of prior, without any reinforcement that is going to tell the data what it should be, the model what it should be learning. And so the basic LDA and Poisson factorization models are unsupervised, which means that you just like factor analysis, you just extract from the data some patterns that come up. That makes it hard to test some specific theories or to build some priors and some other literatures into your research. So there are ways to get around this. One is to use seeding. So, for example, in the paper on the movies, we wanted to use some theory from movie psychology to try to have some hypothesis as to what type of features should describe movies. And so we seed the topic that we get to actually reflect some of these psychological traits that could be portrayed in the movie. So that's one way to try to bring some social science, maybe theories and prior into the modeling. The other limitation is the bag of words assumption. So as Igor said earlier, these are the models we're going to look at today are bag of words models, which means that basically you have a text, and what you capture is how many times the word appears in the document. It doesn't tell you where it appears. So there's no such thing here as an arc in the document. There's no structure. So we just know that this word appeared 20 times, but we don't know where it appeared. And so that kind of limits also a little bit the type of questions that we can address. And I think there's also an opportunity for research that will try to address these limitations. So for example, Greg Allenby had a paper last year in Marketing Science in which they tried to constrain the topics in each sentence to be the same. So kind of trying to put some structure into the text to try to kind of get to beyond just the bag of words, actually trying to see where the words appear in the document. And so I'm sure there's going to be some interesting papers along these lines in the next few years. That's kind of a nice next move for these type of models. All right, so hopefully now we have some ideas of what type of data we want to look at, what type of research questions we're trying to address, and then we can move into the model. So again, we don't have too much time, so I'm going to only scratch the surface, and the slides will be online. You can use them if you want as a source of references. I'm going to talk about two basic models and some of the extensions that are possible. The first one is latent directly allocation, LDA. So David Bly is a professor here in statistics and computer science. So he's at Columbia in the statistics and computer science departments. Some of our students were lucky enough to take courses with him. And so he, in 2003, published this paper with his advisor and someone else on this method that extracts topics from text based on the co-occurrence. So it's unsupervised, it's Bayesian, so it's likelihood-based, unlike factor analysis. It's actually a likelihood-based approach. that kind of generalizes something called latent semantic analysis in a probabilistic Bayesian framework, and just trying to extract topic based on words that appear together. So if you have a corpus, a bunch of movie scripts, and you look at the text, you can see the word crime tends to appear a lot with guns and with police. So maybe that gives you a topic that is that appears in these movie scripts. So visually, you have a document here. So again, this document here is going to be translated. So you have a bunch of documents, right? You have a corpus of documents. Each document is going to become one row in your data, which is going to tell you how many times does each of the words appear in the document, and then each document will be one row. We're going to factorize this matrix into two components. One of them is going to be a topic intensity. So every document is going to have a vector that is going to tell us what is the weight of each topic in this document. And then we'll have the other side of this will be the topic distribution. So every topic will be described as a probability distribution over the words. So for example, in this document, so this is a website about cars. You can see, we think that there's a pretty high weight on the yellow topic here. And the yellow topic talks about economy, compact, affordable, and so on and so forth. So you factorize this matrix as every document has a weight on these topics, and every topic has a weight on the different words. And so the product of these two give you an approximation of the initial data that you had, right? So and then probabilistically, we're going to assign each of these words to a topic. So when we read this text, we think that the word midsize here is probably belongs to the yellow topic. So it could be that midsize also appears in some of the other topics, but we think here, given the other words in the document, that this instead of midsize probably actually came from the yellow topic. Yes, Igor?
Topics you formulated, right? You said the topics, or not?
No, the topics. So the topics and the topic weight and intensities come from the data. And it's completely unsupervised.
So those topics have automatically kind of found in the data?
Yes, they're found automatically. They're not labeled automatically. So that's just like when you do factor analysis, you get factors and you have to label them. Here, same thing, you get some topics and you have to say, well, this here talks a lot about economy, so I'm going to label this topic the economy topic, and so on and so forth. The labels of the topics is what you have to, as a human, assign to the topics, but the weights here and the weights here all come from the data with no supervision.
But those are results, something like factor analysis or whatever, what appear linked.
Exactly.
Then you give the name.
Yes, exactly. So think of these as factors. So when the word economy appears a lot in a document, compact and affordable are likely to appear also in the same document. And so these tend to move together, and we can label them as the economy topic. So yes, Khaled.
Once you get the distribution for each topic, can you come up with distance between topics to say, for example, that America made is closer to economic, Japan and France are closer to economic cars than comfort?
Yes, you can do that, sure. Yeah, once you have the weights, you can look at their distance. But in that case, you can just look at any type of distance between the two. I mean, the topics are defined as vectors in this space of dimension equal to the number of words. So you can use any type of distance measure to look at how far they are from each other. Yeah.
But there should be hundreds of topics like that, right?
Yeah. Oh yeah, so that's a great question. So how do you know how many topics there are, right? So, and I was going to have a slide on this, which obviously I won't have time to go. So let's address this now. So yes, and that's kind of the typical trade-off when we, in machine learning and statistics is the trade-off between fit and complexity. If I have, let's say, 1,000 words in this vocabulary, I can have 1,000 topics. I'm going to explain everything perfectly, because every word will be its own topic and will perfect fit, right? But lots of complexity and poor interpretability. So there's a couple of ways to get around this. One of them is to use some sort of cross-validation approach to try to find a number of topics that make sense given some measure of performance. So maybe we want to make sure that that we don't overfit the data. You could also look at things like the Bayesian information criterion or some other like kind of DIC, deviance information criterion measure that will try to penalize for the number of parameters. And actually what I found in my experience is that there's a trick here, which is that when you look at the model, actually there's a prior that we put on the topics, which is going to induce sparsity in the topics. So actually the model itself has built in, because of the prior distribution, some aversion to complexity. So the model will penalize topics for being too complex. And so what I've been doing now, after spending hours and hours and wasting a lot of kilowatt hours of computing time, is basically, let's say we're going to allow for 100 topics, run the model with 100 topics, and actually out of those, some of them would just be empty. So if you look at the distribution, some of them would just be flat, empty topics with very little weights on them, just because the model is going to induce sparsity because of the prior distribution. And so that actually is in some cases at least, seems to be doing to do the trick. But yeah, that's one of the issues. How do you label the topics? How do you find the right number of topics, and so on and so forth? All right, so a few notations. So yeah, I'm going to go pretty briefly on this. So we have documents, we have words. The data is really how many times a word V appears in document D. We're going to allow a number of topics. Each topic is going to be defined by a probability distribution on the vocabulary of words. So if we have 1,000 words, we have each topic is a row vector with 1,000 numbers. And then every document is going to have a topic intensity on every topic. So if I have, 10 topics, every document will have 10 weights that will give us the probability weight on each of the topics for these documents. So this is the probabilistic model, very simple. This is the simplest form of the model. So you're going to put a prior distribution on the topic distributions directly, right? And then if this number here is less than 1, this is going to induce sparsity. It is actually going to penalize topics for having large weights. It's going to drive topics to having large weights on only a few of the words. And then we have the topic intensity is also coming from a directly. Same thing, if this is less than 1, this is going to try to force every document to have positive weights only on a few topics. So that's how you can induce sparsity. And so that's how you generate data in this framework. You draw topics from this directly distribution. You go topic intensities from this other directly distribution. And then whenever you have a word, so it's a token. So a token is basically one unit of analysis. So this here will be one token, which was assigned to the word midsize. And so the process is that we have this token here. We're going to assign this to one of the topics based on this distribution. So we're going to draw a color for this word based on this distribution. And then suppose that we draw the color green. Then once we know this is a green word, we're going to draw here from this topic to see which actual word we're going to put in this slot. Okay, so that's kind of the data generating process. So pretty simple. All right, so that's, again, unsupervised. Yes?
Is this monotonic with respect to transformations of WKD? Take logs of the word count? Would it get the same answer?
No, yeah. So because here in that particular model, the unit of analysis actually is a token. So it's actually a slot in the document. So even though the data are the number of times each of the words appears in the document, you model this as if each token was assigned one after the other. So it has to be count data. Same thing with Poisson factorization. The data actually has to be count data. So extensions, you can use add some supervision by saying, I want this topic to represent the notion of bravery. I have a bunch of movies. And I want one topic to really capture how much bravery is in the story of the movie. So you can use some seeded version of LDA that is going to say, there's a topic that's going to weigh more heavily on this set of words. I really want this topic to reflect some theory that I have from my knowledge of this market. So these are a few examples. Correlated topic modeling, we're going to allow for correlation between the documents in the occurrence of topics. And then you have hierarchical topic modeling. We're going to have some more general and some more specific topics. We're going to have this tree structure, and we're going to try to extract not just the topics, but the hierarchy of topics that go from more general to more specific. Relational topic modeling, we're going to try to model the fact that different documents tend to be closely related to each other. Maybe they tend to be cited by the same people, and so on and so forth. And then Jai and I have this paper in which we extend LDA. We call the hierarchical dual LDA. So we have two types of documents. We have search queries and we have web pages. So we have the queries that people type and the pages. Each of them has its own data generating process. They share the same topics, but also it's dual because there's kind of two separate types of documents. But it's hierarchical because we know that the topics in the web page are linked to the topics in the query. So it's a hierarchical structure that's at the same time dual. And so that's one example of extending the LDA framework. All right, so that's kind of just the, we're not talking yet about inference, we'll get there later. That's just kind of the modeling framework. Make sense? Yes? All right. So I'm going a little bit fast. If I'm going too fast, let me know, or too slow also, let me know. All right, so LDA was introduced in 2003 in machine learning. It started becoming popular in marketing a few years ago. Now we see more and more people using it in marketing. Now my sense is that the machine learning people actually have slightly moved maybe a little bit away from LDA and more towards Poisson factorization. I don't know if people would agree with that. And again, there's some convenience here. It's very similar type of model, but it just allows capturing count data and dependent variables much more easily. Because now I can say, okay, Ryan, his preferences are this vector in this topic space, and here's a movie, the topics of the movie, of this vector. I'm going to see how close Ryan is to this movie, and that's going to predict how much he likes this movie. So it's very easy and natural with the Poisson factorization to capture some dependent variables, a little bit easier maybe than with LDA. So that may be one reason why it's become quite popular. So it's the same basic structure. So again, we have topic weights. Instead of coming from a directly, they're going to come from a gamma distribution. So again, same thing, we can pick those to induce sparsity in the topics. Documents will also have intensity. Instead of coming from directly, they would come from a gamma distribution. And then same thing, we're going to multiply together the weight on the topics and the weight on the words. And so this is going to give us the rate of a Poisson variable. So now I have let's say 5 different topics. I'm going to see, okay, here's a document. What is the weight of this document on topic number 1? And I'm going to multiply this by the weight of this topic, the weight of topic 1 on word number 1. And then I'm going to let's go now, what is the weight of this document on topic number 2, and the weight of topic number 2 on word number 1. So I'm going to basically add up the different ways in which I could observe word V in document D. So it could come from different topics. So I observe the word mid-size in this document. Mid-size could come from a range of different topics. I'm going to see, okay, what is the weight, what is the probability that it comes from topic 1, 2, 3, 4, 5, and I'm going to add this up, and this gives me the rate with which I'm going to observe this word mid-size in this particular document. Khaled, yes?
So how is this different from the NDA? Is this just change of the
So at this point, exactly, that's the only difference. This is gamma instead of being Dirichlet, and this is Poisson instead of being, well, no, here's another difference. The dependent variable here is the counts, is how many times word V appears in document D. With LDA, the dependent variable was, here's a, I'm going to close my eyes, I'm going to draw a word from these documents. What is the probability that this word is mid-size, car, range, miles per gallon? So in the case of LDA, I was modeling the assignment of each slot in the document to one of the words. So let's say you have a document with 5,000 words. There would be 5,000 observations for these documents, and this slot was assigned to the word mid-size. This slot was assigned to the word car, and so on and so forth. Here, with Poisson factorization, the data is going to be how many times does mid-size appear in this document? How many times does range appear in this document?
But in an NDA, we care about how many times the word appears.
Yes. Yes. So I mean, the basic data is the same, but the model in the LDA is at the level of each token, and the model here is at the level of the word itself, and how many times it appears. But the data are the same because in LDA we don't care about the order in which the words appear. So we don't care that mid-size appeared, first place or 10th place. All we care is that it appears somewhere. But the data generating process is actually going to look at each token, each slot separately. as opposed to here, we just count the number of times the word appears in the document. Yes, Michael?
This looks like it would be an asymptotic version of LDA, because if you have multinomial counts with Dirichlet prior on top of that, the total number of each of those multinomial counts would be cosine, and then your marginals of your Dirichlet distribution would be beta distributions, and so which is just a ratio of the gamuts. So I wonder if this is just an asymptotic version.
I think that's a great question. Jill, Ryan, do you know the answer to this?
I don't think this asymptotic word. Another two more difference I add. One is you notice this molecule is simpler. Using LD, you have latent number of Z, which tells you the common membership of each word, but now you don't have that variable. Empirically, that particular variable will make the computation very cumbersome.
Right, I think that integrates that.
Yeah, but you're actually going to introduce that in the inference. You're going to actually introduce an auxiliary variable that is going to count how many times word V appear in document D coming from topic K. So actually, we're going to introduce this back in the inference.
So maybe asymptotic was the wrong word, maybe marginal was the...
So there's some interesting work by Matt Addy, who's at Chicago. I don't know if you know the name, but that links these two ideas. I don't know, I'm not super familiar with it, but I know that he uses, for instance, some version of like a Poisson regression model as a way of scaling and parallelizing some kind of like LDA type model. So I think there are fundamental links, but I don't know.
Yeah.
So one's not necessarily the other.
But in terms of performance, this one is better than LDA. In terms of picking a document, just as a text mining.
So Poisson 1, LDA 0. Let's go. Oh, yeah. So yeah. So I mean, I think really, I mean, if you, I mean, I think like people like David Bly, I think would probably today lean more towards Poisson factorization than LDA. And maybe just because it's kind of a new thing, it's cool and just do something different. But I think, I've seen, really, for us, if you want to kind of control, incorporate some other variables, it's really pretty convenient to have a Poisson framework in which you can, again, model very easily the some dependent variables as a function of the fit between different vectors. So again, I don't think we have too much time to get into the details of the contrast of the two. But again, I encourage you to look it up. That's a nice approach. LDA is fine also. I mean, as Artem said, it's not like it's worse or better. Just different approaches. But Michael is right. There might be some fundamental relationship there that we probably need to sit down and figure out, or maybe look for the literature on that. Yeah. So how do you pick the number of topics? So there's again a couple of, I would say maybe three main ways of doing this that I know of. One of them is to look at things like DIC, like some measure of fit that penalizes the number of parameters, like deviance information criterion, which in my experience always tends to favor more topics. So you can just keep adding topics, and the DIC will keep going lower and lower. So I haven't found this to be a very meaningful way of doing that. Another approach is to use something like cross-validation. So suppose you're running this model to be able to predict something. You can do, I think, what Stefan was taking this morning. You take 80% of the data, you train the model there, and then you see how it predicts on the other 20%, and then you pick the number of topics that is going to maximize this simulated out-of-sample performance. Another thing that people do now, and in some of David Bly's papers, that's what they do, and I've myself, in one of my current papers, that's what I ended up doing, because you just pick a high number, let's say 100, you run the model with 100 topics, and you know that all of these, because of the sparsity inducing priors, some of them will just be flats and empty. And so in that case, in one of my current projects, I have 100 topics, all of these maybe 25 are meaningful, and the others are just, the prior is the same as the posterior. There's no information there. So the model basically automatically zoomed in on 25 out of 100 that were meaningful. And that's much easier to do. So I mean, I think I'm converging a little bit towards this approach.
So here we have a graph, right? One set of nodes is the topics, the other set of nodes is the words. And you basically have a message passing kind of algorithm going back and forth.
Yeah, so that's why it's called a graphical model.
So in a sense, you cannot have cycles, because if you
Yeah. So it doesn't have to be a tree, but yeah, these are all called. Or it could be, I don't have the slides here, but so Jia likes to draw graphical models. It confused me for a year. I think I finally understand a little bit what they mean, but you can have these very complex models in which you have the different places that tell you the unit of data, and then you have the different nodes, and then the arrows. It doesn't have to be a tree. It could be a very complex model, but indeed, usually it's not cyclical. It's just, you have this is going to be influenced by this, and this is going to influence that. For me, I find it easier to think in data generating processes, personally, than in graphical models, but certainly the graphical model is one way in which people think about these models. Absolutely, yeah. So so let's see how easy it is now then to introduce some other maybe dependent variables. So this is a paper by Gopalan, Charlie, and Bly. Let's try to do content-based recommendations. So we have the Poisson model. So we have topics like before. We have documents. Every document has a set of topic intensities. Then we model the words in the documents. But then in their case, the documents were scientific papers, and they were looking at researchers who download these papers, or who read these papers. And so then you can have a user also, right? So you can have, in that case, researchers. Each researcher is going to have a preference for different topics. So if I'm a cardiovascular biologist, maybe I have certain topics that interest me, right? So this is going to be also coming from a gamma distribution. And then if I see a paper that has topics that fit my interest, I'm more likely to actually read the paper or cite the paper. So that it becomes very easy then to model this rating or this dependent variable as a function of the fit between my preferences and the document. What they introduced also in this framework is these offset variables, because there are some papers that maybe talk about some topics, but they appeal to people who care about other topics. So one of the examples they give is the EM algorithm paper. There's nothing about biology in the EM algorithm paper, but somehow it's read by biologists. So this is an example of a paper that, even though it's not about biology, it actually appeals to people who care about biology. So they have these offset variables that are going to explain a little bit better the dependent variable. And so this framework you can see here, the beauty is all of this is conjugate conditionally, so the inference is pretty simple. You can write the conditional posterior of every variable in closed form. And I won't have time to get too much into the estimation, but it's actually not, it could be pretty efficient. And you can tweak this in many different ways, and I won't have time to talk about this, but that's something with Jerath, for example. We look at people typing search queries, and we have the search result, and we have the search volume of the query, and then we have the click-through rate on the different results. And we can model all of this within this framework of Poisson factorization, trying to capture the fit between the content of the page and the preference of the user, and also capture some differences in preferences. Let's say if you search for Super Bowl, maybe you have different preferences before the game, during the game, after the game, so trying to measure some of these offset variables. So it's a very convenient and powerful modeling framework that you can apply in marketing context as well. And I won't have time to go, I won't pay Ryan justice to his dissertation, but you'll hear more about this, I'm sure, as he goes on the job market. All right, so inference. So very quickly, these models that I showed you are all conjugate, that is conditionally, which means that you can write down the posterior distribution of every parameter given the others. So if you want, you can use MCMC, which is a standard Bayesian method for estimating Bayesian models. That works. If you want to be even more efficient and to learn something new, you can also use what is called variational inference. And actually, if you come back on September 15th or 14th, David Bly will give, I think, a 3-hour tutorial on this topic the day before the big data conference that will be held at Columbia in September. So plug for the conference coming up in September. So I won't have time to get into a lot of... All right. So you'll have the full 3-hour tutorial on this. But basically, it's an approximated method that is going to try to approximate the posterior distribution with a member of a family of distribution, and going to try to find the parameters of this approximation that minimize the distance between the true and the approximated distributions. This runs at least one order of magnitude faster than MCMC. It's a deterministic algorithm that converges to a point estimate. But if if you have big data, it makes your life much easier. It's faster. It converges faster. All right. So I won't have time to go through this, but again, you have the references here and all the formulas here. So if you want to apply this could be maybe a starting point. So you can start with this and then look at the actual references. And so it's just basically a series of, it's an iterative algorithm. You update one approximation given the others iteratively until you converge. But instead, unlike MCMC, where you have to run thousands of iterations, here you converge maybe in 100 or so iterations. So it's just faster. And also there's less work per iteration as well. You don't have to draw variables from a distribution. It's all closed form deterministic updating. So all right, so a few practical things before we close. So again, it's more like a guide. It's not the only way of doing this, but these are ways that we've done with my co-authors, and no one has screamed at us yet. So these are things that you can do to maybe make it easier to conduct research there. So how do we select the vocabulary? So let's say there's 10,000 words that appear in the corpus with some frequency. How do we pick the ones that we want to put in the actual model? So there's something called the TF-IDF, and I won't go into the details, but basically that's a measure that's going to allow you to pick the words that. So it's going to remove the words that either appear everywhere, so there's no information because these words are in every document, or the words that appear only very infrequently. So it's going to allow you to keep the words that are a little more meaningful and more informative on the document. And so usually, you can take maybe 1,000, 2,000 words. So again, that's kind of the order usually that you end up with. Measuring fits, there's something called perplexity, which is basically some transformation of the likelihood function, which is measuring basically how surprised you would be to see this document given your model. And so that's, again, I won't have time to go through all the details, but there's the formulas here. No reference, but again, just Wikipedia probably would give you also some references there. So it's a way, both within LD and Poisson factorization, to get a sense of fits of the model. Number of topics, as I said, you can use cross-validation, or you can just set it to a high number and then let the sparsity do its magic and just end up with some topic that would just be basically empty and flat, and then some more meaningful ones. So this is a cool one. So topic visualization. So so you have all these topics. So basically the topic is a probability distribution or just a set of weights in the case of Poisson factorization. How do we visualize those? And so one thing we like to do is to simulate some content from the topic. So you can basically say, okay, here, if you were to draw words coming from this topic, here are 5,000 words, and then you put them in a word cloud, and then you see a word cloud of the words in the topic. Now there's a little tweak here, which is that there might be words that appear in every topic frequently, so it's not really as informative. So there's the notion of lift, which is how much does this word appear in this topic above, compared to how much it appears in other topics, or how much it appears in general in the text. So you can fine tune how much weight you want to put on the topic weight itself. So how strong is this word in this topic, and how much weight you want to put on the lift, which is how unique is this word to this topic. And so what you can do then is you can just generate some words, and it's kind of nice visualization. So this is from studying the text and the abstract of marketing academic papers. So I think the 1,300 papers that were published in JMR, Marketing Science, JCR, and Management Science from 2010 to 2015, I think. And so you can see here, the goal is not just to understand the content of the documents, but also how the documents compare to the abstract. So what is the process by which people extract an abstract from the document? And so what you see here are examples of topics, like this topic here is a topic that you see that its representation in the abstract is much smaller than in the document. So documents tend to talk a lot about variables, average, table, sample, model, And these words actually appear much less in the abstract. So you can actually model the process to which people selectively underweight or overweight certain topics in the abstract versus the full document. This is, on the other hand, a topic that tends to appear more in the abstract than in the text. So think like, the implications, the findings, the marketing mix implications. So that's a topic that usually gets overweighted in the abstract compared to the document. So again, I won't have time to talk much more about this, just a teaser. And I think I'm almost out of time. So we have like 1 more minute for maybe questions, if you want. Yes? No, yeah. So in that case, no. So no, yes. You just go to worldlaw.net. And location doesn't matter. If you want, you can create some semantic graphs. But in the case of topic modeling, there's no real within a topic. There's no connection between the words in the topic. Yes. Yeah. So I guess I'm a little bit old school. I use MATLAB myself. But I'm sure that Jen and Ryan can point you to some R and Python packages.
I think R is top model and L LBA.
There's one called quantitative analysis of textual data, somehow quantata. And you can do this in that package too. These word cloud without going to Wordle.
Yeah. Which saves you like 25 seconds each time.
I think there's like actually like a CRAN task view or whatever it's called about like natural language processing. So if you go there, you can find all of these packages.
Yeah, TM. Yes, the TM. I think R is TM. Yeah. So again, it's not hard to code this in MATLAB also. I mean, or maybe C or R yourself directly. I kind of like to keep control of the model and know exactly how it's estimated. And but there's also packages. I don't know how easy. I think Stan maybe would be a good way if you want to go out, if you want to extend some of the models. Maybe Stan, as Ryan tells me, that you can enter the specification of the model and it can estimate everything for you. Especially with So another project of Columbia, I guess, Andrew Gellman is.
And also has to use a variation inference because other MC won't be. It's really slow to do either.
Yeah. So again, it depends on how much you want to get off the shelf versus customize. It's a matter of taste, but yeah, there are certainly. It's a pretty big field. I mean, so people have in marketing. There's it's still growing, but it's a substantial field elsewhere. So there's lots of resources.
Do you have your own software or something working on that? Do you have your software, your own software?
Yeah. So actually, what I'm doing now, I'm creating using. So I don't have like a commercial grade software myself. I mean, Oded and I, we had the paper. We put together like a PHP, website where you can enter a topic and we help you come up with ideas. I'm doing now a similar thing where you upload your paper and then we help you write the abstract of the paper. But this is not commercial grade software. I mean, it's more like practical applications. Stan is actually a piece of software that is headed by Andrew Gellman, who's here at Columbia in statistics, and he has, I think, 5 or so people working full-time that are developing this software package, which is, I think, free and open source. So that would be the software to run the topic models. But in my research, we look more at some proof of concept of the applications. But I don't personally have software to run the analysis. Okay, so thank you for your time. And
Thank you very much, Olivier. So we break for about 15 minutes, and then we come back and we have 2 more talks.
Your slide when you started introducing.
Do I really need to wear it with my voice?
They are recording it, so they want you to. You can even put it down there. It doesn't really matter. It rotates. The thing rotates. You can like put it in the middle, like here, and it rotates.
Okay.
Well, not.
Can I put it here? No, too far.
Yeah, put it like
fine.
here.
Okay, fine.
Yeah, but we can do it later.
I would suggest putting it above that button so that.
So it should slide.
Yeah. Sorry.
Sure.
I'm gonna give you a 10 and a 5 and a 1. Just
what time?
People seem to resent this a little bit, so I'm just giving you a heads up.
And then start throwing stuff at me.
Yeah, and then
after the 0, start
This one
throwing.
is 30 minutes. Although oddly enough, Asim gets 10 minutes more than you, so I don't know. Maybe Asim was given 10 minutes longer than you. So I don't know if you want to
seniority,
fight him about it or what.
Seniority, of course.
I guess so.
Plus, his stuff is so much more interesting. So.
Yeah. But is this working?
I don't think so.
Hello.
Is it?
Hello. Actually, maybe it's not working.
I know it is.
It's working.
That's weird.
You have pretty loud.
Do you need a?
Yeah, exactly. I don't. That's why I put it low.
Yeah. Okay, so shall we start? You
Sure.
want me to introduce you?
No.
We had a whole
I think
stockpile of.
I put mine over there, so I have one. I brought with me my.
This is a good thought.
I'll talk to you afterwards. About I didn't mean that it's better. It was actually
Thank you so much.
I'll tell you what I meant by the including the DV in the exploration. It's not a matter of style. It's a matter or superiority for that matter. It's objective of what you are. And do you assume that the topics are exogenous to the dependent variable or not? What? I am. Yeah. Be careful.
No, you be careful.
What? Who?
Gil, he wanted to study that. I found his he actually wrote a paper on it.
Yeah, I know he did. Yeah.
You're here by everybody. Just remind me.
All right. Welcome back for, I guess, the last stretch, I think. No more breaks. It's myself and then Asim. He should be easier, right? He's over there. What I'm going to do is think about Olivier as being kind of the primary show, kind of the National Geographic show. I'm going to be the commercial break of that show. So that will be more of the application of text mining, application of machine learning and text mining. This is a joint work with one of our brightest doctoral students, Alain Lamer here, and Michal Herzenstein. I think our doctoral students received lots of airtime here. So this is Alain, and Michal Herzenstein is in University of Delaware. What this project is about, it's about trying to see whether there is value in the words that people write when they ask for loan default, for requesting for loan, and whether they will default on their loans. That's the objective. So let me show you two examples. We have borrower 1 and borrower 2. So borrower 1 says, I'm a hard-working person, married for 25 years, have 2 wonderful boys. Let me explain why I need the money. He asked for $75K. By the way, both of these, borrower 1 and borrower 2, have a very good credit rating. And they need the loan to fix the roof. Thank you, God bless you, and I promise that I'll pay you back. And then the borrower 2, well, in the past year, in a new home place has been more than great. The roof is now leaking, and I need to borrow the same amount to cover the cost of the repairs. I pay all my bills, blah, 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 on time. So just based on that, if that's all you know, they ask for $75K, $7.5K, sorry, good credit ratings. Who thinks that borrower 1 is more likely to default? Who thinks that borrower 2 is more likely to default? All right, so let's look a little bit deeper. I'll tell you in a minute who is more likely to default, but let's look at a few traces in their text, right? So what does borrower 1 tell us? That he's hardworking. Tells us a little bit about his family. Ask for help, and very polite. Promises, need help, and thank you, God bless you, and so on. What about borrower 2? Talks about the past year. Tells you some comparisons more than. and tells you details about their bills. Turned out that you guys, the majority of you are correct. In fact, borrower 1 is approximately 8 times just based on this text. This is the text that we created. This was not the actual loan. We kind of maximized the differences, if you will. Just based on the text, actually, this borrower is 8 times more likely to default actually than borrower 2. So that will be the objective of our work here, is to look at actually thousands of these and ask ourselves other traces, other patterns that are predictive of whether someone would default, over and beyond kind of more of the demographics and financial type of information that we know about these loans and borrowers. The context that we'll do it will be a platform called Prosper. Prosper is a peer-to-peer lending when people actually go and ask other people for loans. It has about 2 million members. The loans are fairly small, between $1,000 and $25,000. When you request a loan on Prosper, on any of these peer-to-peer lending platforms, there are a few of these platforms. Prosper is one of the biggest one. There is Lending Club is the second, actually the biggest one, but they're the 2 biggest ones. You ask, what do you provide? You provide a little bit of personal information, so a little bit of demographics. They go to Experian and get some of your financial information, for example, debt-to-income ratio, your credit score, so they get the FICO score. They don't report to the lenders exactly the score, but some discretized version of that. Then you provide some description of why you need the loan. And then what happens is there is a bid. There is a bid between lenders, at least at the time, not anymore actually in Prosper, but at the time that we had the data, a bid between lenders to give you the money. We will not be modeling this bid. We will take it as an input. We'll take the interest rate that you received already as an input into the model. And actually, arguably, if you believe like economists that this is an efficient market, in fact, the interest rate that you received based on the bid should already include everything that is in the credit score, in the text. All of the risk in this loan should be reflected by this. So after we control for that, nothing should be left. But I'll show you that actually quite a bit is still left. And our interest would be particularly that. Does the text explain over and beyond everything else, meaning the interest rate and everything else that we know about the person? So the question is yeah.
So I think that people are strategically writing this, or is it just their type, and that's what comes out?
Yeah. So I believe that people are that both exist, meaning what we did is, I won't show you much of that analysis, but we actually compared the words that lead to, that are predictive of default. I wouldn't say lead here, it's really more of a correlation predictions, that predictive of default versus the words that are predictive of whether you'll be granted the loan. And to some extent, that should give us some insight into this strategic thing. And there are things that actually weigh on one, weigh on the other, and there are things that actually exist in both, which would be the case where you say, look, it works with a strategic type of behavior. But if anything is strategic, it should appear in the whether you are rejected or not, right? Originally, whether you receive the loan in the first place. So again, the objective is there information in the words? Are they predictive first, over and beyond everything else we know? If they are, then what words specifically are predictive, and what type of writing style are predictive of default? So the data includes about 1.5 years of data from Prosper, about 140,000 loan requests. Out of these, 18,000 were granted. We will look particularly at those who granted for the purpose of default, for the purpose of whether they were accepted or not. We would look actually at the ratio of the 18 to the 138. And actually default rate at the time, now it's a little bit lower in Prosper, but at the time it was about 33% of the loans defaulted, so quite high default rates. What we were trying to do is we were trying to ask ourselves, let's try and provide all of the information that exists to lenders and put it into our models. We're trying to mimic the world on the sides of the lender in terms of just to understand whether the person, whether they're, not to mimic in the model the lenders, but rather whether, or if it account for everything the lender saw, would we still have any information on default? So what do lenders observe? They observe the amount, we'll put it in the model. They observe the interest rate, as we mentioned, if this is, because it's a Dutch-like auction, if the market is efficient, actually this variable should explain everything pretty much. Geographic location, where the borrower is in. We had some pictures. What we did with the pictures is we actually had human coders code them for gender, age, things along these lines. Prosper ratings. So Prosper provides seven ranges of your credit grade, and what eventually you see is these grades of AA for 760, FICO score of 760 or above, A for 720 to 760, and so on and so forth. So we'll include this obviously in the model as well. And then if you actually log in, you'll see also debt to income ratio, home ownership, other stuff that they get from experience. We'll put that into the model as well. And again, our main interest would be in here. Now this person here was very, very diligent. As you see, the purpose of the loan, generally it's way less organized than this particular snapshot. The text. It could be anything. People could write in any way and anything they want. So we'll have two purposes. The first purpose, we'll just put all of these variables into a mixer, mix them very well, and try to maximize prediction. And we'll do that using an ensemble learning algorithm, where the objective would be to ask, if I use my best predictive model, can I still predict better if I include the words in the loan? And in the second step, we'll try to explain, well, what specifically, which type of words are predictive of default, what particular writing style are predictive of default. In terms of text mining, just very basic kind of steps. The text mining here was fairly basic. We didn't do anything fancy. Started with breaking the text into words, then stemming. Stemming means I take a verb like ran, run, running, making it all one stem. We looked at bigrams. So instead of looking at one word at a time, credit card, we look at the combination of single words and two words at a time. One could increase it if you want to trigrams or more. And we remove the stop words. Stop words will be words like the, and so on, because we were less interested in them. And then as far as the analysis, Olivier talked quite a bit about LDA. We ran LDA, and one of the analyses we ran at least included NDL. Another one included more of a really simple dictionary when we looked more for the writing style. So again, pretty basic text mining here. So first, the predictive model. So when I was in grad school, I took a class from Jerome Friedman and Tip Shirani, and this was a machine learning class, but at the time they didn't call it machine learning. They actually called it nonlinear models. That's how they called it. There was a book, and so at the time machine learning was nonlinear models. And I remember sitting in the classes, one of the advices from Jerome Friedman was, when you go to a statistics paper, usually there will be a horse race of a table with a horse race of all of these models. First of all, go and cross the top one, because that's the current paper. They always win. But then look at the second one. That's going to be a pretty damn good predictive model. And actually, my mental meta-analysis that I've done on choice models suggests that number 2 is usually good only little. So that's typically kind of the second model, if you look at all of these papers that compared, at least in scanner panel data. But indeed, the practice was, when you are trying to build a model, predictive model, you compare different models and you choose the best one. But since the time I was in grad schools, actually things have changed in the way we think in machine learning, and we're saying, why actually pick the top one? I mean, different models are best in different areas of the data. Why not actually put them all together, model averaging, ensemble of models, if you will? And that's exactly what we did here, meaning instead of comparing these different predictive models and choosing the best one, what we did is we said, we looked at 2 logistic regression, 3 versions of tree-based. In fact, eventually only 2, because this one really performed horribly. We did drop it, but we took these 4 different models, estimated each one of them on the data with cross-validation and so on. And then based on cross-validation, what we do is we look at the appropriate weights for these models that then maximizes prediction. So really think about it as throwing everything to the mixer. Obviously, I want to be able to give you any inference from it, right? Because what we've done is just averaging bunch of models just to maximize predictions. Use then cross-validation, actually used it 10 times so we can get even some bootstrap, if you will, type estimates of how well we do in predictions. And then we compare the models with text and without text. So objective is to test, does text help? So what you see here, this is, for those of you that are less familiar with this is a ROC curve where you compare kind of the false positive rate to the true positive rate, which means perfect model would fall right here. Perfect model would be up here. So the better, the closer the model is to that corner, the curve is to that corner, the better, the more predictive it is. And in blue, you see the model with text. In green, you see the model that is just based on the financials, so the demographics, the FICO scores, in fact, everything but the textual variables. And in red is the model with only the textual variables. So what you see is actually that yes, it does help, actually, and I'll show you in a minute that it's statistically significantly so, but it does help to add the text. But even a model that just includes the text actually already tells you quite a bit about whether this person is likely to default. This would be kind of the 45-degree line, would be what you would get simply by chance. And here's the same thing, but now in numbers. This is what we call the area under the curve, would be that area, the area here. That will be the area under the curve. And what you see, again, the model with text only is about 67%, text and demographics 72.5%, and about 70.5% is what you get with just the financial and demographic variable. Again, we did it cross-validation, and what you find is actually this difference is statistically significant. So the text does significantly help in predicting whether someone would default. So all of that was great. We were happy with that, finding the text is predictive, but really we were interested in understanding, but what particular text is predictive of default? Zach. This is out of sample. Yes, so this is all on tenfold cross-validation. Yeah. No, yeah, does not have to go up because it's predictions. Yeah. And so we took three approaches to try and understand what type of words and writing styles are helping there in predicting default. The first one is a naive Bayes. So the idea behind naive Bayes, think about it like discriminant analysis. Think about it like trying to find the words that most discriminate between the defaulted and non-defaulted loans. In fact, think about that ratio. So the likelihood of the word appearing in defaulted loan to the likelihood of the word appeared in repaid loan. And we look for the words that are truly leads to this ratio is either being very high, meaning default, or very low, meaning they appear more in the repaid loan. So what you get at the end of this analysis, without getting into too much detail about naive Bayes, but again, not a complex method at all, you get a ratio for each word of how likely it would be appearing, the word appearing given that it's a defaulted, divided by the likelihood of the word appearing given that it was repaid. For example, the word God appeared 2.2 times more in defaulted versus repaid loans. Okay? So I don't expect you to see much in this. So what I did is I followed Olivier's advice and I put it in a wordle, where the size of the word in the wordle would be the ratio of this naive Bayes. Okay? And so what you see here, first in the middle, you see the words that were most likely to appear, where the ratio of appearing in default to repaid was the highest. Few months, loan explained, here's God, payday, God bless, and so on. These were words that appeared quite frequently. What we did then in these satellite wordles, we manually combined them into topics. Okay? This was not yet using LDAs, but rather us putting them into topics that seem to make sense. What you find is there is a topic that is about kind of the hardship of the person, right? Or words that are about the hardship of the person, stress, loss, behind, divorce, and so on. This is more of the, again, hardship, but more of the financial one, if you will, bankruptcy, payday loans, child support, and so on. And again, around there work type of hardship, right? Work hard, been working, current working, and so on. All of these were more likely to appear in defaulted loan than in repaid loans. Then there were words that around being very pleading, right? Need help, get help, just need. Again, some of these words may really explain the dire situation of these people who ask for the loan, but remember, all of this is over and beyond their FICO scores and so on. And then there was a topic about what you saw in the example I provided in the start, these topics about really being polite, right? I mean, God bless you, I promise, take care, thank you, hello, hi. Those who defaulted tend to express themselves in that particular way. Yes, so again, if I'll have time, I'll show you some analysis that we've done where we ran exactly the same naive base, but this time not splitting on default versus not, but rather splitting on receiving the loans in the first place or not. And then we compare the two to see which words explain rejecting or receiving the loan and which words truly explain default. But yeah, some of these words may have been said for them, like for example here, they may have said it in order to receive the loan. And in fact, you see for these words that they are affecting more actually receiving the loan than default. People tend to refer to others when they are defaulting. They mention more their family. They mention God, chance. All of these are words that are being mentioned much more, but those who defaulted versus those who did not. They tend to explain more. Those who default tend to use words like explain because they give you the excuses of why the credit rate is bad or why they need a loan in the first place, and tend to use actually much more of a future tense words, which is consistent, by the way, with literature on deception. That those who deceive tend to use language that is much more future tense relative to, for example, past tense. What do repairs talk about? Well, let's look at the opposite ratio, right? Or those who were high on the opposite side of the same ratio. Those who repaid tend to talk about their financial and generally positive financials, but also kind of showing financial literacy, right? They're actually talking about their bills and their car insurance and so on. They tend to talk about their bright financial future, right? I mean, that they're going to graduate. Some people may argue that wedding is not exactly bright financial future, but could be. They tend to talk about time, generally about, remember, both of them talk about time, but actually those who repaid talked more in years and less in months. They tend to talk more about the long term, but again, consistent with some literature on long-term planning. And they tend to use many more of these comparative type of words. More than, instead. So again, showing a little bit of more of also sophistication in the language they use. So that was one way of analyzing the data. But here we had to create these groups, right? So we say, why not use kind of Olivier's LDA? Well, as of today, it's yours, I guess. I mean, you own it today. So we said, let's use LDN. Let's see what topics exist in these loans. Luckily, I don't need to explain this. But one thing you can learn from this, by the way, this is quite similar in structure to the ones Olivier mentioned and Eva talked before about contagious. This is exactly the example why you can't infer from seeing similarity contagious. I haven't seen Olivier's slides. He hasn't seen mine. Both of us are affected by a third source, which is David Bly's slides. So, and actually both of us probably didn't receive it directly from David Bly, but rather from students who took the classes from David Bly. So this is truly homophily as opposed to contagion. Why you see similar slides on the LDA, but I won't explain it because that's exactly the same idea that Olivier explained. We look for topics that appeared in these loans. We ran again an LDA of it. Actually, Olivier was talking about how do we select the number of topics. This is the kind of Olivier was talking about measures of fit, of model fit. Here is with 1, 2, 3, 4, 5, and so topics. We found that actually for 7 topics, this perplexity measure, which was the measure of inverse of model fit, was minimized, and we therefore stopped at 7 topics. And these were the 7 topics. Actually, this is another thing that Olivier was talking about. These words here are not the words that were most commonly appeared here, but Olivier was talking about lift versus the frequency of occurring. This is the highest relevance, meaning balancing words that appear frequently in these topics but do not appear in other topics, right? Let's kind of think about it, the intuition behind these words. So there was a topic related to employment and school, topic related to interest rate reduction, people explaining their expenses, business and real estate type of loan, family, loan details and explanations, and monthly payments. And now what we do is we're going to throw all of these LDAs, are going to go kind of the two-step approach, if you will, put it into a model together with everything else. Remember, I also have all of the demographics and everything else. We're going to throw all of this in and see whether these, and in what direction do these predict default. We ran a kind of a simple logistic regression here. Binary variable would be default or not. What do we find? We find, first of all, let's look at the non-text variables. It's all in the expected direction. So the more money you ask, the less likely you are to repay. The dependent variable is 1 repay, 0 default. Credit grades all go in the expected direction. Lender rate seem to be obviously if you received a really high interest rate from the lenders, you're less likely to repay. Remember, this variable arguably could have captured the entire variance. Those who ask multiple times for loans are less likely to repay. But let's look at the text. They're kind of maybe more interesting. So the benchmark here would be the baseline. The one we dropped would be loan explanation. Remember, we saw already from the naive base that this is pretty predictive of the fact that you will not be repaying the loan. And indeed, talking about employment and school, remember all of these your future may look better. Indeed, you're more likely to repay. Those who talked about interest rate reduction, again, we saw credit card and all of these words that appear on repairs were more positive. Talking about family was actually lower. I think this is actually a good maybe, because often being asked, well, where is God here, right? Where did God fall in these topics? It actually didn't fall in a meaningful way. So I think it's interesting to see that kind of going back to this notion of, do I want to run an LDA or model that includes the DV? If I'm trying to maximize the difference between default and non-default, God plays a really important role in it. If I'm just trying to explain what are the topics in the loan, God didn't seem to come up at least not in a meaningful way. I don't remember which topic actually it belonged to. Alain, do you remember which topic it was highest on? Yeah, God is everywhere. That's true. Family. Was there a question, Asim? Yeah, I could.
God may have appeared.
Yeah. You never know where God appears, but yeah, may have. But you're right. We could have directed it towards it. Correct.
How do you explain this fact?
Because the objective of the two analyses was different. Meaning, the objective of the previous analysis in naive base was to look for words that maximize the difference between default and not. Here, at least in the step of the LDA, all we did was saying, tell me what exists in the data. God is not it was not a big and important word in that discussion. However, it is predictive of default. So I did not choose the topic here in order to maximize explanation of default.
It tells about lack of correlation of God with anything else. Otherwise, it would end
With anything else in terms in the text, but not with respect to the outcome variable. So if your objective is the outcome variable, you should actually use a method more like maybe the factorization approach, or if that's the goal, or the naive base where you are maximizing the difference between or SVM. You could use a support vector machine type of techniques to find the words and maximize differences. The last, I think we have about a couple of minutes. So the last thing I want to show you in the last couple of minutes is we said, okay, that's great. We have topics. The topics actually were fairly consistent with what we saw with a naive base. What about if you go one level higher, just the writing style of people? So here we used a really kind of low-tech type of method. What we did is we used a dictionary called the Look dictionary, the LIWC. And what this dictionary has, it has about 64 different dictionaries of words, and we looked at the frequency of each dictionary appearing in each one of the loans, okay? And this dictionary have dictionaries like positive affect, social word, plural, past, present, and so on and so forth. And here's so what we did is we run a model just similar to the model I showed before with LDA, but this time instead of the 7 LDA topics, we have 64 different dictionaries. This is a regression, but I don't expect you to see much of it. But there were actually 14 dictionaries that were significant in this regression, and actually they were very much consistent with some of the findings from the LIWC. One of them is that the notion of extroversion. So dictionaries that tend to load high on extroverts, on writing style of extroverts, seem to be also very much associated with default. For example, using more religious and body words, more social and human words, more motion words, less negation and less insight words. All of these are both appearing in writing style of extroverts and appearing and were more likely, significantly, were more likely to appear in defaulting loans. The second one had to do more with deception, where what we found was that many of these dictionaries that in the past has been found to appear in deceptive text, like more present and future words, more social words, more motion words, were actually also more likely to appear in these in defaulting loans. Longer text, so people who deceive often tend to write longer. We found that actually longer loan requests actually were more likely to appear by defaulting loans that eventually defaulted. So to wrap up, since we are almost out of time, what we really were trying to do here is ask ourselves, can we use the text to predict what these people would do? And actually, just from a text mining perspective, if you look at most of the text mining work, when often it is used merely to describe, for example, describe the market. Sometimes it is used to predict, but predict the market as a whole, predict how the stock markets would go, predict how the sales of a product. Here we are talking about the text predicting what that particular person will do in the future, and actually sometimes years later. And actually there are very few papers that have done that more in a general sense of text mining, taking text currently and predicting what that particular person would do in the future, and again here quite far in the future. And what we found was that it is predictive. There are particular words that are predictive, and again, particular writing styles, particularly extroverts and deception type of words. So with that.
I need the mic.
You need the mic.
And then, okay. So which one do you choose to show something there in the sense?
This is like
Which one? The red one. Okay.
So Asim, click this like in between your buttons here. It might slide, so it's better to the other one.
Like this, right?
No. Sorry, you had it right.
You had it this way.
Oh, this is the, okay,
Yeah,
thank you.
Slide, so it's better.
Sure.
10 minutes, 5 minutes, and 1 minute.
Okay, sure. So Ryan has already warned me that he is going to warn me about timing, okay? So I'll try to be as quick as I can. So, yeah, reception is important after deception. So, this is an application of what you would call sort of, text mining type of stuff. So it's a probabilistic topic model for recommendations and for personalized search. This is joint work with Young Lee and Jonathan Zhang. Both of them were PhD students at Columbia. So basically just a little bit about recommender systems in general. These are popular, as we all know, in e-commerce and digital content settings. And they are useful in contexts wherein we have a large number of users as well as a large number of products. Typically, users are unaware and uncertain about products, and therefore they basically need some recommendation, some help in terms of what might be suitable for them. And
one thing that is very important is that there is considerable heterogeneity in user preferences. And so this heterogeneity may actually be driven by what sort of attributes a user likes. Another important thing in this context is that the database that you work from is constantly evolving. New users sort of come into the system, as well as new products come into the system, and so you have what are called multiple types of cold start problems. What do you do when a particular product is just introduced, and if there are no sort of indicators of preference for that particular product, or if a new user has come in and we don't know really anything about this user, how do we sort of handle this type of situation? So in terms of recommendation systems, in this particular talk, we are going to focus on 3 types of interfaces that a user can sort of access. One is unconditional recommendations, which basically means I go to the system and I say, show me some products, some movies that I would like. Basically an unconditional request, and the system looks through the history of this particular individual and other individuals and makes some unconditional recommendation. The other is what could be called personalized search, which is basically saying the user can say, here is a product, a movie that I like. Can you show me other movies that could be sort of similar to this one? And so how can you sort of leverage on that? And the important aspect there is the word personalized, in the sense that we are not just looking for movies that are similar to a given movie, but those movies that would also appeal to a particular user. So there is some level of personalization in the recommendation that happens. And similarly, you can think of personalized search based on keywords. So instead of a movie, I can sort of type 3 keywords and say, show me some products that would appeal to me as an individual based on these keywords. So the keywords are used for relevance inference, and then the data from the individual is used to figure out among all the relevant products that might come up in a particular query like this, how do we sort of order them so that there is some sort of personalization in the results that come out. So basically, when we talk about a domain like this, there are a number of modeling and computational challenges. So typically, whether you're working from ratings or other type of data, we deal with a sparse database, and therefore borrowing of information is critical, in the sense that you cannot just rely on one individual. There is some sort of a Bayesian shrinkage that has to be part of the calculus here. There's also a representational challenge, especially if you are interested in content-based recommendation systems, in the sense that in most situations, the products do not come with very detailed information. There may be some dictionary that is available which sort of gives you the genre of a particular movie, or there may be certain products that attributes that the provider may have put in the database, but you need to somehow come up with other pieces which can sort of provide the content. So automatic feature extraction, luckily these days we live in a world of the internet, and so there is stuff on textual representations are available, reviews, people sort of tag products in different places, and so one can utilize this information to come up with an automatic extraction of features. And of course, this is typically a big data problem, in the sense the databases have large volume, so there are scalability challenges, and then of course variety, in the sense that if we integrate text as well as numerical data, you are talking about bringing these things together in a meaningful fashion. So just to give you an idea about the data that we will be working from, it's like ratings-based data. This is movie recommendations, so people have already sort of rated some movies. That is basically the dependent variable. In this particular data set, we are working from around 111,000 users. Of course, one can increase the size of this, and it is possible to deal with much larger data sets. Around 4,600 movies. These movies, basically, they are 21,000 unique tags. So people have tagged these movies with different sorts of words, and so we are trying to utilize that. And so in total, there is around 233,000 tag applications, many of them sort of, the same tag is being utilized by other people, okay? And so if you just focus only on covariates of the typical type, these movies come from 19 genres. So the genres are part of the database. But apart from the genres, we also want to include textual information from the tags to see whether the tags sort of, help. So this is the proportion of movie genres, and it's not very surprising. There's a lot of drama here, and then there is some sort of comedy, thriller, and so on. And this is a word cloud. Word clouds are quite popular today, it looks like. And so here's a word cloud of the tags, and as was already mentioned, this is basically plays randomly, but you could still sometimes see some interesting patterns. So for example, there is superhero nudity. If it is topless, it can be indeed disturbing, okay? So so now the other thing I wanted to sort of show basically was that one could leverage both the genre information as well as the tags. And so suppose you focus on children movies, you can see clearly that you have Disney, animation, Pixar, and talking animals and all that wonderful stuff associated with children's movies, and you also reassuringly see that there is no nudity in this particular word cloud, okay? On the other hand, again, when you look at romantic movies, you see, of course, romance comes there right in the middle, and then there is comedy, there is Tom Hanks, and, bittersweet, and all that sort of wonderful stuff, right? So you can see that, the tags that have been used for the movies are indeed sort of, have face validity. And the reason why we basically have this picture here is also to sort of, highlight a feature of the modeling, which is that, we are assuming that the genre variables that you have, like things like children movies and romantic movies, will basically guide the application of tags to the movies. And so I'll show you how that basically works. So this is just, the number of tags, histogram for each movie, and you can see that, basically around 10, 20 tags per movie is the modal sort of, situation. There's a lot of heterogeneity in the ratings, both across movies and across users. And so one could potentially sort of, leverage this heterogeneity in coming up with personalized recommendations and personalized search results, okay? So now let's spend a little bit of time talking about the model. I'm lucky that, Olivier did such a masterful job, and so you guys are all sort of, familiar with at least components of the model that I'm going to be using here. So this particular model integrates ratings, the covariates, which I basically mean the genre variables, and the textual descriptions or the product tags. And so the tags are kind of like a bag of sort of words or a bag of tags associated with each movie. And the idea here is to infer topics that are predictive of preferences. So basically meaning that we are not doing a two-step approach of inferring the topics first and then sort of using them in prediction. It is a one-step approach, and so the topics are supposedly going to be predictive of what the preference is going to be. And the covariates are basically there, the genre variables are there to guide the allocation of topics to the products. So of course, it is important, it is crucial to incorporate unobserved heterogeneity in this whole thing, and so we will be sort of using that. And finally, again, going back to sort of what Olivier has already shown, we will be using something called stochastic variational Bayesian regression framework for speedy estimation. So the idea basically is scalability. So variational Bayes has been around for quite some time in computer science, and in fact, of course, there are people who have done very good work in marketing. Michael is here, a wonderful paper in JASA on variational Bayesian inference long time ago. So This is what could be called a directed acyclic graph. So indeed, this is a graphical model, and as Olivier pointed out, sometimes it is difficult to figure out what is happening in this jungle. I am actually quite a believer in directed acyclic graphs if the graph is simple enough to sort of understand, because it definitely helps you in terms of having come from a MCMC tradition for 20 years. It is always good to sort of have the DAG so that you can write the full conditionals, but in this case this is probably not very sort of useful. So let's go to the generative model. Again, this is something that you have seen sort of before. So what's happening here basically is that you start off with a topic distribution for each topic. So you assume that there are certain topics that are being discussed in the tags. So maybe K topics. And so you have a topic distribution associated with each of those topics. Basically, a topic is a probability vector on the entire vocabulary, and so certain topics place higher probabilities on certain words, and so we want to sort of if we go back to old times, it's almost like factor analysis in some sense, and which word is kind of loading onto which topic. Then for each product, this is a mixed membership model, so we are basically assuming that each product or each movie has partial membership in many of these topics, and so there is a vector alpha which sort of gives you the document proportions, and so we want this alpha, the document proportions, to sort of be governed by the genre variables. So the idea being that if the movie is of particular genres, then you should expect a set of topics to be represented in that. So if you go back to what we saw here in this graph, in this figures out here, you can see that if the topic, if the movie is a children's movie, you should expect certain topics to be sort of discussed among the tags. And so how do you sort of allow for that? You basically take step 2, wherein you are saying that the topic proportions for a particular document, in this case a movie, will be explained by the x variables in that log normal, where the x variables is a vector of genres associated with the movie. And then of course you draw the topic proportions for each product from a Dirichlet distribution, which is being governed by the topic alpha vector. Then for each tag application, so as Olivier was mentioning, you're basically, for every tag application, for every token, you have to figure out which topic is this coming from. So that is basically a categorical sort of variable. So you can figure out it is topic 20 for this particular tag application. Then you draw the tag by going to that topic 20 and then doing another categorical sort of distribution, because the topic is basically a probability vector. So you deal with two multinomials there. Here's where the heterogeneity comes in from the user's point of view. So if you are a user who is interested in sort of seeing movies, first of all, the user will have a preference vector. So gamma I is a vector of coefficients, which basically give you an idea as to how much this user likes a particular topic. So this could be normally distributed multivariate normal with its own mean and its variance covariance matrix, and so you sort of pick up that. And then finally the rating, which is the dependent variable of interest, is basically a normal with the actual proportion of the topics being used as a vector along with the gamma I, which is our set of coefficients. Yes, Olivier.
The vocabulary is tags as words, right? It's the vocabulary of tags.
Yeah, so the vocabulary is the so if you go back to the vocabulary, we are basically talking about a total vocabulary of 21,255 product tags. Okay, so that would be how it would be. And the number of tokens we would be talking about is 233,000 tokens. So when we go back here, you can see again that this is the dependent variable YID, and then, it is being sort of, informed by a number of things. In particular, the topic allocation is Z and so on. So, another way of sort of, thinking about it, it is always interesting to sort of, think in terms of connections to previous literature. And so you will see that this is kind of in the same spirit of what in the old days, nobody really does this type of stuff anymore, but in the old days, structural equation modeling. Okay, so is something that used to be very popular. So you had a measurement sort of, equation, and you had a structural equation, and how do you sort of, relate the two. So again, many of these things appear new, but these are sort of, variants of stuff that statisticians have been doing for many, many years. So given this setup, then, estimation is another thing that one could sort of, focus on. So here's where we basically use variational Bayesian inference. The idea was that, when you are dealing with a large data set, MCMC sometimes becomes problematic, takes a very, very long time. And so it might make sense to think in terms of some approximation. So the basic idea of variational Bayes, as Olivier already mentioned, is that you take your posterior distribution. So if P of theta given Y is the posterior that you want to sort of summarize, instead of taking draws from the posterior as you would do in MCMC, you sort of approximate it with a simpler variational distribution. And the basic idea is to come up with a variational distribution that is closest to this posterior distribution in some sense. And the typical metric that is, so what we are doing, the advantage here is that sampling is now being replaced by an optimization, because you sort of say there is a variational family, and we are interested in figuring out the parameters of this variational family. So the inference is really about lambda. So if Q of theta given lambda is the variational distribution, and you are looking for values of lambda that would make this variational distribution as close as possible to the true posterior. And so the distance metric that is used is KL divergence, which is basically given by this wonderful, expression out there. This is a way of sort of, computing distances between distributions. And so minimizing the KL divergence is also equivalent to maximizing what is called the evidence lower bound. And so you are basically taking the joint distribution of the data, and you have your variational family here, and you are basically maximizing the elbow, and you would come up with a particular variational distribution. So obviously, when you do an approximation, there are obvious advantages in terms of speed. You are sort of, not doing thousands and thousands of MCMC samples. You are doing an optimization. So definitely it is speedier, but of course you lose out on some stuff, because any approximation will basically make there is some loss somewhere, and the loss depends upon the type of approximation we are making. And so there are many ways of sort of, doing variational Bayesian approximations, and this is a very active field. So variational Bayes is a hugely active field. Much of it is driven by Columbia. So, Columbia Data Science, familiar names, Michael Jordan, David Bly, John Paisley. These are all the people who are active in this particular area. So what we use in this particular paper is what is called a structured mean field specification. So this is a ugly posterior distribution out here, and so we basically break it down into a product of many different sort of terms, but we try to create as much of correlation as possible within each term. So that is basically what is called structured variational inference. So instead of assuming that each parameter is independent of each other, which is what is the typical mean field assumption, here you sort of take blocks of parameters so that you respect some level of correlation among some parameters. Of course, this is still a huge approximation compared to working from the complete posterior distribution. And so the other thing that we sort of focus on in this particular paper is that we use what is called stochastic variational Bayesian inference. Again, this is sort of very recent stuff. The paper that originally sort of propagated stochastic variational Bayesian inference was 2013-2014 paper. Michael Jordan and again David Bly and Paisley involved in that. And so the idea here is that our model that we have includes a mixture of both conjugate and non-conjugate components. So how do we sort of do quick variational Bayesian inference given that particular thing? One of the challenges, and I cannot go into details here, but one of the challenges that you sort of encounter the moment you sort of go into non-conjugate settings is to sort of how to handle gradients that involve the expectation of the elbow. And so in fact actually Michael's paper was one of the first ones to sort of deal with this stuff. And again, apart from that, so we use what is called a transformation approach to sort of do this. There is also stochastic natural gradients which can be utilized in order to sort of speed up things. So the idea of a stochastic gradient is that instead of using your entire sample to sort of compute the gradient, we are doing optimization. You need a gradient to optimize. So if you go through your entire sample to sort of compute the gradient, it is going to be too costly in terms of computational time. So how do we sort of compute the gradient in a quick and dirty fashion? And so this is where you use mini batches of data. So random mini batches are being used in order to sort of quickly compute this gradient, and then based on that you sort of go ahead with the optimization. So there's also many other interesting things to sort of think about in this. So how do you sort of select the sizes of the mini batch? You probably sort of start off with small mini batches and then you adaptively increase the size of these mini batches as you move towards the optimum. So what is a good way of sort of selecting this and increasing the sizes of the mini batches? And then of course whenever you do stochastic optimization, one has to sort of be careful about learning rate parameters, because if you choose the wrong one instead of convergence, you end up somewhere in heaven. And so how do you sort of do the adaptation? And this is also a very interesting field with a lot of sort of methods that are available these days to sort of guide the learning rate parameter adaptation. And so we use one of them which is called ADAM, but there are many others. So there is ADAGRAD, there is RMS Prop, and all this stuff. And so in fact a very good book on sort of looking at this stuff would be the deep learning book, which has which Ryan is intimately familiar with. I have to make a Ryan reference, and of course Gia also is very familiar with this type of stuff. And so you could sort of read up on this if you want to from that book. It's a wonderful book. So anyway, so we sort of, as is customary, if you want your paper to be published, you have to have null models, and so we have some of them. And so one is a hierarchical model using Jerath. So this is a fairly sophisticated model in itself, in the sense that it is a fully Bayesian sort of, specification. And so just to give you an idea, the null model, which is just, a hierarchical regression, nothing fancy there. Basically, the VB took 0.16 hours, so I don't know how much minutes it is, but very few. And the MCMC took only for 5,000 iterations, somewhere around 21 hours. And so you can see that, I think much of the complexity there comes from the fact that the number of sort of, users is large, and you are having parameters for each user. And so the full model that we sort of, estimated, sort of the VB took 5.3 hours, and the stochastic variational Bayesian took 1.3 hours, and MCMC is too painful to do, so we didn't even try, basically. Okay, so now of course when it, no, the SVB probably, but the whole fun of research is to code, right? I do research because I enjoy my research process. What's the point of taking a canned package and putting it on some data set, right? So how do you know for the SVB you're not so you have to obviously sort of, local optimum problems will be there whether in an SVB or whether in VB, because we are dealing with a complex optimization problem. And so so if you are doing SVB, maybe you can even run it multiple times. Okay, so there are no guarantees in the entire VB field itself. There are no guarantees. So
that's my issue. Is like when I took the class with Paisley and I asked him that same question, it's like in the machine learning literature, it's okay, we don't care that much. But in marketing, like when
yeah.
we publish a paper,
yeah. So again. This is a good question, actually, and thank you for pointing to the answer too. Okay, in the sense that when do you care and when do you not care, right? So I mean, it depends, right? In the sense that if you are doing theory construction, which is what most marketers do, theory like price coefficient should be negative type of stuff. Okay, so in that case, obviously it matters tremendously whether you actually are going to the optimum or not. But when you're thinking in terms of predictions, then machine learning guys definitely don't care too much about that. Okay, so going into insights, if you can think of insights in this particular domain. So the one idea about sort of recommendation systems is that if it is a black box, if you just recommend something, people don't know why that recommendation has come about, and that is exactly the reason why content-based recommendation systems are so much more better at sort of doing this job. And so this is topics. These are the topics out of a supervised model. So these topics are supposed to be predictive of the response. And so this table is very large in the paper, but I cannot sort of I cannot put everything in a slide. So I basically am showing you top 5 words within each topic. Okay, so these are 20 topics. The rows are the topics, and sort of across the row are the top 5 words. So you can see, for example, interesting topics. So topic number 19 is drama, romance based on a true story, Tom Hanks, etc. And then topic number 18 is fantasy, animation, Pixar, Disney, adventure. So you can see almost, this is the interesting thing, you see the aha effect. If your words that you have or the bag of words that you use are actually clean, you see that these topics are kind of like magnets that basically attract words that sort of go together. And so you'll see some interesting sort of topics out here. And the more interesting thing would be to sort of say, okay, if we take a movie, so Forrest Gump, this is kind of like a document, and so we are interested in seeing which topics does this sort of draw from. So it looks like Forrest Gump is drawing mostly from topic 19, somewhat from 20, and some from 1. And so if you go back to topic 19, you see that it is drama, romance, Tom Hanks based on a true story and so on. So you can see that clearly there is some sort of face validity to this whole sort of exercise. Now if you sort of go to each movie, each topic, and if you want to again sort of understand what the topic is all about, you could also sort of look at what could be the top 3 movies within a topic. And you again see for topic 19 you see Forrest Gump, Titanic, and King's Speech. And here for topic 18, which if you go back was fantasy, animation, Pixar, Disney, etc., you will see that How to Train Your Dragon, Up, and Beauty and Beast, and so on. And so you can see again that this is sort of some sensible stuff that you can get out of this. Now in terms of predictions, this is one thing that we could sort of focus on. So of course this is not a causal model like Eva's. All we can do at this stage is just to sort of show that it does better in terms of prediction. Yes, Khalid. So I was waiting for Khalid's question. Okay. No, it's okay, man. Sorry?
How much is the topic different from the genre?
Yeah, so we will come to that, right? I mean, one way to sort of see is the predictive performance. We're talking of tags, which are like 23,000 tags versus 19 genres. And so the genre is, again, if you go back to my very, very, this is just going back too much, but when you go back to the genre, you see that there are so many tags which sort of, can be potentially representative in the genre, okay?
What I meant is that couldn't you just reach a level where actually each genre is described by topic? So there are 19 genres and you have 20 topics.
Yeah, very, very interesting, yeah. But it doesn't seem to be the case, right? So, what you're saying is, my 20 topics, if they were basically isomorphic to the genres, then the two models should do a similar job in terms of predictions, and that doesn't seem to be the case. Okay, so in terms of predictions, we basically ran many different models with many different sort of topics. So 20 topic model, 10 topic model, 30, and so on and so forth. And then, as is generally the case, you can sort of use various measures of prediction. So you have the mean absolute differences, root mean square error, correlation between actual versus predicted, predictive R square, whatever you want. I mean, you can also do perplexity. There are 1,001 different things that are potentially possible. So given this, you can see clearly that it doesn't look like beyond 20 is needed, in the sense that the predictive performance is typically more or less the same whether you have a 20 topic model or a 30 topic model and so on. Okay, so then in terms of how well you do for the predicted versus actual, and the interest here is from the loss function is not basically symmetric, in the sense that most people go to a recommender system to ask for things that they would like rather than things that they would not like. And so it is good if the recommender system does a good job in terms of things that are liked by individuals. And so if you focus on this, you can obviously, there are too many numbers here, but the first thing obviously is that on calibration data you would do better than on holdout data. So that holds true here too. But also we see that when you compare the genre only model versus our 20 topic model, we basically see that there is a significant improvement, 0.73 versus 0.88, and then 0.31 versus 0.32 and 0.3 versus 0.39. And so there are various measures by which we can say that it is better than just including the genre. Yes, Jia.
I could be wrong. Similar reason you have 20 topics for that is because it's not because you are using text itself to do better recommendation. It's because before, if you only use genre, it's binary.
No. Genre is not binary, in the sense that one movie can belong to multiple genres.
But then it's now, so it's 0, 1, right? 0,
Yeah,
1,
so certainly.
But now you have text, you make the mixed membership, you allow move it to continuous space that help to
Yeah, so it is possible, but without the tags it would not be possible to sort of deal with that. And so the tags is providing some addition. Part of the improvement could come from being sort of instead of just a ordinary heterogeneity model, you are basically going to a mixed membership sort of specification. And part of it is that there is information in the tags that is not automatically accounted for in the genre. So in terms of recommendations and search, since I have 2 minutes left, I think, basically. So unconditional recommendations would be user one. If you just look, this guy seems to love action, Transformers, Armageddon, Pearl Harbor, Star Wars, Rocky IV, and so on. And then, user 3 seems to be a classic type of individual, starting with Casablanca, Rear Window, and so on. And so you can see that, these are two different types of individuals. And so you can sort of, use the Hellinger distance to sort of, figure out the distance between one movie and another. And so we can sort of say, okay, if you have Pulp Fiction, here are some movies that are similar to Pulp Fiction, and then those are some movies that seem to be similar to Lord of the Rings, just based on the LDA sort of, specification. And then you're saying, okay, if some user comes and says, give me some movies that are similar to Pulp Fiction, you will come up with, so this is search in some sense, so you will come up with a set of, say, 10 relevant movies. So the set is the same across the 3 users, it is only the ordering that is different, and the ordering is being computed based on the preferences of the user. So for example, user 3, Once Upon a Time in the West is higher compared to Drive, which is a 2011 movie. So it looks like, this is almost like a linear ordering in terms of the year of the movie. Similarly, if somebody comes in and says, I have 2 keywords, show me a heartwarming and inspirational movie, again, you can come up with a set of 10 relevant movies or 5 relevant movies, and then you can order these differently depending upon the preferences of the individual. So that basically I think I am almost on time. So thank you. If there are any questions, I'll be happy to answer. I think people are ready to go. So. Sorry? Okay, so one of the questions, I can answer you later if you want. But he asked, why do you need this set of 10?
Yeah, why can't my set of 10 best be different than God's set?
So you could certainly do that. I mean, that is also possible. I just wanted to say, if these were the relevant ones, how would you order them? Okay, so, Okay, I think we are done.
Yeah.
I have to give Kinshuk the last word.
So I just wanted to wind up. So first of all, let's thank all of the speakers with a round of applause. It was an excellent day. I personally learned a lot, which was my selfish purpose actually behind this whole thing. And and I hope you guys, everybody appreciated it. So, and thanks also to people to all the attendees. People are here from as far as California and Texas and North Carolina, not to forget Boston and Philly and other places. So, so thank you very much for coming. I just want to repeat that all these slides and all the videos of all the talks will also be posted online. So I'll send you an email out to you, maybe in a week or so, whenever that is ready. Yeah. So next is the reception. It's at Burnham and Schwartz, which is on Broadway between 113th and 114th. So you had to have pre-registered, but if you really feel like, you can come if you haven't pre-registered. So I'll see you there soon. Thank you.